now start the concept of flow-through pipes. We have seen laminar flow. Now we are looking at flow-through pipes. I have told you this is the most important chapter in entire internal topic. Regarding flow-through pipes, if you remember, we have already discussed a portion of flow-through pipes previously in the form of basics or fundamentals of flow-through pipes. So first topic over here was fundamentals of flow-through pipes. Fundamentals of flow-through pipes. Flow-through pipes. This topic is finished. We have already done this topic. So let me put a tick mark over here. After having studied this thing, what are we going to study over here? What are the other topics we are studying? You see, this chapter is important because it deals with the problems which we face in real flow conditions, right? So when you are working as an engineer in water department, water resource department and all, that time you are going to come across some problems which are dealt with in this chapter. The most basic problem you are going to see over here is regarding the concept of losses in flow. It is regarding the concept of losses in flow. Under this losses in flow, you are going to see two types of losses. One is known as major loss. The other is known as minor loss. You are going to see two types of losses, major loss and minor loss. Very, very important topic. As a matter of fact, everything over here is important. Fine. After studying the concept of losses, now we'll talk about a particular case, which is connections in pipes. You see, when you are connecting two reservoirs with a particular pipe, it is not always possible to have a single pipe. You'll have to go for compound pipes. That is where series connections and parallel connections come into picture. So second topic you are going to have over here is connections in pipes. Connections in pipes. All these are real-time problems. You're going to have two types of connection. One is known as series and the other is known as parallel connection. Parallel connection. You can expect problems from here also. After this, a very, very interesting topic, one of my personal favorite topics. It is called as grade lines. You're going to study the concept of grade lines. Grade lines basically help you visualize Bernoulli equation. This is a particular topic where you are going to put a diagram picture of Bernoulli equation. You are going to see two types of grade lines. One is known as energy grade line. The other is known as hydraulic grade line. Energy grade line and hydraulic grade line. Two types of grade lines you are going to see. Fine. After having studied the concept of grade lines, now we are going to look at a particular type of pipe from where questions have come in many examination very frequently, very important for interviews also, and that pipe, very famous pipe known as siphon pipe, flow through siphon. We'll talk about flow through siphon pipe. Siphon pipe. This is the next topic we are going to have. After having studied flow through siphon, next thing we are going to study some types of flows. One flow is branching of pipes flow or three reservoir problem, very interesting problem. Recently in GATE examination that problem has appeared, that is branching of pipes. Branching of pipes. You can also call it as three reservoir problem. Three reservoir problem. Apart from this, you will study a topic by the name pipe networks. Pipe networks. Very, very logical topic. Pipe networks. After this, you are going to see two types of power. One power is received from the fluid, one power is supplied to the fluid. The first power, which is received from the fluid, is known as hydraulic power. It is known as hydraulic power. The second type of power you are supplying to the fluid. You know this thing, when we supply power to the fluid, we are going to use an external agent, for example a pump. Therefore, we call this power as pumping power. We call this power as pumping power. Pumping power. After having seen this, we will see some miscellaneous problems. Miscellaneous problems. Let us say, I just write like this over here. Let me tell you, these problems can be in the form of variable diameter, can sometimes be in the form of a pipe which is having discharge throughout the pipe taking place. Imagine you are having a pipe and every distance later you are having a tap which is issuing water continuously from that particular pipe. So how to deal with those type of problems we are going to see over here. Miscellaneous problems. We'll try to develop some standard results over here. At last you are going to see a particular concept, famous concept known as water hammer effect. It is known as water hammer. The syllabus over here is quite big, but don't worry, if you understand the basics, it is going to be quite simple for you. See, all you require over here is to understand the concept and be good with mathematics. It is sufficient, you can solve any problem over here. So these are the various topics we are going to study in the case of flow through pipes, and one topic has already been studied, that is fundamentals of flow. This is going to be quite lengthy also. In total, it will exceed around 5 hours. Let us start the topic of losses in flow. The concept of loss in flow is probably the most important topic in entire flow through pipes. Very important topic and quite a lengthy topic also. How to understand this concept? Let's start with understanding the meaning of loss. What do we mean by loss over here? I have actually discussed the concept of flow previously also in the chapter of energy equation, but let us recall. Remember that whenever a real flow takes place, it is supposed to have some kind of resistance experienced. Imagine you are having some flow taking place over here. A real flow is taking place in this particular direction. If a real flow takes place in this direction, then it is going to experience certain resistance which is opposing the flow. So let us say the opposition I'm showing in the backward direction. This, let us say, is resistance against the flow. What happens because of resistance? If there is some resistance, the flow will give away some of its energy to overcome this resistance. So every instant you are moving forward, let us say you move forward over here by some distance, you are going to give away some of your energy in order to overcome the resistance. Whatever energy you are keeping on giving away to overcome the resistance, that energy in our subject is known as loss. So I can define loss as the energy sacrificed, or you can also say given away. If you don't want to use sacrifice, you can also use given away by a fluid in order to overcome resistance against flow, is known as loss. The energy sacrificed by the fluid in order to overcome the resistance against flow is known as loss. Now, the type of loss depends on the type of resistance. This word is very important over here. So if you are having a particular type of resistance, corresponding to it, you are going to have a particular type of loss. At this stage, we are going to divide the loss into two types. So let us say there are two types of losses. There are two types of losses. In a fluid flow. The two types of losses are, first one is known as major head loss. Or if you are looking at head, you can say major head loss. The second type of loss is known as minor loss. It is known as minor loss. In simple language, you can say that major loss is caused due to fluid friction, or you can also say it is by the virtue of wall shear stress. It is caused by the virtue of wall shear stress. Coming to minor losses, what is the reason behind minor losses? We'll study it in detail, but at this stage just understand that whenever there is a geometric change geometric change in the pattern of streamlines, in streamlines pattern, then you are going to observe minor losses taking place. So you are having two types of losses. One which is by the virtue of friction is known as major, and one by the virtue of abrupt geometric changes is known as minor. After having seen this much introduction for losses, we are now going to look at each of these in details. Let us now look at major head loss or major loss. Major loss. Let us start writing some points regarding this major loss. The first point, what is the cause of major loss? The cause of major loss I have mentioned some time back. Let me again write this. It is caused due to fluid friction. Fluid friction, or you can also say due to wall shear stress. Wall shear stress. You see, wall shear stress in our subject is something which is very similar to friction. That is why in place of fluid friction, you can also include the concept of wall shear stress. I will give you a proof of this thing in some time. Now, second point over here. What is the formula for major loss in the case of flow through pipe? The formula for major loss, head loss major, the formula for major loss is given by something known as Darcy-Weisbach equation, which we have already proved. And the formula says it is equal to FLV square by 2GD, FLV square by 2GD. And if you would convert the velocity in terms of discharge, then this formula would become 1 by 12.1 FLQ square by D power 5. So this is the formula for major head loss in the case of flow through pipe. And this formula is known as Darcy-Weisbach equation. This is known as Darcy-Weisbach equation. This is known as Darcy-Weisbach equation. And let me at this stage also recall that F over here is known as Darcy friction factor. Darcy friction factor. It is known as Darcy friction factor. And the value of F, I have mentioned all these things previously also. The value of F is equal to 4 times F prime or F dash. And what is F dash over here? F dash is known as Fanning's coefficient of friction. F dash is known as Fanning's coefficient of friction. Fanning's friction coefficient. Friction coefficient. So now you are seeing over here that the value of head loss, major is proportional to F. It is proportional to F. Let me also mention over here, it is proportional to F power 1. Now, if head loss is proportional to F power 1, this is not dash, rather it is F power 1, numerical 1. Okay, numerical 1, let us say. If it is proportional to F power 1, it means that your head loss is directly related to friction. That is why I write over here, it is caused by the virtue of fluid friction. Recall one more thing. The value of F was equal to 4 times tau naught divided by half rho v square. I hope you remember this thing. We have studied in the fundamentals of internal flow that F is equal to 4 tau naught by half rho v square. That means F is having a direct and linear relationship with tau naught. From here I can also say that head loss has to be proportional to tau naught. Head loss should be proportional to tau naught. That is why I say it is caused by the virtue of shear stress. If you give me the idea of wall shear stress, I can give you the idea of how much head loss major is taking place. So these two are the fundamental points regarding major head loss. Okay. Next thing, let us see how this head loss or what this friction factor is depending on. So third point over here. Third point, what is friction factor depending on? You see, I'm going to take two cases. 3.1, that is laminar flow case, let us say. In the case of laminar flow. In the case of laminar flow, we know that the value of F is equal to 64 upon Re. The value of F is equal to 64 upon Re. We have actually proved this thing. Now from here I can say that the friction factor in the case of laminar flow is going to be only a function of Reynolds number. It is depending only on Reynolds number, nothing else in the case of laminar flow. Second thing, let us say I'm having turbulent flow. 3.2, let us say I have turbulent flow. What is this friction factor depending on in the case of turbulent flow? This is slightly tricky. It is here that turbulent flow becomes slightly difficult for us. In the case of turbulent flow, friction factor is depending not only on Reynolds number. Apart from Reynolds number, it is also going to depend on something known as surface roughness. Epsilon over here is known as surface roughness. It is known as surface roughness. So in the case of turbulent flow, your friction factor is depending on Reynolds number. Apart from Reynolds number, it is going to depend on surface roughness. Remember this thing. From here, theoretical questions have appeared multiple times in IES examination, and these questions will somehow come in the form of a statement question. Okay, there were cases where they have given choose the correct statements, in which one of the statement was, in the case of laminar flow, head loss is influenced by surface roughness. What would you say? In laminar flow, is head loss influenced by surface roughness? No, the statement is wrong. Why? In laminar flow, if friction factor is independent of surface roughness, it implies head loss also is independent of surface roughness. And what would you say if I say that in turbulent flow, head loss is influenced by surface roughness? The answer is yes. In turbulent flow, F is dependent on surface roughness, therefore head loss also can be dependent on surface roughness, is it not? So these kind of theoretical questions can appear from this point. Next point over here, we have seen 3 points. Let us look at the fourth point over here. Point number 4. I want to know how is major head loss depending on the length of the pipe. If you see over here, we have the formula of major head loss as FL V square by 2GD, or equal to 1 by 12.1 FLQ square upon D power 5. D power 5. If you see in either of these equations, you are finding the power of length is 1 over here. That means head loss linearly increases with respect to the length of the pipe. So let me write a statement over here. I can say major head loss. Let me, one moment please. Let me write major head loss, major head loss, head loss increases linearly along the length of the pipe. Major head loss increases linearly along the length of the pipe. Now look over here, there are two words important for you. One word is increase, the other word is linear. Other word is linear. The immediate effect of this is something which we have already seen, okay, and that is regarding pressure. Now recall, how was pressure increasing or decreasing? If you recall, you can say that pressure decreases linearly along the length of the pipe. Pressure decreases linearly along the length of the pipe. We have seen this thing. That is why we said that the value of minus dp by dx is a positive constant. I hope you remember this thing. Of course, all these things are going to be functional provided you are having steady flow and you are having a fully developed flow. So you see, pressure drop and head loss, both of them are related to each other. By the virtue of drop in pressure, there is a rise in head loss. At this stage, I'll do one thing. I'll give you a graph. If you find it difficult to understand, you can skip the graph also. Let us say we can construct a graph to understand the idea of head loss and pressure drop. Imagine this over here is x-axis and this is my vertical axis, y-axis over here. Let us say I take a portion of a pipe. Okay, I'm having a certain pipe over here. I'm having a certain pipe over here. There is a flow taking place in this direction. Flow is taking place in this direction. If I look for the pressure, then I can say that the pressure is going to drop linearly along the length of the flow. The pressure is dropping linearly along the length of the flow. So in this, the value of y is basically pressure. Y is pressure over here. So pressure is decreasing linearly. And what will happen to head loss? The rate at which the pressure is being lost, exactly at the same rate, but in the opposite direction, I'm going to have rise. This is head loss. So whatever is the slope of this thing, exactly an opposite slope I'm going to get over here for the value of head loss. Are you following this thing? So pressure is decreasing linearly, head loss is increasing linearly with respect to the length of the pipe. Chaliye, after having seen this, now let us look at the fifth point and the most important point. Fifth point, I regard this point as the most important point in major head loss. This is regarding how is head loss influenced by velocity, discharge and diameter. So let me write over here, influence of three things I'm looking for. One is velocity, one is discharge and the other is diameter on head loss major, on head loss major. This is my idea over here. Under this, I am going to take two cases. Case 1, let us say 5.1 case. 5.1 case, I am having laminar flow. I am having laminar flow. Case 1 is laminar flow. Now we know in the case of laminar flow, the value of F is equal to 64 upon RE. 64 upon RE, which is also equal to 64 times mu upon rho Vd. 64 mu upon rho Vd. Let us use that value of F in the Darcy equation. So I know head loss, which is FL V square upon 2GD is equal to 64 mu upon rho Vd into LV square upon 2GD. This is the value I'm having. Now, I can say from here that the value of head loss is equal to, if you simplify this equation, you are going to get 32 mu VL upon 32 mu VL upon gamma times D square. 32 mu VL upon gamma times D square. If I rewrite this equation by taking discharge in place of velocity, then this value is equal to 128 mu QL upon pi times gamma times D power 4. This is the equation I'm having. At this stage, I am now going to look at how the head loss is varying with respect to velocity, discharge and diameter. First thing, look at this equation and tell me head loss is proportional to velocity power how much? Velocity power, you see over here, the power is 1. So I can say head loss is proportional to velocity power 1. And come to discharge now. Head loss is proportional to discharge power how much? Again you see 1 over here. So you can say head loss is linearly proportional to velocity. Head loss is linearly proportional to discharge. Fine, I have satisfied this thing. Next I have to look for diameter. I have to look for diameter over here. Please observe, I am having two variations. One is head loss proportional to 1 by D square and head loss proportional to 1 by D power 4. Two variations. Which variation is going to be correct? Which is the correct variation over here? The answer is both the variations are correct, but under the corresponding conditions. For example, this variation is correct provided the condition is when velocity is going to remain constant. If the velocity is kept constant or if the velocity is maintained, then head loss is proportional to 1 by D square. And when is this variation going to be correct? Come on, please guess now, or you can check over here and tell me. This is going to be correct provided discharge is going to be a constant. I hope you are following this thing. So head loss proportional to 1 by D square provided velocity is constant. Head loss proportional to 1 by D power 4 when discharge is constant. Fine. If you are having a doubt regarding where we are going to use this, let me help you with a question. You see, the kind of questions which appear over in this topic are something like this. The questions can be, let us say there is a pipe which is having a length L, it is experiencing certain discharge Q, let us say. It is experiencing certain discharge Q. and the diameter over here is equal to capital D. Now the question can say it is having laminar flow. For some reason we are removing this pipe, replacing with a pipe, let us say, of diameter 2D. We are replacing with a pipe of diameter 2D. The length again is equal to L. Okay, the diameter has become 2D, length is still equal to L. If he is asking that if the head loss in this particular case was equal to H, what is the value of head loss in this particular case? What is the value of head loss in this particular case? You cannot answer the question now. You have to ask further whether the value of discharge is maintained as constant. Let us say if the value of discharge is maintained as constant, then you will say, since discharge is constant, the value of head loss over here is proportional to 1 by d power 4, 1 by d power 4, which implies H2 upon H1 is equal to d1 upon d2 whole power 4. From there you can get the answer. Are you following this thing? Imagine if the question said that the velocities are kept same. Imagine if the question says the velocities are kept same. Then what would you do? In this particular case, one moment please. In this particular case, you would say that since velocity is constant, now the relationship is head loss is proportional to 1 by d square. Now the relationship is head loss proportional to 1 by d square, which implies H2 upon H1 has to be equal to d1 upon d2 whole square. This would be the relationship then. Are you following this thing? So these kind of questions are pretty common in examinations, in all examinations as such. GATE, IES and any PSC examination, PSU examination, you will find questions of this sort coming in laminar flow and turbulent flow also. So this was regarding the variation of head loss with respect to velocity, discharge and diameter. We have seen only for laminar flow. Let us move further now. Let us now talk about turbulent flow. So this, let us say, is 5.2. I am having turbulent flow. 5.2, this is turbulent flow. Chaliye, let us see this thing. Under turbulent flow, I am going to take two subcases. So under subcase, we are again having a subcase, let us say. This subcase is, let us say, 5.2.1. What is a subcase? Recall we mentioned in the case of turbulent flow, friction factor is going to be a function of two things. One is Reynolds number, the other is epsilon. It's going to be a function of two things we have mentioned. But there are some cases in turbulent flow where the effect of epsilon is going to be so less that the effect of Reynolds number will increase. I am not saying Reynolds number is high. I am saying effect of Reynolds number is high. There is a difference. I hope you are following. Let me repeat this. We know that friction factor in turbulent flow is a function of Reynolds number and surface roughness. In some cases what happens, effect of surface roughness is so less that the effect of Reynolds number is high. We can say that in this particular case, the value of F is purely a function of Reynolds number. This can happen. This is my 5.2.1 case. Are you following this thing? So we can say that the effect of surface roughness has drastically diminished. Therefore, F is depending only on Reynolds number. Now you might ask me, when is this going to happen? When is this going to happen? This happens generally in two cases. This happens in two cases in general. What are the two cases? The first case is you are having a relatively smooth pipe. Relatively smooth pipe. If you are having a smooth pipe flow, in that case it is much possible that epsilon's effect is negligible. Second thing, this can also happen if RE is relatively less, relatively low. RE is relatively low. If the value of Reynolds number is less, even in that case, that friction factor can depend only on Reynolds number. Now, please don't think that RE is low means you are going into laminar limits. No. Within turbulent flow, you are having a lower range of RE. Generally, we say that if the value of RE is less than 10 power 5, it is a lower value for turbulent flow. Are you following? So, less than 10 power 5 also is lesser value of Reynolds number in turbulent flow. Now, if you are having f as a function of Reynolds number, the value of f in general, I am giving you a general idea, the value of f in general comes in the form of a into re power minus b. This is the format in general. I don't say this is the only format. I'm not saying this is the only format. I'm saying a general format is something like this. This is the general format of f over here. One such example I can give you is f is equal to 0.316 into re power minus 0.25. This equation is a very famous equation in turbulent flow known as Blasius equation. Blasius equation. This is known as Blasius equation. Now you see it is in the form of A, where A is equal to 0.316 into re power minus B, where B is equal to 0.25. This is a common format of f in the case of f equal to a function of Reynolds number. What to do in this case? In this case, you can say that the value of head loss, which is equal to FLV square upon 2GD, is equal to A into re power minus B multiplied to LV square by 2GD. I hope you are following this thing. So I get over here, this is equal to A into rho VD upon mu whole power minus B multiplied to LV square upon 2GD. Please look at this equation. H is something like that. Now I can say from here, H is proportional to, please observe, velocity power how much? You are seeing over here velocity power 2 minus B times diameter power how much? Diameter power minus of 1 plus B. This is the format I am having. So H is proportional to velocity power 2 minus B into diameter power negative of 1 plus B. You don't have to remember this thing. I'm not asking you to memorize this, please. I'm telling you that if you get such a format, how to approach the question. So from here you can say that the value of H in this particular case is proportional to velocity power 2 minus B, and H is proportional to 1 by diameter power 1 plus b, and this relationship is valid provided velocity is kept constant. I hope you are following this thing. This relationship is valid provided velocity is kept constant. Now, if I convert that in terms of discharge, if I convert this in terms of discharge, please recall velocity is equal to q upon a, or you can say in place of velocity you can say velocity is proportional to q into d power minus 2. Correct? Upon a means a power minus 1, and a power minus 1 is proportional to diameter power minus 2. Is it not? So in place of velocity you can write proportionality as q into d power minus 1. Hold that thought and let us rephrase this thing. Again I am telling you, if this is confusing you, forget about this. You look at the questions, you will be able to solve. I am just telling you how to approach a question. This is not for memorizing purpose. Okay, don't think you have to memorize all these things. See, you can manage lesser memory provided you are having good aptitude. Fine. I always stress having more aptitude and logical skills rather than memory based skills. Let us see over here. I can also write this as head loss proportional to. अब देखिए, in place of velocity I am writing q into diameter power minus 2 whole power this thing multiplied to diameter power minus of 1 plus b. So I can say head loss is proportional to q power 2 minus b multiplied to. Now look over here. This is going to be d power minus 4 plus 2b into d power minus 1 minus b. You know how to do all these things, right? These are basics of exponents and radicals. So you can say head loss over here is proportional to discharge power 2 minus b times diameter power. Minus 4 and minus 1 will make it minus 5. Plus 2b minus b will make it plus b. This is the value I am having. So from here I can conclude that over here head loss is proportional to q power 2 minus b, and head loss is proportional to 1 by d power 5 minus b, and this proportionality of head loss with diameter is going to be valid provided discharge is going to be constant. I hope you are following. I am just saying that. 1 minute. Saying that if you are finding f in the form of a into re power minus b, then you can conclude that head loss is proportional to velocity power 2 minus b, and head loss is proportional to 1 by d power 1 plus b, and this proportionality is valid when velocity is constant. Likewise, you can say head loss is going to be proportional to q power 2 minus b and 1 by d power 5 minus b provided discharge is kept constant. This is the first case under turbulent flow. And what was this case? Please recall, this case was when f is a function purely of Reynolds number. That is going to happen under two conditions. What are those two conditions? One thing is you are having a relatively smooth pipe. Second thing, you are having the Reynolds number relatively low but within the turbulence range. Fine. Let us do one thing. Let us go to the next concept now. That is 5.2.2. 5.2 was turbulent flow. Under turbulent flow we have seen 5.2.1. We are seeing 5.2.2. and this is saying that F over here is going to be, or you can say F is given as a numerical value. F is given as a numerical value. You will see many of these kind of questions. Okay, you'll see questions wherein he'll say use the value of F. Generally they'll say use it as 0.02 or 0.025, something like this. They'll give you some numbers directly. I'm just giving you examples over here. Generally the range is from 0.02 to 0.03. You can have lesser and more also, no problem at all. Fine. When will you be given in examination? When will you be given F as a numerical value? You'll be given under two conditions. When will this happen? Under two conditions. Condition number one. Condition number one is you are having a rough pipe. If you are given a rough pipe in a question, you might be given the value of F as a numerical value straight away. Second thing, you are having a very high Reynolds number, high value of RE, high value of RE. Then again, you are going to be given the value of F as a numerical value. If you are getting any doubts, look at any question. You will be finding many questions where F is directly given to you. Chaliye, what to do in this particular case? In this particular case, you are going to treat F as a constant as you are treating any numerical value. So let us recall our formula for head loss was FL square upon 2GD or equal to 1 by 12.1 FLQ square upon D power 5. You see, the way this 2G is a constant, similar to that even F is a constant. If you treat F as a constant, then what will happen? This is a very simple case now, probably the simplest of all cases. In this case, you can say head loss is proportional to velocity square, or head loss is proportional to 1 by D power 1, and this is valid, this proportionality is valid only if velocity is constant. Likewise, you can say head loss is proportional to discharge square, and head loss is proportional to 1 by D power 5, and this is valid provided Q is going to be constant. This is how you are going to have the relationship if you are given the value of F as numerical, or the question is suggesting any of these two things, then straight away use this thing. This is more important. Especially in IAS examination, I have seen many questions coming on this particular case. So this is regarding the idea of major losses. Let us quickly summarize now. Okay, we have mentioned 5 points over here. First point we have mentioned the cause of your head loss. The cause of head loss, there are either you can say fluid friction or shear stress. We have seen the formula also. It was given by Darcy-Weisbach equation. Then we have mentioned that the cause behind fluid friction is, in the case of laminar flow, only Reynolds number. In the case of turbulent flow, along with Reynolds number, you are having surface roughness involved. Then we have seen how is the major head loss varying with respect to the length of a particular pipe. It is a linear variation and a linear growth increment is there. Lastly, we have seen how is the major head loss varying with respect to velocity, discharge and diameter in all the cases we have seen till here. Till here we have seen the concept of major losses, and this was major loss through in a flow through pipe. Now let us see, under major losses only we are taking one more case which is known as flow through duct. Flow through duct. Now first of all, let us define this duct over here. How do we define this duct? Now you see, pipe was having a circular cross section. If you have a conduit which is having a non-circular cross section, for example, a rectangular cross section or a triangular cross section, something like this, then that conduit is known as a duct. So I can define a duct as a conduit having a non-circular cross section, non-circular cross section is known as duct. A conduit having a non-circular cross section is known as duct. Example of a duct. Best example are AC ducts, air conditioning ducts. You might have seen in big malls, especially near the underground cellars and all, you'll be finding some AC ducts. These AC ducts are mostly going to have rectangular cross section. These have rectangular cross section. Moving further, in the case of ducts, we have to define something known as characteristic length of flow. What is a characteristic length of flow in the case of duct? So let me write over here, characteristic length of flow in ducts. The characteristic length of flow in ducts is given by something known as hydraulic diameter. It is given by hydraulic diameter. We generally represent this hydraulic diameter with a capital D and a subscript H. D subscript H. What is the formula for this hydraulic diameter? The formula for hydraulic diameter is given by 4 times cross section area upon perimeter. This is the formula for the characteristic length in the case of flow through a duct. Let us apply in certain cases to get a better feel of this hydraulic diameter. Suppose the cross section is rectangular. Let us take A bit. You are having a rectangular cross section. Imagine a rectangular cross section, something like this. Let us say the cross section is having length as L and width as B, let us say. Width as B. So what would be the value of hydraulic diameter over here? Let us first of all calculate the value of area. The area over here has to be equal to L times B. And what about the perimeter? The perimeter over here is 2 times L plus B. 2 times L plus B. Now if I put in this value of A and B in the formula of hydraulic diameter, the value of hydraulic diameter comes out to be equal to 4 times L into B upon 2 times L plus B. So over here, in the case of a rectangular cross section, the value of D hydraulic would come out to be equal to how much? It would be equal to 2 times LB upon L plus B. 2 times LB upon L plus B. Now I don't want you to remember this as a formula. You can get this anytime you want. I just want you to understand how to find out the value of hydraulic diameter. Let us take one more case. And this case is an interesting one. Let us say B-bit. You are having a circular cross section. Circular cross section. Now what happens in the case of circular cross section? In the case of circular cross section, let us say there is a circle of diameter capital D, a circle of diameter capital D. We know that the characteristic length has to be diameter itself. Let us check whether hydraulic diameter is giving us the same value. So let me first find out the value of area. The cross section area over here is pi by 4 times d square. Cross section area is pi by 4 times d square. And the perimeter over here is equal to pi times d. Perimeter is pi times d. Now if I apply in the formula, the value of d hydraulic has to be equal to 4 times cross section area upon wetted perimeter. Then it becomes equal to 4 times pi by 4, 4 times pi by 4 times d square whole divided by pi times d. Now please check this thing. 4 and 4 cancel, pi and pi cancel, 1d cancels off with 1d over here. All I am left with is the value of d hydraulic is equal to diameter itself. So the hydraulic diameter in the case of flow through a pipe or a circular cross section is going to be the diameter itself. So please remember, the formula for your hydraulic diameter is 4 times area upon wetted perimeter. Chaliye, let us move further now. Regarding duct, you have to know one more thing. This might not be important from examination point of view, but from information point of view, quite important. When do you use a duct and when do you use a pipe? Remember this thing. Pipes are generally used whenever you are having a working fluid that is a liquid, and ducts are used when the working fluid is a gas. So let me write this as a note. The working fluid through a pipe is mostly a liquid. Whereas the working fluid through a duct is mostly a gas. Remember this thing. Furthermore, after having defined the diameter hydraulic, you can further say that the Reynolds number in the case of flow through duct, has to be equal to. Now you remember the formula for Reynolds number actually is rho into V into characteristic length divided by mu. So what is this formula going to yield in the case of a duct? It is going to give you Reynolds number is equal to rho V d hydraulic upon mu, or you can also say it is going to be equal to V into d hydraulic upon mu. This is the formula of Reynolds number in the case of ducts. RE in ducts. This is a formula of Reynolds number in the case of ducts. With this, we complete the concept of flow through duct, and using whatever formulas are given for friction factor in the question, you can find out the losses in the case of flow through duct as well. Let us now start the concept of minor losses. The word is suggesting that the percentage of this loss is going to be relatively less when compared to major losses. But please understand, it is not always going to be the same way. Sometimes minor losses can become more significant than major losses. But mostly in the case of flow through pipes taking place, these losses mostly contribute towards 5 to 10% of total losses. 5 to 10% of total losses. Again, I am repeating, there are some cases wherein minor losses can become more significant than major losses. Now let us see the meaning of these minor losses. You see, minor losses take place whenever the geometry of flow is going to abruptly change. I can write down over here, losses in flow, losses in flow due to abrupt change in geometry, abrupt change in geometry, abrupt change in geometry of flow, geometry of flow are known as minor losses, are known as minor losses. These are known as minor losses. Now, what are the changes that can take place in a flow? Let us think of some changes. The various changes can be in the form of sudden expansion. You can have something like sudden expansion, or you can have sudden contraction, sudden contraction in a flow, or you can also have bends taking place in a flow, or you can also have something known as fitting in a flow. Sudden expansion would mean, imagine you are having a pipe over here, suddenly you're connecting it to a bigger cross-section pipe. This could be something like sudden expansion. Now imagine a reverse flow taking place. Let us say the flow is taking place from here. Then that could be a case of sudden contraction. Now there is a possibility of a pipe bending. Let us say you are having a bend over here. Now that is the case of bends in a flow. You can sometimes have valve fittings, you can have T fittings, elbow fittings. All these things will come under fitting losses. So all these losses are somehow changing the geometry of the streamlines. And when these changes take place, that is when you are going to have these minor losses. Now let us see the physics behind the minor losses. Why exactly are minor losses taking place, and when exactly will they take place? Let us see the physics behind the minor loss. physics behind minor losses. Now, before I go any further in this topic, let me tell you, if you find this difficult to understand, the end result is sufficient if you remember. Fine. So try to understand this thing. If there is any difficulty, it is not that important. If you remember the end result, that is sufficient for you. Let us see now. Before going any further, recall what is the direction in which a real flow takes place. We have discussed this already in the Bernoulli equation chapter. We have said that a real flow takes place from higher total head to lower total head. So let me write over here one point. Real flow takes place from higher total head to lower total head. Higher total head to lower total head. This is something we have actually established. Total head. We have established this thing already. Now, let us talk about the boundary streamlines. Imagine you are having a particular passage like this. You are having certain passage is like this. We are talking about a real flow taking place, and we are now concentrating on the boundary streamlines. Let us say there is a certain flow taking place over here. I'm choosing over here some boundary streamlines. Suppose I choose these boundary streamlines over here. When I choose these boundary streamlines, there are certain fluid particles closer to the streamlines. We know that these fluid particles which are closer to the boundary, have very, very low kinetic energy. So if I can say over here, the kinetic energy over here is extremely low. Forget about potential energy. Everywhere the potential energy over here is almost the same. So now I can say my total head is equal to pressure head plus kinetic head. Okay, I am neglecting the potential head or the datum head. The reason being, everywhere the datum head is almost same. If the total head is equal to pressure head plus kinetic head, and for the boundary streamlines, the kinetic head or the dynamic head is extremely low, then I can say the total head is almost in the hands of pressure head. So let me write this also as a statement. Let me write this. I can say for boundary streamlines, the total head is almost in the form of pressure head. Now mind you, this is only true for which streamlines? This is only true for boundary streamlines. In the case of boundary streamlines, the total head is almost in the form of pressure head. Not exactly, but you can say approximately 100% of total head is equal to pressure head only. If it is so, now I can say, specially for these boundary streamlines, flow should take place. I know that flow should take place from higher total head to lower total head. Instead, I can say flow should take place from higher pressure head to lower pressure head. So I can say, especially for boundary streamlines, flow should take place take place from higher total head, sorry, higher pressure head, higher pressure head to lower pressure head, to lower pressure head. I hope you are following this thing. Let me again recall. Actually, the flow should take place from higher total head to lower total head. But for the boundary streamlines, total head is as good as pressure head. Therefore, I am saying for the boundary streamlines, flow should take place from higher pressure head to lower pressure head. Now remember this much. After this, let us take certain cases. Let us take certain cases. Imagine you are having a nozzle. Let us say you have a nozzle. Something like this. You have a nozzle. The flow is taking place in this direction. Now, I am concentrating only on the boundary streamlines over here. Let us say I choose boundary streamlines over here. I know that these boundary streamlines are going to have some fluid particles. Let me mark these fluid particles over here. These are the fluid particles which are present at the boundary streamlines. Now please concentrate. Let us take two sections over here. Section 1 is the initial section. Section 2 is the final section. Tell me, as I'm moving forward, what is happening to the cross section area? I can say that as I'm moving forward, the cross section area is decreasing, which is implying that velocity is increasing, which is implying that pressure is decreasing, So along the forward direction, pressure is decreasing. If pressure decreases, and I take this axis as x-axis, I can say the value of pressure gradient dP upon dx over here. Pressure gradient has to be negative. It has to be negative. Why should it be negative? Because as I'm moving forward, the immediate next pressure is lower than the previous pressure. Therefore, dP is over here negative. So dP by dx is negative. Fine. Now tell me, we know that for these particles, flow should take place from high pressure to low pressure. If flow should take place from high pressure to low pressure, I see that the pressure forward is lesser. Therefore, this particle will try to move forward. Likewise, this particle will try to move forward. Every particle is trying to move in the direction of the flow only. I know that flow is in this direction, and the particles are also moving in that particular direction only, in the forward direction only. Therefore, I am not having any problem. So let us mention over here, there are no losses whatsoever. We do not have any losses over here. Whereas, let's take the opposite case. Imagine you are having a diffuser. Imagine you have a diffuser over here. This is a diffuser. Cross section area is increasing. I am having a flow in this direction. Let us say this is my x-axis. I know that as I move forward, area is increasing, which implies velocity is decreasing, which implies by Bernoulli equation pressure is increasing. Therefore, in this particular case, as I move forward, since pressure increases, I can say dP by dx has to be positive. Previously I was having dP by dx negative, now I'm having dP by dx positive. The flow I know should take place in this particular direction. Fine. Let us now concentrate on the boundary streamlines. If I choose the fluid particles over here, imagine these fluid particles. I know that these fluid particles are not affected by this flow. They only have one demand. Their demand is they want to move from high pressure to low pressure because they are boundary particles. Now they are looking for high pressure to low pressure region. They want to move in the direction of low pressure. Tell me which section is having lower pressure, section 1 or section 2? We know that section 1 has lower pressure. Therefore, these particles are not trying to move forward, they are rather trying to move in the backward direction. They are moving in the direction opposite to the flow. I hope you are following this thing. Previously, there was no difference in the direction of flow between these two things. But now there is a difference in direction. These particles are trying to move in the backward direction. When they want to move in the backward direction, they create a reversal in flow over here. They try to create a reversal in flow over here. This reversal in flow is characterized by tiny vortices and circulations. These tiny vortices and circulations are known as eddies. Singular is eddy, singular is EDD, eddy, plural is eddies. And these eddies are responsible for the minor losses. I hope you are following this thing. So these are responsible for the minor losses. I can summarize this as, whenever I am having a negative pressure gradient, I am not going to have any losses. Whenever I have positive pressure gradient, I am going to have minor losses taking place. Why is it so? The reason is there is going to be a difference in the direction of flow between the boundary fluid particles and the main flow. Because of this difference, there is going to be circulations developed near the boundary, and these circulations are going to create tiny vortices or known as eddies. So now we can summarize this. Minor losses in a flow take place if dP upon dx is going to be positive. If you remember this much, it is sufficient for you to apply the formulas. If you remember only this statement, it is sufficient for you to apply the formulas. The reason I have discussed previously, if you are finding any difficulty in understanding that, just remember these things. Now let us see how to develop the formula in the case of sudden expansion. If we know this formula, we can develop the formula for sudden contraction also. Let us say you are having a passage something like this. Some passage like this, let us say. The flow is taking place in the forward direction. Flow takes place in the forward direction. Now the streamlines are going to move something like this. The boundary streamlines are going to move something like this. Let us say this is some section, section 1. This is section 1. And this section, let us say, is section 2. This is section 2. The velocity at section 1, let us say, is equal to V1. The velocity here is equal to V1, and the velocity here is equal to V2. Similarly, the pressure here is equal to P1. The pressure here is equal to P2. And there is some eddy formation taking place over here. Now, why is eddy formation taking place over here? The reason is, as I move forward, the area is increasing. If the area increases, the velocity should decrease and the pressure should increase. That means in this particular case, the value of dP upon dx is positive. Since the value of dP upon dx is positive, therefore I am having the formation of eddies taking place. Furthermore, let me also mention that there is a particular pressure acting over here. The pressure acting near the formation of these eddies, let us say, is certain pressure P prime. So this is how the geometry of flow is looking for us. Now what we are going to do is, for this particular passage, I am going to apply Bernoulli equation, continuity equation and momentum flux equation. Let me start first of all with continuity equation. I know that by continuity equation, I can say that the value of A1 V1 has to be equal to A2 times V2. A1 V1 is equal to A2 times V2. So from here I can say that the value of V1 is equal to, let us say, A2 upon A1 times V2, or you can also write V2 is equal to A1 upon A2 times V1. Let me say these two things. So basically I am writing one velocity in terms of the other velocity. Let us mark this as certain equation number 1. Very simple. Next thing what I am going to do is, I am going to apply over here momentum flux equation. I am going to apply momentum flux equation. What do I have if I apply momentum flux equation? I can say that by momentum flux equation or momentum equation, I can say summation of force in x has to be equal to delta m dot into velocity in x. This is the equation I'm having. Let me do one thing. By momentum flux equation, I can have this thing. Now let us look at what are the various forces acting in x-axis. I see that there are 3 forces acting in x-axis. One is the pressure force here, one is the pressure force here, and the other is the pressure force in this region. Fine. So if I draw the control volume should look something like this. The control volume should look something like this. There is going to be certain pressure force over here that is equal to P1 A1. There is going to be certain pressure force over here which is equal to P2 times A2. Then there is going to be certain pressure force here, the pressure force here. The value of this pressure force is equal to P prime times A2 minus A1. P prime A2 minus A1. Okay, that's the entire region at which P prime is acting, A2 minus A1. And I know that the velocity here is equal to V1 and the velocity here is equal to V2. The velocity here is equal to V2. Now taking this as my control volume, let us write the equation. Look at this control volume, let us write the equation. The equation can be, I am starting first of all with P1. So I am having P1 times A1, P1 times A1 in the positive direction plus P prime times A2 minus A1, A2 minus A1, P prime times A2 minus A1. Next thing, minus P2A2 minus P2A2 has to be equal to delta m dot into velocity, has to be equal to delta m dot into velocity in x. This is the equation I'm having. Now at this stage I'm going to write a statement which is proved experimentally, and that is the value of P prime, the value of P prime is almost equal to the value of P1. P prime is almost equal to the value of P1. If it is so, then I can write over here P1 times A1 plus P1 times A2 minus A1, A2 minus A1 minus P2 times A2 minus P2 times A2 is equal to delta m dot into velocity in x. This is what I'm having. Now you see over here, I'm having P1 A1 positive, I'm having P1 A1 negative. If you observe, I have now P1 A2 minus P2 A2, which is going to give me P1 minus P2 whole times A2, P1 minus P2 into A2. This is equal to, I can take m dot common over here. The value of m dot I can write as density into A2 times V2. M dot is density A1 V1 or density A2 V2. I have preferred this so that I can cancel A2 and A2. Next, the delta velocity is equal to V2 minus V1. This is the value I'm having. From here I can cancel off A2 and A2. I can cancel off A2 and A2. So from here I can say P1 minus P2 whole divided by rho. If I take this rho over here, I am having rho. This has to be equal to V2 square minus V1 V2. V2 square minus V1 V2. Let us do one thing. Let us write rho g over here, rho g, so that it becomes pressure head difference. Then I'll be having this value. Save this as an equation number 2. Save this as equation number 2. Let us say this is equation number 2 we are having. Now what I'm going to do, after having completed momentum flux equation, now I'm going for Bernoulli equation. So let us say I'm writing over here Bernoulli equation by Bernoulli equation. Now you see, in our subject most of the times you are going to apply these 3 equations only: continuity, Bernoulli and momentum flux equation. Now by Bernoulli equation I know that P1 by gamma plus V1 square by 2g plus Z1 has to be equal to P2 by gamma plus V2 square by 2g plus Z2 plus head loss, and this is head loss minor over here. I know that the value of Z1 and Z2 are same, so cancel of Z1 and Z2. So what am I left with over here? I am left with head loss equal to P1 minus P2 by gamma, P1 minus P2 by gamma plus V1 square minus V2 square whole divided by 2g, Now look over here. I have saved the value of P1 minus P2 by gamma. Let me borrow that value over here. If I do so, I am going to get the value of head loss is equal to that was equal to V2 square minus V1 V2 whole divided by G plus V1 square minus V2 square whole divided by 2G. This is the value of head loss. Let us refine this thing now. Let us refine this thing. From here, I can further write this as, let us take 2G as a common denominator. So I am having 2V2 square minus 2V1V2, 2V1V2, 2V2 square minus 2V1V2 plus V1 square minus V2 square whole divided by 2G, whole divided by 2G. Now observe this thing. I am having 2V2 square and I am having minus V2 square. I can cancel this off. I can cancel this off. So now the value of head loss becomes equal to V1 square minus 2V1 V2 plus V2 square whole divided by 2G. Now this is in the form of A square minus 2AB plus B square, which I can say is also equal to A minus B whole square divided by 2G. Therefore, the value of head loss in the case of sudden expansion is equal to V1 minus V2 whole square divided by 2G. This is the value of head loss in sudden expansion. Head loss in sudden expansion. Sudden expansion. Now at this stage you might be wondering, why have I taken a sudden expansion case? You see, when there is a gradual expansion, then also might be having head loss, but that is going to be insignificant. You see, significance will occur when there is a sudden change in geometry of flow. That is why we are choosing sudden changes like sudden expansion, sudden contraction, bends, fittings, all these kind of things. After having seen this, we will look at the various formulas of head losses. Let us now look at the various formulas of head losses, minor head losses. This is important for you. So, minor losses, all the formulas we are going to look over here. All the loss. I am going to start with the first one, which you have seen recently, that is sudden expansion. Sudden expansion. Sudden expansion. Let us again draw the diagram once. Imagine you are having a cross section which is changing to something like this. The streamlines of flow are developing like this. This, let us say, is section 1. This, let us say, is section 2. Let us say the flow takes place in this particular direction. The flow takes place in this particular direction. The velocity here is equal to V1. The velocity here is equal to V2. We have already established you are going to have formation of eddies over here. There is going to be formation of eddies over here. The formula is pretty simple. Whenever you see eddies, I try to remember the formula like this. Whenever you see eddies, the formula of head loss is going to be velocity before eddy, that is V1. Velocity before eddy is V1 minus velocity after eddy, minus velocity after eddy is equal to V2 whole square by 2G. Whole square by 2G. This is how I like to remember the formula. Velocity before a d minus velocity after a d whole square by 2g. So this is the formula for sudden expansion. Now I am going to take a special case under sudden expansion. That is, when you are having a pipe connected to a reservoir and the pipe is discharging the fluid into the reservoir. So let us say under expansion only I am having a special case. Imagine there is a pipe connected to a huge reservoir. Huge reservoir, let us say something like this. Huge reservoir. This is a reservoir and fluid is discharged from the pipe to the reservoir. This is called as exit losses. This is known as exit losses. It is known as exit losses. Now why is it called as exit losses? I have heard from some students, the doubts were, is it not the entry into reservoir? If it is an entry into reservoir, why are you calling it as exit loss? You see, we are always looking from the perspective of a pipe. Tell me, from the perspective of a pipe, is it the exit of a pipe or entry of a pipe? Of course, it is the exit of a pipe. That is why we are going to call this as exit loss. Let us say over here the velocity is equal to v. This is an expansion such that the value of v2 is becoming equal to 0. We know in the reservoir the velocity is negligible. It is equal to 0 for us. So now if I apply the same logic what I had in expansion, recall the formula, head loss was equal to v1 minus v2 whole square by 2g, whole square by 2g. Then what do you have over here? The value of v2 is equal to 0. Therefore, the value of head loss has to be equal to v square upon 2g. This is the formula of head loss in the case of exit of a pipe into a reservoir. Now sometimes what happens is they will give you that the coefficient of loss is k. They will give you that the coefficient of loss is k. Now why would they give you coefficient of loss? Remember this thing. Sometimes what happens is, sometimes what happens is the exit might not be sharp, it might be something like this, a smoother exit. If you are having a smoother exit, it is possible for the losses to be lesser. Likewise, sometimes you can have a portion of pipe entering into the reservoir also. This thing can also happen. Therefore, you can have a different value of head loss. So in these cases what happens is the question will give you coefficient of loss. Remember, this coefficient of loss is represented by k. K is known as coefficient of loss. K is known as coefficient of loss. If the value of coefficient of loss is given, forget this formula. Forget this formula. In such a case, the value of head loss is going to become k times v square upon 2g. K times v square by 2g. If coefficient of loss is not given, you can choose that formula. If coefficient of loss is given, forget that formula and choose this formula. This is regarding the losses in expansion. Now let us take the next case, which is sudden contraction case. Sudden contraction. Let us take the case of sudden contraction. Now in the case of sudden contraction, you are going to have a higher diameter pipe contracting to a smaller diameter pipe. Let us see. something like this. Let us say something like this. Now, if you observe the streamlines of flow, the streamlines of flow are going to contract before they experience this throat. They keep on contracting. The moment of contraction drags the contraction further to something which is very famously known as vena contracta. Beyond vena contracta, you are going to have expansion again. You are going to have expansion. This is how the pattern of streamlines is going to be developed. Let us now choose this section over here, as section 1. I am choosing this section as section 1. I am choosing this section over here as section contracta, C. I am choosing this section over here as section 2. 3 sections I have chosen over here. Each section is having a velocity. Let us say the velocity over here is equal to V1, the velocity here is Vc, and the velocity here is equal to V2. So these are the velocities we are having at the corresponding sections. Now the question is, where are the eddies developed? In these kind of problems, some people mistake. Some people tend to show eddies wherever they see empties. That is wrong. Again, I am repeating. You are not supposed to show eddies here, 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 everywhere. That would be wrong. Okay. Never show eddies wherever you see empty spaces. You are going to show eddies only when you find positive pressure gradient. So let us check where the pressure gradient is going to be positive. Let us see. From section 1 to section C, in this much of span, tell me what is happening to the area. The area of the flow decreasing, velocity increasing, pressure decreasing. That means in this region, the value of dP upon dx is going to be negative. Pressure is decreasing over here. If pressure is decreasing, this is a favorable pressure gradient we are having. Fine. Now look at this region from section C to section 2. What kind of pressure gradient are you having over here? You see the area is increasing. If area increases, velocity decreases, pressure increases. This is the range of adverse pressure gradient. In other words, dP by dx over here is positive. If dP by dx is positive, I am supposed to show a deformation only over here. It is only over here that I am going to show eddy formations. Once I have shown the eddy formations, now it is time for me to write down the formula of head loss. I hope you are following. We are not having eddies over here. Now you see, this is a case of expansion again. If you observe over here, this is again a case of expansion. Expansion from this cross section to this cross section. And I know the logic over here has to be head loss is equal to velocity before eddy, that is Vc, minus velocity after eddy, that is equal to V2 whole square by 2g. This should be the formula of head loss. Velocity before eddy minus velocity after eddy whole square by 2g. Now what I'm going to do, let me refine this formula. So I can say head loss is equal to, let me take V2 square common. If I take V2 square common, V2 square by 2g common to Vc upon V2 minus 1 whole square. Fine, this is the thing I'm having. Recall, there is something known as coefficient of contraction. We have discussed this previously also. Something known as coefficient of contraction. The value of coefficient of contraction is area at vena contracta upon area at section 2, or by continuity equation you can say inverse with velocities, that is V2 upon Vc. This is your coefficient of contraction. Now observe over here, this is Vc upon V2. Is it not inverse of coefficient of contraction? Yes, it is. Therefore, I can as well write this head loss as, I am writing this head loss as, head loss in sudden contraction is equal to, it is equal to V2 square by 2g multiplied to 1 by cc minus 1 whole squared. This is the formula for head loss in sudden contraction. This is a formula for head loss in sudden contraction. After having understood this, let us move forward to a special case in contraction. That special case, is something like this. Imagine there is a reservoir. To this reservoir you are having a pipe connected. Let us say this is the reservoir. The flow is taking place in this direction and the velocity in the pipe is equal to V. Is it not a case of contraction? Yes, it is. From infinite area I am going to a finite area now. Fine, it's a case of sudden contraction again. Okay, what do we call this kind of loss as? Tell me, entry loss or exit loss? We are looking from the perspective of pipe. From the perspective of a pipe, this is entry in the pipe. That is why we are going to call this as entry loss. We are going to call this as entry loss. And what should the formula over here be? The value of head loss has to be equal to V2 square. That is, in this case, V square by 2g multiplied to 1 by cc minus 1 whole squared. This is a formula. Now, let me tell you, this is a very special case. In this particular case, the value of 1 by cc minus 1 the whole squared is approximately equal to, or it is tending towards, this value is tending towards 0.5. This value is tending towards 0.5. If it is tending towards 0.5, I can say entry losses are equal to 0.5 times V square by 2g. 0.5 times V square by 2g. This is the value of entry loss. Again, let me recall over here, there are chances of changing the formula provided coefficient of loss is given. Very simple thing. If coefficient of loss is given, and when will it be given? You know this thing. It will be given whenever the entry is not going to be exactly like this. Imagine you are having some part of the pipe entering into the reservoir. This time you will be having a different value of losses. You check these things. If you go to the overhead tank in your building, you'll be finding some cases like this. Okay, the losses are now going to change. Similarly, if you are having a very smooth corner, if you have a smoother corner, again the value of losses will decrease. Fine. So these kind of things can happen. Whenever this happens, the value of head loss now becomes k into V square by 2g, where k is your coefficient of loss. So till here we have seen two types of losses. One is sudden expansion, one is sudden contraction. Now let us look at the last case, the simplest of all cases. The last case is losses in bends and fittings. Losses in bends and fittings. Losses in bends and fittings. I have told you previously also, the type of bends you can have are elbow bends. You can have something like a smoother bend and all those things. Similarly, you can have valve fittings, half open valve, full open or full open valve. All these kind of things can be there. Over here, there is only one formula. The value of head loss over here is equal to K into V square by 2G. Again, this K over here is coefficient of loss. Over here is coefficient of loss. This is regarding the concept of minor losses. So all you have to remember is, if you are having minus dp by dx to be negative, that is when you are going to have a d's. Whenever you see a d's, the logic is velocity before a d minus velocity after a d whole square by 2g. Fine. If the coefficient of loss is given, your formula becomes all the more easy. You are going to say coefficient of loss multiplied to v square by 2. Let us start the concept of connections in pipes. One of the most important topics in entire fluid mechanics is connections in pipes. Now imagine you are having two reservoirs. Let us say one reservoir over here, one reservoir over here. If you want to connect a pipe from this reservoir to the other reservoir, it is not always possible to have a single pipe. For various reasons, you would have to take multiple pipes into picture. Now these multiple pipes can be connected in two ways. So there are two ways of connection. One way of connection is known as series connection. It is known as series connection. The second way of connection is known as parallel connection. Parallel connection. So there are going to be two connections we are going to discuss now. One is known as series connection, the other is parallel connection. We'll see these things in detail. But before we start the analysis of these connections, we have to take into picture the assumptions required. So let us talk now about the assumptions required in the case of connections in pipes. Assumptions required in the case of connections in pipes. First assumption. Now you see, these pipes are going to be quite lengthy. Since the pipes are lengthy, the major head loss, which is proportional to length, becomes more significant than the minor losses. So the first assumption we are having over here is we are neglecting the minor losses. But if the question says consider the minor losses, then you have to consider. So let me write the assumption something like this. Minor losses are neglected unless the question or the problem specifies them to be considered. So if the problem is mentioning that consider the minor losses, then you are going to consider. If it is not mentioning anything about the minor losses, straight away neglect the minor losses. This is the first assumption required. The second assumption required. Now tell me, what kind of flow would you expect is taking place through these pipes? Now these are going to have mostly water flowing through them. With water, most of the time you are going to have turbulent flow taking place. So the assumption over here is we are going to expect the flow to be turbulent in nature. So flow is assumed to be turbulent. Now let me again tell you, if the question is specifying otherwise, you have to neglect the assumptions. So these two assumptions are generally chosen. Fine. Next thing, let us define something known as equivalent pipe. So after completing the assumptions and before starting the analysis, let us now talk about equivalent pipe. How to understand this equivalent pipe? Imagine you are having n pipes in connection, series, parallel, all of them are there. Let us say you are having pipe P1, then you are having pipe P2, then you are having parallel connections, then you are having another connection over here. Likewise, you might be having n number of pipes in connection. Let us say you are removing all these pipes and replacing by a single pipe, and you are replacing by a single pipe such that whatever was the head loss created over here is equal to the head loss created in the equivalent pipe. Whatever was the net discharge in particular case is equal to the discharge in this particular pipe. Then we are going to call this pipe as equivalent pipe. So how can I define this equivalent pipe? I can say an equivalent pipe is a single pipe which can replace a system of pipes in connection such that it creates the same head loss and same discharge what was created in the system of pipes. I hope you are following this thing. So let me write the statement now. I can write the statement as a single pipe, one moment please, a single pipe which can replace a system of pipes such that it creates the same discharge. It creates the same discharge and head loss. That is, it is creating the same discharge and head loss as compared to which pipes? The system of pipes. So this is known as equivalent pipe. This is the definition of equivalent pipe. This is a very, very important point. We are going to use this for some questions. So this is regarding the basics of connections in pipes. You have to remember over here few things. First of all, two types of connections, series and parallel. Two assumptions, minor loss is neglected and the flow is turbulent. And you have to understand there is something like a resultant pipe you are having which is called as equivalent pipe. You remove all the pipes in system and just replace it with a single pipe which is carrying the same discharge and having the same head loss. That is called as your equivalent pipe. Now let us start the analysis of first case. That is series connection. So let us see analysis of pipes in series. Pipes in series. Analysis of pipes in series. Now let us imagine that you are having a reservoir over here. You have a certain reservoir over here. To this reservoir you are connecting a pipe, let us say P1. You are having another pipe, let us say P2. You have one more pipe, P3. Likewise you are having, let us say, n number of pipes which are connected in series. Then you have one more reservoir over here, let us say something like this. You have another reservoir over here. Let us say the fluid is present over here. The fluid is present over here. Fine. Now first of all, for the flow to take place, the total head in these two reservoirs has to be different. Only then you are going to have head loss created. Only then will the flow take place. By total head in the case of reservoirs, we only mean the datum head. The reason is pressure we know at the top is equal to 0. The velocity also is equal to 0. So whichever fluid level is having higher elevation, from there the flow will take place to the lower elevation. So in this particular case, the flow is taking place in this direction. Let us say this is the first pipe you are having. This is the second pipe you are having. Likewise, you are having n number of pipes. You are having n number of pipes. Now each of these pipes are going to have their own specifications. So let me mention over here, each pipe has a set of specifications. Each pipe is going to have a set of specifications. What are the specifications each pipe is going to have? First set of specification are geometric specification. For example, every pipe will have its own length. It will have its own diameter. If surface roughness is important, it would have its own surface roughness, epsilon. Friction factor, every pipe would have its own friction factor. Likewise, it would have its own velocity, its own discharge. The flow through each pipe is going to have its own velocity, own discharge. Furthermore, you can also say there is going to be a certain drop in pressure in each pipe. There is going to be a certain head loss in each pipe. So all these specifications are going to be there for every pipe over here. Our aim is to identify the relationship of these specifications and the specifications of equivalent pipe. So important thing over here is to identify the condition of equivalent pipe. Let us see how we are going to move about this. You see, there are only two things important over here. One is continuity equation, the other is energy balancing. Let us start first of all with continuity equation. So I can say over here, by continuity equation, I can say over here, by continuity equation, imagine that over here I am having certain discharge Q1, over here certain discharge Q2. I can say both these discharges are going to be same. Likewise, if I have a discharge over here Qn, I can say even that discharge is going to be same. So basically discharge through every pipe is going to remain identical. So by continuity equation I can say that the value of Q1 is equal to the value of Q2. Likewise, it is going to be equal to the value of Qn. Furthermore, if I replace all these pipes by a single pipe, that is equivalent pipe, even that pipe should carry the same discharge. Therefore, I can say that it should also be equal to Q equivalent. Q equivalent. So this is the first relationship I'm having. Let me save this as equation number 1. If you want to remember this in the form of a statement, I can say discharges are identical. Discharges are identical. Fine. Next, I am going to apply the condition of what we call energy balancing. For that purpose, let me do one thing. Let me first of all choose this thing. After having identified the condition of discharge, let us now talk about energy balance. Imagine that when the flow is taking place in the forward direction, I choose a particular point over here. I choose a particular point here and a point here. The difference in pressure between these 2 points is going to give me delta P in first pipe. Likewise, if I choose this point and this point, I can say the difference in pressure over here is delta P in the second pipe. If I choose the difference in pressure between these 2 points, that is going to give me delta P in nth pipe. If I want to see the equivalent drop in pressure, then it is going to be the difference in pressure between these 2 points. So now keep this in mind and let us write by energy balance, or you can also say pressure balance over here, because we are talking about pressure energy over here. By energy balance, I can say the value of delta P in equivalent pipe, the value of delta P in equivalent pipe has to be equal to delta P in first pipe plus delta P in second pipe plus delta P in third. Likewise, you can say till delta P in nth pipe, till delta P in nth pipe. From here I can say now that if I divide this entire equation by gamma, if I divide this entire equation by gamma, so what do we have? If we divide this by gamma, we know delta P by gamma is going to give me head loss. If it is giving me head loss, I can say from here the value of head loss in the equivalent pipe has to be equal to head loss in the first pipe plus head loss in the second pipe, likewise till head loss in the nth pipe. So this is the equation I am getting for the relationship of head loss. This is the relationship of head loss. I can also say head loss equivalent is equal to summation of head loss in ith pipe, where I is ranging from 1 to n. I is ranging from 1 to n. Both these equations are identical. Both these equations are identical. So from here I can summarize this as, in the case of series connection, head loss is cumulative in nature. Head loss is cumulative. By cumulative we mean it has to get added up, We saw one statement previously which said that discharge is identical. One more statement you are seeing over here, head loss is cumulative in nature. Now let us do one more thing. Let us recall that the formula of head loss can be written as, let me write this, head loss can be mentioned as 1 by 12.1 FLQ square upon d power 5. 1 by 12.1 FLQ square upon d power 5. This is a standard formula for head loss. And I told you previously also, we are in general neglecting the minor losses. Therefore, only major loss over here. Imagine I write this formula for every term over here. If I write this formula for every term, first of all 1 by 12.1 will get cancelled off. Furthermore, even Q will get cancelled off. Why? Let me write over here. Since 1 by 12.1, or let us say rather, one second, Q square by 12.1 is identical for every pipe, since Q square upon 12.1. So this part and this part is going to remain same in every term over here. Beforehand only let us cancel them off. If we cancel them off, the equation now becomes F into L upon d power 5. F into, one moment please, F into L upon d power 5 for equivalent pipe has to be equal to F into L upon d power 5 for first pipe plus F into L upon d power 5 for second pipe, so on and so forth till F into L upon d power 5 for nth pipe. This is an equation we are having. I can highlight this equation first of all. This is true in the case of series connection. This equation is true in the case of series connection. Or I can also rewrite this as, if you are comfortable with mathematical notation, simple mathematical notation, you can write this also as FL upon d power 5 for equivalent pipe has to be equal to summation of FL upon d power 5 for ith pipe, where I is ranging from first pipe till nth pipe. You can also write like this. So this is a standard thing which you are supposed to remember in the case of series connection. Okay. Now what we are going to do, we are going to write this equation again, but after making a certain assumption. So we are making an assumption over here. Let us see, this is an equation I am having. Let me write, if the friction factor in every pipe is identical, in every pipe is same or identical, then what happens? Then the value of F equivalent is equal to F1 is equal to F2, so on till equal to Fn. If the friction factor is going to be identical. Now see, if friction factor is identical, I can cancel off F everywhere over here. Okay. If that is happening, now the equation becomes all the more simple. The equation would look something like this, as L upon, one moment please, L upon d power 5 for equivalent pipe has to be equal to L upon d power 5 for first pipe plus L upon d power 5 for second pipe, so on and so forth, till L upon d power 5 for nth pipe. This would be the equation. Mind you, you can't use this equation every time. You can use this equation only if the value of friction factor everywhere is identical. I can also rewrite this equation as, in notation form, L upon d power 5 for equivalent pipe has to be equal to L upon d power 5 for ith pipe. Sorry, one moment please. Summation of L upon d power 5 for ith pipe, where I is ranging from 1 to n. This is in the notation form. The notation form. Again, I'm telling you can use this thing provided you have this relationship valid. And this equation has a name. It is known as Dupit's equation. It is known as Dupit's equation. This is regarding the case of analysis of series connection. So two things you have to remember. First, discharge identical. Second, head loss cumulative. And if you apply the formula of head loss, you are going to get this equation. You are going to get this relationship over here. If you don't even remember these things, again I'm telling you, don't stress much on memorizing stuff. If you understand some things and remember some basic things, you can easily develop these equations. So let us say if you apply the formula of head loss, you are going to get this relationship, and in that relationship, if you even find an assumption that the friction factor is identical everywhere, then you are going to get Dupit's equation valid. This completes the concept of analysis of series connection. Let us now start the analysis of parallel connection. Let me write over here. Analysis of parallel connection. Parallel connections. Now, first of all, understand one thing which is very commonly asked in interviews also. What is the purpose of using parallel connection? Parallel connection is primarily used if you want to increase the discharge. Okay, you'll be seeing in some questions in our exercise also, whenever we have a parallel pipe added, the discharge is going to get increased. Now let us take a case. Imagine you have a reservoir. You have a reservoir. You have another reservoir over here. You have another reservoir, two reservoirs. Let us say the level of fluid is still here. The level of fluid is lower over here. Fine. I am connecting these two reservoirs by a set of parallel pipes. Imagine something like this. Imagine you're having some parallel pipes like this. Fine. Let us see. This is the first pipe. This is the second pipe. Likewise, you're having n number of pipes in parallel. The fluid is branching off over here. and the fluid is converging over here. The fluid is converging over here. I have shown 3 pipes. Imagine some n number of pipes over here. Now the connection of these pipes is parallel connection, and again each pipe is going to have a set of specifications. I have told you already, the specifications can be length, diameter, surface roughness, friction factor, velocity, discharge, drop in pressure, head loss. Likewise, a number of specifications are possible. Our goal again is to establish the same thing. Our goal is to find out a relationship between equivalent pipe and the system of pipes over here. Fine. Again, I'm going to use the same process. First, start with a continuity equation. Let us say I'm starting over here with continuity equation. So let me start by continuity equation. Now tell me, if discharge Q is moving over here, it is getting divided into Q1, Q2, Q3 till Qn, is it not? That means if I look for the value of this discharge Q, it has to be equal to Q1 plus Q2, likewise till Qn. That means the value of equivalent discharge, the net discharge is equivalent discharge only. The value of equivalent discharge has to be the sum of each of the individual discharges. So I got this relationship over here. The value of equivalent discharge has to be equal to sum of the individual discharges. If you want, you can write this in notation form as Q equivalent has to be equal to summation of Qi. Where I is ranging from 1 to n. Both these things are same. If you want to write a statement over here, you can say discharge is cumulative. Recall, in the case of series connection, discharge was what? Cumulative or identical? It was identical. Over here it is cumulative. Next thing, please observe over here. One moment please. If you observe, for the pipe P1, initial pressure is present over here. The final pressure is present over here. For the pipe P2, again initial pressure is present here, final pressure is present over here. For the pipe Pn, again initial pressure is present over here, final is over here. So I see that every pipe is having same initial pressure, same final pressure. If it is so, tell me by, one moment please, by energy balance, tell me, if initial pressure is identical for every pipe and final pressure is going to be identical for every pipe, what can you say regarding the value of delta P in each of the pipes? Let us say delta P1, delta P2, delta P3. Likewise, if you look for delta Pn, what can you say regarding all these drop-in pressures? They are supposed to be identical. So I can say from here, the drop-in pressure in every pipe is going to be identical. And that should also be equal to delta P in the equivalent pipe. Let us say at this stage, I divide this entire thing by gamma. I'm dividing this entire thing by gamma. If I divide this drop in pressure by gamma, what am I going to get? I am going to get head loss equivalent is equal to head loss 1 equal to head loss 2, so on and so forth till equal to head loss n. So I have a relationship established over here, and this relationship says that the value of head loss in every pipe is going to be identical. So let me write a statement. Head loss in every pipe is identical. Head loss in every pipe is identical. Are you following this thing? So this is regarding the concept of this is regarding the concept of connections in the case of parallel pipes. Now let us take a very interesting concept known as grade lines. The concept of grade lines is particularly important from interview point of view, and you can have very good questions also coming in examination from here. Now let us see what grade lines are. In kinematics, we have discussed some lines like streamlines, path lines, streak lines, timelines and all, which help you visualize how the flow is taking place or the kinematics of the flow. Now this topic of grade lines, basically it is helping you visualize how the energy heads are going to vary along a particular flow. We are going to have two grade lines. The first type of grade line is known as energy grade line. It is known as energy grade line. Energy grade line, or it is also called as total energy line. Total energy line. Now, how do we define this energy grade line or total energy line? This is defined as the locus of total head throughout a particular flow. So I can call it as the locus total head, total throughout a flow, throughout a flow, throughout a flow is known as energy grade line or total energy line. You can also call it as a line representing the total head throughout a particular flow. This is going to be your energy grade line or total energy line. The second type of line we are having is known as hydraulic grade line. Second one is known as hydraulic grade line. Hydraulic grade line. Hydraulic grade line. Now, how do we define this hydraulic grade line? Now, this was talking about the total head. This particular line is going to talk only about the piezometric head. So you can say the locus of piezometric head, piezometric head throughout a flow, throughout a flow is known as hydraulic grade line. So we are having two lines. One is talking about total head, the other is talking about piezometric head throughout a particular flow. Now let us draw a simple case of grade lines and then decide the properties of grade lines. Let us start now. Imagine you are having a passage, let us say something like this. A passage, something like this, through which a flow is taking place. One moment, please. Let us say you have some passage like this, through which a flow is taking place. Let us say the flow over here is ideal flow. You have an ideal flow taking place over here. Now what I'm going to do is, I'm going to choose a reference datum. Suppose the reference datum is somewhere over here, a horizontal line. This, let us say, is reference datum z is equal to 0. Fine. And furthermore, let me choose over here a center line, something like this. This is a center line, let us say. Now I want to draw both hydraulic grade line and energy grade line. Let me start first of all with energy grade line, EGL. For EGL, I have to look at total head. So EGL is talking over here about P by gamma plus V square by 2G plus Z. EGL is talking about this entire thing. So let us say I choose this line for my EGL. I know that this distance over here, is representing datum head. So let me write here, this is my datum head Z. Now at this particular position, let us say I have pressure head up till here. Let us say this, let me go even further. Let us say till here, what I'm having is pressure head. So let me write over here, this is P by gamma. On top of this, let us say I'm having velocity head. Let us say velocity head is up till here. Till here I'm having is velocity head. So let me write over here V square by 2G. Fine. Let me take another point. This is, let us say, certain point A. I'm choosing another point over here. Let us say this point is point B. I know that the datum head is going to become something like this. This, let us say, is a datum head I'm having. So suppose this is Z over here. On top of this, I'm going to have pressure head. I know logically that as I go forward over here, since the area is decreasing, velocity is increasing, pressure is decreasing. So let us say the pressure head is going to be till here only. This, let us say, is my pressure head. So let me mention over here P by gamma. And finally, now I'm representing my velocity head. Let us say the velocity head is up till here. The velocity head is up till here. So let me say this is representing V square by 2G. I hope this diagram is clear to all of you. Fine. Now, if I show energy grade line, it is supposed to show the total head throughout the flow. Let us say at every point, if I keep looking at total head, since the flow is ideal, the total head everywhere is going to remain same. Therefore, my energy grade line is going to be a horizontal line. I'm going to have a straight horizontal line representing my energy. Therefore, this is EGL, or you can say it is TEL. TEL means total energy line over here. Next, let us look for piezometric head or hydraulic grade line. Hydraulic grade line. Now, this hydraulic grade line talks about P by gamma plus Z or piezometric head. So, if I look for piezometric head, I can say that the locus of piezometric head is something like this. It is something like this. So, this is representing my HGL. This is representing HGL. Now, at any particular point, if I look for the difference between HGL and EGL, at any point, if I look for the difference between HGL and EGL, what is it going to show? What is this distance going to show me? It is going to show me the velocity head at that particular point. So I can say the first point over here, the difference between HGL and EGL is going to be the velocity head. I hope the diagram is clear to all of you. Let us now write down some points. Let us now mention some points. The first point over here is the difference between EGL and HGL is velocity head V square by 2g. It is going to be velocity head, that is equal to v square by 2g. This is the first point we are having. Next thing, tell me, is it possible for HGL to move above EGL? If HGL is moving above EGL, it basically means I'm having a negative velocity head. Is it possible for the velocity head to be negative? Can v square by 2g become negative? It is impossible. So I can say that second point over here is, HGL is always below EGL, except when velocity is zero. When velocity is zero. Now what happens when velocity is zero? When velocity is zero, imagine at zero velocity conditions, total head and piezometric head, both of them are going to be same. You see, v square by 2g is 0. That means p by gamma plus v square by 2g plus z is as good as p by gamma plus z. So I can say in this particular condition, HGL and EGL overlap. HGL and EGL overlap. So this is the second point I'm having. So remember this thing, HGL is always below EGL except in one particular condition, when velocity is zero. When velocity is zero, what happens in that condition? HGL and EGL are going to overlap. Now please tell me, when is this going to be possible? Can you give me an example of where the velocity is zero? Where the velocity is zero? The best example of velocity being equal to zero is the case of a reservoir. In the case of a reservoir, the value of HGL and EGL, or the line representing HGL and EGL, both of them are going to be same. This is the second point we are having. Third point, let us say. Third point, tell me, is it possible for HGL to rise up and down? Is it possible for HGL to move up and move down? Yes, it is possible. But what about EGL? EGL can keep moving down because of head loss. But can EGL move up? For EGL to move up, the total head is supposed to increase. Now that is only possible when you are giving some energy from outside. For example, you are using a pump. So let me write over here, third point. HGL can move up or down, That means the value of piezometric head can increase or decrease. Is it possible? It is possible. Now, EGL declines or it moves down under two conditions. One condition is you are having losses. Other condition, when you are extracting of the energy, for example, if you install a turbine, EGL has to move down. So EGL moves down due to losses, due to head loss or a turbine's involvement, let us say, or a turbine, when you are having a turbine involved. Fine. So this is a case. And for EGL to move up, there is only one case possible. You see, in a flow which is unaffected by external work, EGL can never move up. HGL can move up, but EGL can never move up. For this to happen, the only thing is you are supposed to have an external source of energy, for example, a pump. EGL moves up only if a pump, by pump I mean any kind of external source of energy. You can have a, something like a fan also over here, fan or blower or pump, any of these things are fine. EGL moves up only if a pump is installed, is involved, is involved. Fine. So this is regarding the motion or the growth of HGL and EGL. HGL can grow upward or downward. EGL in generally should move downward. It can move upward provided you are having an external source like a pump. Moving further, one particular case is extremely important. Very, very important case. Now you see, what happens when you are having a uniform diameter pipe? Think about this thing. In the case of a uniform diameter pipe, we know that the velocity throughout has to remain a constant by the virtue of continuity equation. You see, diameter constant implies area also is constant. Therefore, velocity has to remain a constant. Fine. If velocity remains a constant, that means the gap between HGL and EGL is going to be maintained. V square by 2G is constant. Therefore, the gap has to be maintained. From here, I can conclude that in the case of a uniform diameter pipe, HGL and EGL have to be parallel. If they are lines, they will be parallel lines. If they are curves, they are going to be parallel curves. So let me write over here, fourth point. In the case of a uniform diameter pipe, uniform diameter pipe, in the case of a uniform diameter pipe, let me mention over here, V square by 2G is going to remain a constant. V square by 2G is going to remain a constant. What happens now? HGL and EGL have to be parallel. In other words, say have identical slopes. Being parallel is as good as identical slopes. Have identical slopes. This is one more point you are having. It's true provided you are having a uniform diameter pipe. Moving further, one more point let me mention over here. Now tell me, does HGL or EGL have to do anything, or their slopes have to do anything with respect to the slope axis of flow? Imagine the flow is like this. I am having GL over here like this. Fine. Example sake. If for the same flow conditions, if the slope changes, will the value of the slope of HGL also change? No. Remember this thing. There is no established relationship between the slope of HGL, EGL and the slope of the axis of flow. So let me write this. The slopes of HGL and EGL need not be dependent on the slope of axis of flow. Need not be dependent on the slope of axis of flow. Fine. These are some points. There is one more point that is very important for interviews. That point I'll discuss when I'm discussing the concept of siphon. So right now, let us summarize what we have seen regarding HGL and EGL. We have seen that the locus of total head is known as your energy grade line. Locus of piezometric head is known as hydraulic grade line. We have seen 5 points over here. One point is the difference between these two lines is velocity head. Second thing we have seen over here is HGL will remain below EGL. It can overlap with EGL provided you are having velocity as 0. For example, a reservoir. Third point you have seen, HGL can grow downward. It can grow upward also. No problem. This happens. But for EGL to grow upward, you require some external source of energy implied. And that is, for example, a pump. Next, we have seen in the case of uniform, this is very important. This point is extremely important. Okay, because most of the times in your examination, you will get questions wherein you are having a uniform diameter pipe. In the case of a uniform diameter pipe, HGL and EGL are going to have identical slopes, or they are going to be parallel to each other. Next point I have mentioned over here, that there is no established relationship between the slopes of grade lines and the slope of axis of flow. Fine. These kind of points can be important for your theoretical questions. Now that GATE examination also has come up with multiple option questions where multiple answers can be correct, you can expect some theoretical questions also. We have seen the meanings of the grade lines, two grade lines, energy and hydraulic. Now let us do an exercise, very important to understand how the flow is taking place and how the energies are going to transfer. This is examples of grade lines. We are going to draw energy and hydraulic grade line in some cases. Let us start with the simplest case. Imagine you are having a uniform diameter pipe. Let us say you have a uniform diameter pipe over here. The flow is taking place in this particular direction. I can say the flow is taking place over here because I see that in this particular reservoir R1, I am having higher total head, and in this reservoir R2, I am having lower total head. Furthermore, D over here is constant. Apart from D being constant, in order to simplify my exercise, I am also neglecting minor losses. So let us say head loss minor is neglected. So let us consider this value to be equal to 0. Now let us see how to draw the grade lines. Before I straight away draw, tell me what is the formula for head loss major? When we are having the concept of discharge, we can say, let me do one thing. Let me push this over here. We know that the formula for head loss major happens to be equal to FLV square by 2GD. FLV square by 2GD. And I also know that this formula of head loss major is also equal to, 1 by 12.1 FL Q square upon D power 5. This is the formula we are having. Fine. I want you to observe over here. The value of F is constant. In this particular pipe, F is constant. Apart from F, the value of Q is also constant. The value of D also is constant. That means the only way head loss is varying is with respect to length, and head loss is linearly proportional to the length of the pipe. So I can say over here, head loss major has to be proportional to L power 1. This is something we have already seen. We are again establishing this. What is the purpose of establishing this? Purpose of mentioning this, let me tell you, what is the purpose of mentioning this thing? You are seeing over here some amount of head loss. How much head loss are you seeing? If you observe, you can say that this distance over here is right now representing your head loss major. This is representing head loss major. and this distance over here is representing the length of the pipe. I see that the vertical distance between these limits is head loss major and the horizontal distance between them is L, which implies that my energy grade line is supposed to linearly move down from this particular level till here. I hope you're following this. Since this head loss major is linearly proportional to L, I am supposed to have a straight line dropping down over here for my energy grade line. I am neglecting minor losses, so my energy grade line now is supposed to come in the form of a straight line. Let us say this is my EGL. It is a straight line. Now it is a straight line, I can do one more thing. I can try to visualize its slope. Not exactly slope, but something similar to slope, let us say. How to visualize that? Imagine, let me do one thing. Let me take a different color. Imagine I take a very small portion along this particular line, extremely small portion. Let's say I construct this triangle. Now what can I say that this is representing? What is this representing? It is representing a small distance along the length of the pipe. So let me call this as DL. And what is this vertical representing over here? The vertical is representing a small distance along the vertical over here, that is head loss major. So let me call this as D head loss major. So now I see that something similar to slope over here is being represented by D head loss major upon DL. So now I can say from here that there is something called as D head loss upon DL. Which incidentally over here also happens to be equal to complete head loss major upon L. How can I say so? Since it is a straight line, I can say D head loss by DL has to be equal to complete head loss by. Now tell me from here, what is the value of H by L is going to be? The value of H by L is going to be equal to 1 by 12.1 F into Q square by D power 5. This is the value I am having. I hope you are following. This is the value I am having. And this is actually very important to understand. One moment, please. 1 by 12.1 FQ square by D power 5. This is the value of head loss per unit length. Please understand this as head loss, that is major head loss. Head loss per unit length of pipe. Head loss per unit length of pipe. Now you see over here, if I am having my EGL very steep, please try to understand the meaning of steep. Steep mean in this particular case something like this, which is having a very difficulty in climbing up. That is something like steep. If I have steepness of my EGL, if my EGL is more steep, then I would have a higher value to this thing. What would the higher value to this thing mean? It would either mean that F into Q square is high or D power 5 is less. Are you following? In most cases, you can say that steeper the EGL, more the discharge is going to be there. Steeper the EGL, more the discharge. Hold this thought. If you want, please write it down in your book as a note. In most cases, steeper the EGL, more the discharge is going to be there. I am going to use this much later while drawing the grade lines for parallel connections. So steeper the EGL, more the discharge is going to be there. Fine. After having understood this, let us move further. Let us also represent over here hydraulic grade line. Let us represent hydraulic grade line. How would my hydraulic grade line look like? Let us say I'm using the black ink to show hydraulic grade line. I know that in reservoir, the value of velocity over here is equal to 0. If velocity is equal to 0, piezometric head has to be equal to total head. Is it not? Piezometric head has to be equal to total head. Same thing is happening over here. Piezometric head has to be equal to total head. Therefore, if this happens, I can say the representative of metric head is what? Hydraulic grade line. And the representative of total head is what? Energy grade line. So both of them are going to be identical. In reservoir, HGL will coincide with EGL. HGL has to coincide with EGL. So in reservoir, I know that this white line, what is the level of the fluid, itself is representing my EGL. And as a matter of fact, it is also representing my HGL. It is also representing my HGL. Fine. After having shown HGL in the reservoirs, the moment you enter into the pipe, what will happen? Will HGL and EGL coincide over also? No, of course not. The reason is I am having some velocity developed. So now once the velocity gets developed, HGL and EGL, which were previously overlapping, please imagine they were overlapping, now they are going to separate off. Separate off by how much distance? By a distance of V square by 2G. They are going to separate off by a distance of V square by 2G. So let us say my HGL will now drop down. It will now drop down by a distance of V square by 2G. And then it is going to maintain a parallel. Please imagine it is parallel, okay? It is going to become parallel and then it is again going to rise up. Please imagine that these two over here are parallel to each other. The gap in between them has to be equal to V square by 2G. So this is a very, very basic diagram of grade lines. Okay, you are having reservoirs, you are having a constant diameter pipe, you are neglecting minor losses. Everything over here is quite ideal, okay, except you are having major losses, of course. And one more thing I mentioned, that the steepness of the grade line, energy grade line, basically represents your head loss per unit length. In most of the cases, it would show that the discharge is going to be higher. Fine. This is the first case. Now let us take the second case. Again, I'm having the same pipe, same two reservoirs, R1 and R2. Let us say R1 and R2 again. The diameter again over here is constant. Only difference is I am considering the minor losses. Head loss minor over here is not equal to 0. We are considering the minor losses. Fine. I can again say that the EGL and HGL in reservoir R1 and R2 are going to be same. Let us say the white line over here represents energy grade line and the black line represents hydraulic grade line. Same thing over here. So EGL and HGL are going to be, so therefore let us say they are overlapping each other. Next, what should happen? Look over here. The moment a fluid particle is entering from the reservoir into the pipe, it is going to experience some minor loss. What kind of minor loss? Since it is entering into the pipe, it is called as entry losses, and the standard value of entry loss is equal to 0.5 V square by 2G. So fine, we are going to do over here. Let us draw a vertical line over here, sudden loss having, which is equal to 0.5 V square by 2G. Next thing, the moment a fluid particle is moving from the pipe into the reservoir, it is going to have exit losses. standard value of exit loss is equal to V square by 2G. So let us say my EGL would be somewhere over here. It is going to drop down suddenly by V square by 2G, and then it is going to join with this particular line. So these are my corners of my EGL. Furthermore, since the diameter is constant, I am having some length over here. My EGL is going to be a straight line starting from here till here. This is my energy grade line. This is my energy grade line. Tell me, if the previous case and this case are having same reservoir, same length, diameter, same friction factor, in which case would the discharge be higher? In which case would the discharge be higher? This is a very interesting question. If you see the value of dH upon dL in the previous case and this case, both of them are not equal. So let us say dH upon dL in the previous case. Let us mark previous case as case 1. And if I look at dH upon dL in this particular case, let us mark this case as case 2. If I ask you to compare both these cases, in which case is the value dH upon dL going to be greater? Of course, it is going to be greater in this particular case. It is going to be greater in this particular case. Now, if it is greater, what is the value of this thing? Recall the value of this thing is 1 by 12.1 F into Q square by D power 5. Greater than, in case 1, is greater than 1 by 12.1 F into Q square by D power 5 in case 2. I know that 1 by 12.1 is not going to change. F, of course, I am taking as same. D power 5 is also not going to change. That means who is changing now? Discharge is changing. That means discharge in the previous case, when I neglected minor losses, was greater than the discharge in this case, that is when I am considering the minor losses. Please remember, whenever you neglect minor losses, you are going to get more discharge than in the case where you are considering the minor losses. That's a rule. Fine. I hope it is clear from here. So this is regarding my energy grade line. What about hydraulic grade line? You see, drawing hydraulic grade line is one of the easiest. The reason is, it is supposed to be separated from EGL by a distance of V square by 2G. So all you got to do is, you have to take a distance of V square by 2G, and since the diameter is constant, maintain a parallel line. So let us say I am having a distance of V square by 2G over here. This distance is equal to how much? Let me show all the distances now. One moment, please. First of all, this is my hydraulic grade line. Let us show all the distances. This is going to be your entry loss. Entry loss was equal to how much? 0.5 V square by 2G. This is the gap between your EGL and HGL. That is equal to how much? V square by 2G. And this over here is your exit loss. This again is equal to how much? V square by 2G. So this is of grade lines in the case of a diameter constant pipe, while the value of head loss minor is being considered. Fine. I hope you are understanding this. This is actually a very important thing to understand if you want to draw complex grade lines. Fine. Let us move further to the next case. Let us take this particular case. Very interesting case. So what are you seeing? Straight away you are seeing that the diameter is not constant. Diameter over here is not constant. As a matter of fact, I am going to include this particular case later on in a problem also. You will be seeing this in miscellaneous problems. So diameter is not constant, and let us say for the sake of simplicity, I am doing one more thing. Head loss minor, I am neglecting. Head loss minor, I am neglecting. Fine. Let us say this is my reservoir R1, reservoir R2. I'll straight away do some things which will be very easy for you. My white line over here represents EGL, black line represents, black line represents HGL. I know that EGL and HGL are supposed to overlap each other in this reservoir. EGL and HGL would overlap each other in this reservoir. How to draw the diagram? To draw the diagram, I am going to take the help of head loss per unit length, that is major head loss per unit length. Recall, let me do one thing. Let me bring this down. First, let us do some calculations, some mathematics. I know the value of head loss per unit length has to be equal to how much? It has to be equal to 1 by 12.1 into q square by d power 5. Now, if you see this particular pipe, you're finding that, of course, the value of f we are going to take is a constant. Okay, generally we take the value of f as a constant. The value of q also has to be constant. Throughout this particular pipe, a taper pipe, q has to remain a constant by the virtue of our basic equation, that is continuity equation. So mind you, 1 by 12.1 constant, f constant, q constant, all these things are constant. So who is the variable? The variable over here is diameter. That means I can say differential head loss per differential length is proportional to 1 by d power 5. Proportional by d power 5. What does this imply? It implies that the steepness of my energy grade line has to be inversely proportional to diameter per 5. So if I have more diameter, imagine if I am having more diameter. If I have more diameter, dH upon dL has to be less. That means my grade line, energy grade line, steepness will be less. I am using the word steepness. Imagine steepness as some kind of slope to climb a hill. Fine. So if I am having more diameter, lesser steepness. If I am having lesser diameter, you see at the end, I am having lesser diameter. What does this imply? This implies higher steepness. So first thing I understand from here is I am not going to have a straight line first of all. For energy grade line, I can't have a straight line. I am supposed to have a curve. What kind of curve? What kind of curve? Ask yourself this thing. Let me ask you first of all. I am showing you two curves over here. Which curve would be suitable? Would the first curve be suitable or the second curve be suitable? Which curve would be suitable? See, in the first curve, I am going to have over here, if I take a differential triangle, a very small triangle over here, this is my DH, this is my DL. Steepness less. And if you look at the corner, this corner, you are having DH, DL. Steepness high. So I believe this has to be correct. At the very same time, you can prove this is wrong. The reason is, you see over here, DH and DL. So I see you are having more steepness over here. That is not possible because diameter is greater in this corner. I understand. Likewise, if you see over here, DH, DL, steepness is less. So now tell me, first case has to be correct. Therefore, I am supposed to construct my energy grade line, something like this. Let us say this is my EGL. This is my EGL I'm having. I hope you have understood why I'm getting EGL something like this. Okay, moving further. How will my HGL look like? Okay. Will it be a curve exactly parallel to EGL? Take a moment, pause the video if you want and think over it. Will HGL be a curve parallel to EGL? Will HGL be parallel to EGL? Answer is no. Because parallelness can come provided the velocity is constant, not discharge, velocity. parallelness will come provided the velocity is constant. But over here velocity is not constant. I see that velocity over here is high. I see that velocity here is less. That means the gap between EGL and HGL over here will be lesser gap. And the gap between EGL, I'm not having enough space over here. I hope in your book you'd be having. The gap between EGL and HGL over here has to be greater because velocity is high. So I'm having lesser gap over here, more gap. This is not doing justice with what is happening. Please imagine. One moment, please. Lesser gap over here. Okay, more gap over here, something like this. Fine. Try to imagine that you'll be having lesser gap, more gap. The reason for having more gap is because velocity head over here is high. Reason for lesser gap is velocity head over here will be less. Fine. This, let us say, is your HGL. This, let us say, is your HGL. I hope this is clear to you. Whenever you're having diameter not a constant, I hope you know how to construct your EGL and HGL using these concepts. Let us move further to the next case. This case. What kind of setting is this? You're having a compound pipe problem with a series connection. A compound pipe problem with series connection. So let us again start. This is our reservoir R1. This is reservoir R2. Let us say black line for HGL and white line for EGL. White line for EGL. In reservoirs, they are going to overlap, needless to mention now. They are going to overlap each other. Next, what is going to happen? First thing, over here I'm going to have my head loss minor 1, head loss minor 2, head loss minor 3, head loss minor 4, 4 minor head losses. Okay, 4 minor head losses. Let us say I drop down over here by head loss minor 1. Next thing, now tell me, everywhere discharge is same, Q1, Q2, Q3. I know that Q1 has to be equal to Q2 has to be equal to Q3. This is something we have established long back. Okay. Now, if discharge is same, look at this. dH upon dl again is proportional to 1 by d power 5. Of course, in this much range it is going to be a straight line. In this much range again it is going to be a straight line, but both these straight lines are not supposed to have the same slope or same steepness. I see that diameter over here is high, so steepness over here will be less. So let us say I'm having something like this. Excuse me. I'm going to have a straight line, something like this. Something like that. Then I'm again going to have a minor loss. I'm again having a minor loss. After this minor loss, again I'm going to have a straight line, but this time with a higher steepness, higher slope. So let us say, excuse me, this is way too much. Let us say something like this. Okay, please imagine the slope over here is greater than the slope over here. Fine. Again you are going to have a minor loss. You are going to have some minor loss. Again you are going to have a grade line something like this. Again a minor loss. Minor loss. Let us see what are the values of each of these minor losses. Values of each of these minor losses. This one has to be equal to, tell me, if the velocity over here is V1, the velocity is V2, the velocity is V3. Come on, you're supposed to answer me these things now. If velocity is equal to V1, how much is this value equal to? It is an entry loss. That is why standard value has to be equal to 0.5 V1 square by 2G. 0.5 V1 square by 2G. Next thing, what is the value over here equal to? What kind of loss? Expansion or contraction? You are having contraction taking place. In contraction loss, we remember the formula. It is the formula in the next pipe, square by 2G, that is V2 square by 2G, V2 square by 2G multiplied to 1 by Cc minus 1 whole squared. I hope you remember all these formulas, very basic formulas. Next thing, what about your minor loss 3? How much is it going to be? Expansion or contraction? It is expansion. And we know that expansion loss is supposed to be velocity in the initial pipe minus velocity in the forward pipe whole square by 2g. Therefore, it is V2 minus V3 whole square by 2g. Whole square by 2g. Next, finally, how much is this loss supposed to be? This loss is supposed to be equal to how much? It is supposed to be equal to how much? Yeah, it is expansion loss, exit losses, supposed to be V3 square by 2g. V3 square by 2g. These are the minor losses. What about your HGL? How is the HGL going to look like over here? I told you previously also, HGL is supposed to be separated by a distance of V square by 2g. Let us say this gap over here is going to be equal to V1 square by 2g. V1 square by 2g gap, parallel. It is going to get separated over here by V2 square by 2g, parallel. Then going to get separated by V3 square by 2g, parallel. These two are going to be parallel. These two are going to be parallel. These two are going to be parallel. The gaps in each of the cases are equal to the corresponding pipe's velocity head. So this is how you are going to draw grade lines in the case of parallel connection, series connection. Next one, very interesting case, slightly complex case. You might find it difficult to understand initially, but repeat the video again if you want and work over it, you might understand this thing. Okay, looks very simple, but I said it is complex. I'll tell you why. Initially, I'm having this reservoirs, let us say, reservoir R1, reservoir R2, and this reservoir, let us say, the complete value of head loss over here, let us see, is equal to capital H. The complete value of head loss is equal to capital H. I am giving you the liberty of neglecting minor losses. So head loss minor equal to 0, let us say. I am giving the liberty of neglecting minor losses. I am not even interested in your hydraulic grade line. My interest is only in energy grade line. Let us say the white line represents energy grade line. If I ask you how to draw the energy grade line, say this is the simplest case, correct? It is the simplest case. How would it look like? It would be a straight line starting from here, ending till here. So let us say you are having some line like this. Fine. This is my EGL. And I know that if I take, if I take this as DH and this as DL, I know the value of DH upon DL is equal to 1 by 12.1 F into Q square by D power 5. There is no doubt about this thing now. I hope it is clear. Nothing is difficult about this. Now the difficulty starts. The difficulty, let us say, something like this. The people near this reservoir R2, they are demanding more water. They want more fluid over here, more discharge over here. So you as an engineer are supposed to suggest some method of increase the discharge. So you come up with two ideas. There are two standard ideas of increasing discharge. One method is to use a pump and the other method is to use a parallel connection. Let us say we are right now interested in parallel connection. So you do some calculation and you find out that, okay, fine, somewhere in middle, let me give a parallel connection to the pipe. For a portion of the pipe, I am giving parallel connection. So let us say somewhere in middle, you cut over here you cut over here and you say, I am going to supply, one moment please. You say that you are going to supply some parallel connection over here. You are going to supply a parallel connection over here. And now let us create a nomenclature. From here to here, I am calling this pipe as pipe P1. From here to here, I am calling this pipe as P2. And this parallel pipe, this parallel pipe, I am calling as parallel pipe P3. Okay, please imagine that it is having a constant diameter. Don't go at my diagrams. If my diagrams are not supporting what I am saying, you do the imagination. So this pipe P3 is also having a constant diameter. What diameter is all depending on your calculations, how much extra discharge you want. All those things are a separate question altogether. We are right now interested in how discharge is increasing. Let us see now. First thing, the moment you add this parallel pipe, what happens? Look at the sequence of events now. First thing what happens is, previously the value of Q1 is a discharge in pipe P1, and the value of Q2 is a discharge in pipe P2. Previously Q1 and Q2, both of them were equal. Before adding this P3, Q1 was equal to Q2, of course. But now, the moment you add this thing, what happens? After Q1 has come over here, it will bifurcate into Q2 and Q3. It will bifurcate into Q2 and Q3. So now I can write, let me put it over here. Now I can write, previously Q1 and Q2 were equal. Now Q1 is not equal to Q2. Q1 is not equal to Q2. Rather, Q1 is equal to Q2 plus Q3. In other words, you can say the discharge in this particular pipe, has decreased. Q2 has decreased. So let us say Q2 has decreased. Q2 has decreased. Immediate effect of decrease in Q2 is going to be on head loss 2. Look over here. Imagine a virtual node at this particular point. Imagine that, please be patient. Imagine that this distance was initial head loss in pipe 2. This distance was the initial head loss in pipe 2. Now what is going to happen? Since Q2 has decreased, its length is not decreasing, its diameter is not changing, its F value is not changing. Only thing is its distance changing. So automatically the value of H2 also should decrease. H2 also should decrease. If H2 decreases, that means this height is decreasing. That means this particular node will come down. And now the grade line, energy grade line for P2 is going to be something like this. If you are understanding this, half the job is done. This is going to be the new energy grade line. The moment you add parallel connection pipe P3, I am repeating again, please try to visualize. I'll stay away from the board so that you can see. The moment you add P3, first thing that happens is the discharge coming from P1 is going to bifurcate. Therefore, the value of Q reduces from what previous value was there. Because of reduction in Q2, the value of head loss 2 also has to decrease. For that to happen, this imaginary node has to come down. It is an imaginary. This imaginary node, which is above this junction, has to come down. Now you see your head loss 2 has decreased. Your head loss 2 has decreased. This, let us say, is my head loss 2 new head loss 2. As a matter of fact, it is also equal to head loss in pipe P3. It is also equal to head loss in pipe P3. Why so? The reason is P2 and P3, both of them are in parallel connection. If they are in parallel connection, we know that both of them are supposed to have same head loss. Therefore, this is the head loss for pipe P2 new. It is also the head loss of this additional pipe P3 over here. Next thing what happens? Come over here. Next thing that is going to happen is, once this node has come down, now the head loss in P1 has to increase. You see the head loss, my diagram is going to become very complex, but if you're following the entire sequence of events, you'll understand this thing. This is the initial value of head loss 1, head loss 1 initial, head loss 1 initial. This was the initial value of head loss 1. Now, because of this node coming down, my head loss in pipe 1 has to become equal to how much? My head loss in pipe 1 has to become this much, head loss 1. Therefore, my grade line is now supposed to shift something like this. It's supposed to shift something like this. Now, please tell me, what is happening to the steepness over here? The steepness over here has increased. If the steepness over here has increased, then immediate effect is the discharge is also going to increase. So the value of Q1 new has to be greater than Q1 initial. Q1 initial. Are you following this thing? So this is how your energy grade line is going to get changed the moment you add an additional pipe. If you still have some confusion, I suggest you to repeat this particular portion of the video, and if you want, I'll write down some things which might help you to understand. I suggest you to conclude these things by yourself, but if you're not able to, I'll write them down. First thing, let me write over here, before adding pipe P3, I was having only one pipe, but I imagined them as two pipes, P1 and P2. And regarding those two pipes, I know that the value of Q1 was equal to Q2. These are initial values. Q1 and Q2 were same. Fine. And of course, the net value of head loss was equal to head loss 1 plus head loss 2. I want you to visualize P1 and P2 as two pipes in series connection. We know that when two pipes are in series connection, their discharges will be same and their head losses will add up to make the net head loss. Fine. The problem starts after adding P3. This is where the problem started. The moment you add P3, from the junction, P3 comes up and tells P2 that let us share the discharge. If they start sharing the discharge, first thing that happens is the value of Q2 reduces. The value of Q2 reduces. Immediate impact of Q2 reducing is the value of head loss 2 also should reduce. Value of head loss 2 reduces. That is where the virtual node comes down. Once the virtual node comes down, you are going to have a new grade line. I hope you remember what I'm saying, that this virtual node has come down. You are having a new grade line. And as a matter of fact, whatever new grade line you're having is going to be identical for both the parallel pipes, that is pipe P2 and pipe P3. So your head loss 2 new is supposed to be equal to head loss in pipe P3 also, by the virtue of being parallel connections. Furthermore, if this happens once the node comes down, the immediate effect on pipe P1 will be what? Whatever is the decrease in head loss 2 has to be compensated by increase in head loss 1. So head loss 1 has to increase. What do I mean this thing? Again, see over here. What do I mean by this thing? Head loss 2 decreased. This vertical height is basically decrease in head loss 2. It is also increase in whom? Head loss 1. Increase in head loss 1. Head loss 1 increases. What is the immediate effect of head loss 1's increase? Immediate effect is Q1 will increase, or basically the net discharge will increase. This is how parallel connections help you in increasing the discharge. So this is regarding the grade lines in the case of parallel connections. That is, I have only shown over here energy grade line. This is energy grade line in parallel connections. Moving further. Next thing. Let us take the case of pump and turbine. Very simple thing. I'm not going to draw very complex diagrams over here. Imagine you are having a pipeline, line diagram piece, a pipeline. Somewhere over here, you are having a pump. Again, a pipeline over here. Okay. Flow, let us say, is taking place in the direction. Flow is taking place in this direction. I wish to show my energy grade line and hydraulic grade line. Let us say white ink for energy grade line, black for hydraulic grade line. So let us start with energy grade line. Energy grade line, let us say something like this. The moment pump is going to be encountered, pump is delivering the fluid. Therefore, this energy grade line will rise up. Please understand, this is the only place where energy grade line rises up. For EGL to rise up, you have to have an external source of energy like pump or fan or blower, something like that. Next, after that, you are going to have this. This, let us say, is your EGL, energy grade line. Exactly by a distance of V square 2G, you are going to find your hydraulic grade line. You are going to find your hydraulic grade line. Hydraulic grade line. And then this HGL also is going to rise. If the velocities are going to remain same in both these pipes, exactly parallel again over here, you are going to have this distance and this distance will remain same provided the diameter D1 and D2 will be same. If D1, D2 is same, then this distance and this distance will be same, of course. Now the question over here is, by what distance is this rise up taking place? What is this rising up distance? How much is it equal to? I mean, this vertical is equal to how much? This vertical in our terminology is HP. It is head of pump. Remember this head of pump, we have studied this in Bernoulli equation. HP over here is head of pump. It is going to rise by whatever head the pump is going to supply to the fluid. Fine. This is a case of grade lines in the case of pump. Exactly reverse thing will happen in the case of turbine. I would suggest you to pause the video now and see how turbine grade lines are going to be. And then check. Let us say turbine, you are having something like this. Let us say your EGL is going to be something like this. This is EGL. And then you're going to have a sudden loss. Not loss, rather, you're transferring your head to the turbine. And then like this. This is your EGL. And HGL is going to be parallel to this. Parallel again over here. Provided the diameters are same. And then HGL over here. This is your HGL over here. Fine. Again, these two distances are going to be same provided D1 and D2 are same. Furthermore, if you observe, this gap, how big is this going to be equal to? This is going to be equal to HT, head of turbine. That is the amount of head supplied by the fluid to the turbine. That is HT over here. So this is regarding some examples of grade lines. It is sufficient to you. One more example is actually there that I am discussing in the concept of siphon. Please go through that example also. Siphon is actually a very critical case for grade lines, where you will conclude one more important point for grade lines. So this is regarding the concept of grade lines. Now let us take this question. This is an assertion reasoning question. The question says, statement 1, the dimples on a golf ball are intentionally provided. Okay. Dimples over here are the technical word only. Okay, it is not a slang way of denotion. It is a technical word used for a golf ball's indentations. If you have seen a golf ball, it is not perfectly smooth. It is going to have some kind of indentations throughout the surface. Throughout the surface, it is going to have some indentations. Okay, my diagram might not be supporting what I'm saying, but please imagine. Statement 2 over here says, a turbulent boundary layer, since it has more momentum than laminar boundary layer, can better resist an adverse pressure gradient, thus avoiding early separation. Okay, two statements we are having. Let us talk about the first statement again now. Are these indentations or dimples accidentally provided or intentionally provided? These are not any manufacturing defects. So these are actually intentionally provided. So statement 1 over here is correct. There is nothing wrong with statement 1. Statement 1 over here is correct. But what is the purpose? What is the purpose of intentionally providing these indentations? Now when you put these indentations, what happens is, with respect to the smoother ball, this particular ball becomes a rough surface. And we know that rough surface boundary layer separation is going to take place much later. If boundary layer separation takes place much later, you are going to have lesser drag, lesser losses. And why is it all happening? Because the rough surface is going to develop turbulent boundary layer. Now look at the second statement. Second statement says, a turbulent boundary layer, since it has more momentum than laminar boundary layer, can better resist adverse pressure gradient. Yes, it has more capacity of resisting adverse pressure gradient, thus avoiding early separation. So separation will take place much later. This statement also is correct, and this is exactly the reason why statement 1 is correct. Due to this reason, we are having those indentations provided. If you remember, we have spoken about a cricket ball also. Okay, we have talked about how an older ball can generate more speed, and again the same reason was there. You see, an older ball is going to have rougher surface. The losses due to drag are going to be relatively less, so speed of the ball increases for the same effort used by the bowler, right? So statement 1 correct, statement 2 correct, and statement 2 happens to be the correct reason also. Therefore, I can say the answer over here has to be option A. Now imagine you are having two reservoirs. Let us say a reservoir somewhere over here at a higher elevation, and you have another reservoir at a relatively lower elevation. And suppose you have to deliver water or liquid from this reservoir to the other reservoir. So one thing you can do is you can connect a pipe in between. This is fine. But let us take a particular case, very important, wherein these two reservoirs are being separated by some kind of a hill. Let us say you are having a hillock over here, and this is separating. You cannot have a pipe stretching from this reservoir R1 directly to the reservoir R2. Directly to the reservoir R2. Then what? In this particular case, we are going to employ a kind of pipe which is something like this, a uphill pipe, then with a downhill over here. And this particular pipe is a topic which is known as siphon. Very important pipe. It is known as siphon pipe. Very, very important pipe. Let us see a schematic diagram for siphon. Look over here. You are having a neater picture of siphon over here. Let us say I have this reservoir R1 over here. The reservoir R1 is over here. The reservoir R2 is over here. I am having a pipe stretching over here. This is siphon pipe. Now some terminologies you have to remember. One term over here is for the topmost point of the siphon. This is a very, very critical point. It is known as summit of a siphon. S over here stands for summit. It is called as summit of a siphon. How the flow look like once it is fully established? That we can understand by drawing, grade lines like EGL and HGL. So let us do one thing. Let us draw the grade lines in the case of siphon. This is very interesting, very important. If you remember, when I was discussing grade lines, I told you one point regarding grade lines I am not mentioning that time. I'll be mentioning over here. Let us see that particular point. Let us say I have these two reservoirs. I want to draw grade lines over here. I am neglecting minor losses for the sake of simplicity. So first thing, how will the EGL look like? How will EGL over here look like? Energy grade line. Straight up, I have to connect these 2 points for getting my EGL. I have to connect these 2 points for getting my EGL. You have seen this already. So let us say I am directly connecting these 2 points with a straight line. The reason for having a straight line over here is because the diameter of the pipe is being maintained as constant. The flow rate is constant, diameter is constant. So you can say the value of head loss is equal to, we know, 1 by 12.1 FLQ square by D power 5. We know that the value of F is constant, the value of Q is constant, the value of D is constant. Therefore, H upon L is constant. Therefore, we are having a straight line over here. That is the reason our EGL is going to look something like this. So let me mention over here EGL. This is my EGL. Now, how would HGL look like? We know that in these cases, HGL is going to be separated from EGL by a distance of V square by 2G. So let us say over here, I am moving down by V square by 2G. I am going to have a line coming parallel to EGL. The reason being, the velocity throughout this pipe is maintained constant. So therefore, I am having a parallel line over here. One moment, please. Parallel line over here. Please imagine it to be parallel if it is not looking so. And then again, it is going to rise up to meet over here. Fine. Now let us make this picture slightly bigger so that you can understand this diagram. This over here is representing HGL. This is representing HGL, hydraulic grade line. Fine. After having understood this, let us start analyzing this thing. Imagine you take a reference datum, let us say, at this particular level, datum head is 0. Fine. I take a particular point over here. Let us say there's a particular point over here, point 1, let us say. I take a point over here. I want to look at how the piezometric heads are present at this particular point. So first thing, one moment please. If I draw a vertical line, over here, this line is going to give me the datum head. This is the datum head I'm having. Let us say I'm drawing a vertical line from here. Okay, please imagine this thing, this vertical line that is representing my pressure head. Fine, till here everything is okay. Now please do some animation in your mind. Imagine that this particle 1 is keeping on moving forward. As the particle 1 keeps on moving forward, what is happening? Its datum head is keeping on increasing. You see the datum head over here will be slightly greater. And then what is happening to your pressure head over here? Pressure head is keeping on decreasing. You see, pressure head is keeping on compromising, it is decreasing. To the point that, let us say, the point 1 comes at this particular point. Please answer me now. When the point 1 or the particle 1 comes at this particular point, what is going to happen to the pressure head this time? The value of pressure head over here will become 0. Why is it so? Because if you can imagine this way, one moment please, you can imagine this way. Let us say, if you take this entire height over here, this height is representing the datum. Along with datum, this height is also representing P by gamma plus datum head. It is also representing P by gamma plus datum head. It is representing datum because it is showing the elevation, fine. It is representing P by gamma plus Z because it is the HGL I am representing over here. From here I can say that the value of, one moment please, from here I can say that the value of Z and Z cancels off. Therefore, at this particular point, the pressure has to be equal to 0. Very, very important thing. I was having a positive pressure over here. I am having a 0 pressure over here. Let us now say that the particle has shifted over here. Till here it has shifted. That is till the summit. Now, if the particle has moved towards the summit, I know that if I draw this particular height, this height is representing my datum head. It is representing my datum head. Now look at this thing. Look at this very carefully. This entire height is representing datum head. And the piezometric head is given by this much. This is representing P by gamma plus Z. I hope you're following this thing. Now look over here. P by gamma plus Z is lesser than the value of Z. I can write over here, one minute please. P by gamma plus Z is lesser than the value of Z. What does this imply? This implies the value of P by gamma has to be less than 0. It is negative. From here I can make some conclusions. I can say that whenever the flow is below HGL, I am going to have positive gauge pressure. Whenever the flow is at HGL, I am going to have 0 gauge pressure. Whenever the flow is above HGL, I am going to have negative gauge pressure. So let us write these things now. Let me write all this over here. So some notes I am mentioning, very important notes. First point I am having is flow below HGL implies what kind of pressure? Implies positive gauge pressure. Flow below HGL implies positive gauge pressure. Flow above HGL implies implies negative gauge pressure. Negative gauge pressure. And flow intersected by HGL. Intersected by HGL. HGL implies zero gauge pressure. It implies zero gauge pressure. This is a very, very important point. It is not just for siphon, it is in any flow. Whenever you are having these conditions, you can decide what type of gauge pressure you are having. Now let us get back to our siphon. Now we see that in the case of siphon, for a portion from here to here, you are having, I hope you are understanding the diagram now, because this is quite shabby, but please try to understand. From here to here, I am going to have what type of pressure? Negative gauge pressure. And we know that whenever the gauge pressure is negative, it is also possible that the gauge pressure might fall down below the vapor pressure. If it falls down below vapor pressure, we know that the fluid is going to come, it is going to vaporize. There is cavitation that can take place over here. That is why you have to think of some measures to reduce the cavitation effect in the case of siphon, especially in the case of siphon. So how to reduce the effect of cavitation? First thing, try not to give a very high elevation to the summit, because summit is most susceptible or most in danger of cavitation. Try to avoid giving very high height to the summit. That is the first thing. I'll write all those things, don't worry about that. Let us first of all decide these things. Second thing, one more thing you can do is think about the length of this particular pipe. Length of this particular pipe. Now you know that as the fluid is moving along this particular length, it is going to experience head loss. It is going to experience head loss. And this head loss is proportional to the length of the pipe. It is proportional to the length of the pipe. And whenever there is going to be head loss, who is going to sacrifice to give you this head loss? For sure, pressure is going to sacrifice to give you this head loss. So now what happens? More the length of this uphill pipe, more the head loss, and more the drop in pressure. That is why try to make this uphill pipe smaller and downhill pipe bigger. I hope you're following this thing, because in the uphill pipe your pressure is keeping on reducing, whereas in the downhill pipe there is a good chance of pressure increase also, because datum is decreasing over here, therefore pressure is increasing over here. If you're not following, let me repeat this again. A very interesting point, very important point for interviews also. Whenever you see a siphon, you will be seeing that uphill pipe is smaller, downhill pipe is bigger. Why? In uphill pipe, datum is increasing. Datum is increasing. Along with that, you are having head loss. You are having head loss. Datum's increase also will reduce pressure. Head loss also will reduce pressure. Head loss also will reduce pressure. That means there are more chances of reduction in pressure over here. Now come to downhill pipe. You see that datum over here is reducing and head loss is present. Now what happens? When datum reduces, pressure is going to increase, and because of head loss, pressure is going to decrease. Most cases, the net effect of these two things is going to be increase in pressure only. You see over here, net effect is going to be mostly increase in pressure. That means in the downhill pipe, having cavitation is very rare. In the uphill pipe, there are more chances of cavitation. That is why try to reduce head loss. How to reduce head loss? That is, you can reduce the length of this pipe. So mostly in the case of siphon. From here I can conclude that I can write one more note, and that note is reducing the length of uphill pipe is favorable to overcome cavitation effects. Cavitation effects. Are you following this thing? Now, mostly when you're having these kind of siphon problems, the working fluid is water. So it is better for you to remember some standard results when water is a working fluid. We know that, let us mention over here as point 3, if water is a working fluid, if water is working fluid, and mostly water will be your working fluid. We know that when water is a working fluid, the value of 1 atm, in terms of water's head is equal to 10.3 meters of water. 10.3 meters of water. We have studied this thing in statics also, if you remember. Now, if water is supposed to vaporize, in general we say that when the head of water is equal to 2.7 meters absolute, it vaporizes. So for vaporizing of water, the value of pressure has to be equal to 2.7 meters of water in absolute scale. This is in absolute scale. If you measure the same value in gauge scale, how much would you get this as? You would get this as minus 7.6 meters of water. You would get this value as minus 7.6 meters of water. That means if you are having the height between, let me write over here, if the height between HGL and corresponding position in flow, corresponding position in flow, greater than 7.6 meters of water, 7.6 meters of water, then what will happen? If the height between HGL and corresponding level of fluid in the flow is greater than 7.6 meters of water in siphon, then automatically you are going to have cavitation taking place. Then cavitation takes place. Cavitation takes place. Cavitation takes place. So what you have to do over here, you have to see to it that at any particular point, let us say you have chosen this particular point, for example, this particular point, you have to check the distance over here. If this particular distance is exceeding beyond 7 points, it's exceeding 7.6, then cavitation will take place. Most of the time you are going to find the maximum distance between HGL and flow at summit only. It is going to be at summit only. This gap is going to be maximum at summit. Generally we say that if this value is safe, that means it is less than 7.6, then for us nowhere in the flow we are going to have cavitation. So you can say that in the flow through siphon, the maximum distance between HGL and the corresponding point should be 7.6 when water is the flow. Let us take an example problem to understand how to work with this. You are having over here a problem which says there are two reservoirs. The distance between them is 10 meters. Fine. The in the elevation of R1 and the summit over here is 2 meters, that is also given, fine. The uphill pipe is 80 meters, the down pipe 120 meters. Again, you are seeing over here that uphill pipe is generally less than the downhill pipe, fine. Friction factor and diameter of the pipe are also given to you. Now the question asked over here is, find discharge and pressure at summit in terms of head of water, Let us say this is a question we are having. Two things we are supposed to find out. How much is the discharge taking place over here? First thing. Second thing, what is the pressure at this particular point in terms of head of water? Of course, the working fluid also for us is water. Let us see how to approach this question. Let me push it over here. And please feel free to solve the question along with me. This is a question we are having. Let us solve now. First of all, if I want to find out the discharge, I have to get the value of velocity. So first thing is we have to get the value of velocity. So let me draw a rough here now. I am having reservoir R1 over here. I am having a reservoir R2 over here. Rough picture should always be a line diagram. Don't look for neatness, look for answer. Okay. So you are having, let us say, some pipe like this. I'm going to take 2 points over here. Let us say this is point A and this over here is point B. 2 points I'm having. If I apply Bernoulli equation between these 2 points, it is going to be easy for me to work with this. The reason is, I know everything regarding these 2 points. I know the datum difference, I know the pressure at these 2 points, and I know the velocity also at these 2 points. The only unknown will be head loss. From there I'll get the idea of head loss. So let us write now Bernoulli equation between 2 points by Bernoulli equation between A and B. By Bernoulli equation between A and B. What do we get over here? I can say PA by gamma plus VA square by 2G plus ZA has to be equal to PB by gamma plus VB square by 2G plus ZB plus head loss. This is the equation I'm having. Now please observe, point A and point B, both of them are exposed to atmosphere. Both their pressure in gauge scale 0, same, cancelled off. Both of them are in reservoir, therefore we say the velocity is also 0, cancels off. I know the value of Z, I don't know the value of ZA and ZB, but I know the difference. So let me write over here, the value of head loss is equal to ZA minus ZB. Head loss is equal to ZA minus ZB. Now you can look from the question, the value of ZA minus ZB is equal to 10 meters. So from here, I'll say the value of head loss is equal to 10 meters. Now what I'll do is, I'll write the formula of head loss. I know it is equal to FLV square by 2GD. FLV square by 2GD is equal to 10 meters. It is equal to 10 meters. From here I can say the value of velocity has to be equal to root over of 2GD into 10 meters divided by F times L. This is the value of velocity I'm having. Let us look for the value of velocity from here. Put in all the values in SI units. So I'm having velocity is equal to root over of 2 times 9.81 times diameter in SI units is going to be equal to, diameter in SI units is equal to 0.2 times 10 whole divided by F times L. F is equal to 0.02, L is equal to 200 over here. L is equal to 200. L is basically the entire length of the pipe. 80 plus 120 should give you 200. Now this calculation is very, very easy. You see, I can cancel these two things off and I'm having a 10 over here. Now 100 cancels off, two zeros cancel off, 2 and 2 cancel off. Now you're seeing a very good value of velocity that is equal to root over of 9.8, or you can say root over of g. It is root over of g. Velocity is root over g. If you calculate this value, you will get it is equal to 3.13 meters per second. Let me save the value of velocity as certain equation number 1. This, let us say, is certain equation number 1. Getting the value of velocity, it's very easy to find out discharge. Discharge has to be equal to, you know from here, the discharge has to be equal to, Q has to be equal to area times velocity, which is equal to pi by 4 times d square into velocity, which is equal to pi by 4 times, diameter we know is 0.2 square, velocity is equal to 3.13. If you calculate the value of discharge, it comes out to be 0.0983 meter cube per second. In liters per second, you can say it is equal to 98.3 liters per second. So I've got the value of discharge. Half my problem is done. Half my problem is done. Let me save this as some equation number 2. Next thing, I have to identify the pressure at the summit. I have to identify the pressure at the summit. Let us see how to find this out. Very quickly, let me draw the diagram again. You see, you're having a reservoir, you're having a pipe moving up like this. This is what you're having. Now we know that this length over here is 80 meters. This length is 80 meters. That means if I take from here to here how much head loss I'm having, let me call it as H prime. I call it as H prime. How much will that value be equal to? I can say head loss is proportional to length. Head loss is proportional to length. Therefore, H prime, let us say along this thing I'm having H prime, and the entire head loss is equal to, let us say, H. It should be equal to this corresponding height I know is equal to 80. I know is equal to 80 upon the complete length of the pipe I know is equal to how much? 200. It is equal to 200. Now recall, what was the value of complete head loss? The value of complete head loss in this question was equal to 10. From here I can say that the value of H prime, that is the head loss only in the uphill pipe, is equal to how much? 10 times 80 is 800 by 200 is equal to 4 meters. This is equal to 4 meters. Now save this equation. We are going to use this now. Where am I going to use this? I am going to write Bernoulli equation between this point and this point over here. These 2 points I am writing Bernoulli equation. Let me say this point is point A and this point is point S summit. If I write Bernoulli equation between these 2 points, what will the equation look like? Please observe. The equation is going to be PA by gamma plus VA square by 2G, VA square by 2G plus ZA has to be equal to PS by gamma plus Vs square by 2g plus Zs plus the head loss, which is now H prime. This is what I have. Now look at point A. Point A over here is exposed to atmosphere. Therefore, the gauge pressure head is 0. Fine. Velocity has to be equal to 0 over here. The reason is it is in reservoir. If I take the datum over here as 0, automatically the datum of S has to become equal to 2 meters. Because we have mentioned that this height is equal to 2 meters over here. Now, we want the value of PS. We want the value of PS by gamma rather, because we want in terms of head. We want the value of PS by gamma. So the value of PS by gamma has to be equal to how much? It should be equal to minus of Vs square by 2g plus Zs plus H prime plus H prime. Now how much is this value? This value is going to be equal to minus of Vs square by gamma, sorry, Vs square by 2g. How much is it going to be? I am now going to write Vs as root over of g. So it is root over of g whole square. I hope you are following this. Root over of g whole square divided by 2g. Zs is equal to 2. H prime over here is equal to 4. H prime is equal to 4. If you calculate this value, you would get this value as, now g and g cancel off, minus 6.5 meters of water. It is minus 6.5 meters of water. I hope you are following this thing. This is the value of PS by gamma, minus 6.5 meters of water. Now imagine that this value, if it was less than minus 7.6 or also minus 7.6, then cavitation would take place. That is why flow would not take place. Since this value is greater than minus 7.6 meters of water, therefore flow will take place over here. There is no cavitation taking place right now. At this point, let me also tell you one thing, and with that we'll end this concept of siphon. Okay, very interesting thing. That is, how to make the value of PS by gamma lesser. What can make the value of PS by gamma lesser? What can make the value of PS by gamma lesser? The reason is, if the value of PS by gamma falls down below minus 7.6, I am in danger. There is no flow taking place then. Cavitation will take place. So how do I decrease the value of PS by gamma? One way is to increase the value of Zs. One way is to increase the value of H prime. One way is to increase the value of Vs. Forget the value of Vs. Now, what if you increase the value of Zs? That means you are now elevating the summit much higher. If you elevate the summit much higher, then you are going to have danger. Fine. You are going to be in danger of cavitation taking place. That is what some time back I have discussed. One more thing. Elevating the value or increasing the value of H prime. Just imagine that your uphill pipe was 80, downhill pipe was 120. Uphill pipe was 80, downhill pipe was 120. Imagine the reverse thing. Imagine the reverse thing. Uphill pipe was 120, downhill pipe was 80. What would happen then? Just imagine this thing. The value of H prime in that particular case would become equal to 6. The value of H prime, you can calculate this thing, it's quite simple. In this particular case, the value of H prime would become equal to 6. Over here, H prime was equal to 4. Over here, H prime would become equal to 6. Just imagine if I was having a 6 over here. If I was having a 6 over here, then my answer instead of 6.5 would be minus 8.5. Flow will not take place. That is a reason why uphill pipe should always be as less as possible. Fine. So this is regarding the concept of siphon along with an example problem. Let us start the concept of branching of pipes. Branching of pipes. Now this topic is very important, especially in IES conventionals. But in GATE examination also we have seen some questions from here. Once a theoretical question was also asked from this topic in civil paper. Now regarding branching of pipes, very simple topic, logical topic actually. What is going to happen is a set of pipes are going to branch off from a particular junction. And your aim is to identify the direction of flow and the amount of flow, in other words, the discharge taking place. Mostly the number of pipes branching out are going to be 3 in number. That is why this problem is sometimes referred to as 3 reservoir problem also. Let us take an example of a 3 reservoir problem over here. Look at this thing. You are having a particular junction. Let me call this as a junction. I am representing by J. I have 3 reservoirs. Let us say R1, R2 and R3. Similarly, I am having 3 pipes over here, P1, P2 and P3. Now regarding these pipes, some data like length, diameter, friction factor might be given to you. Fine. Now, for the flow to take place, first thing we require is difference in total head, because we know when there is a difference in total head, head loss is developed, and this head loss is going to develop the flow. Fine. So let us say I know that the direction of flow depends on difference in total head. Flow takes place from higher total head to lower total head. By total head we mean P by gamma plus V square by 2G plus Z. P by gamma plus V square by 2G plus Z. Now in these problems, mostly what is going to happen is the value of this V square by 2G is going to be extremely small in comparison to P by gamma and Z, or in comparison to the sum of these two. And what is the sum of these two called as? It is called as piezometric head. So I can say this is basically piezometric head H star plus V square upon 2G. So basically I'm saying in the total head, the value of V square by 2G is much lesser than this piezometric head. If it is going to be much lesser than piezometric head, what I'll do now is I'll say that flow takes place from higher piezometric head to lower piezometric head. Strictly speaking, it should be said as higher total head to lower total head. But since the velocity head is very small and negligible in many cases over here, therefore what we are going to say, we remove the velocity head from the total head, we remain only with piezometric head, therefore we say flow takes place from higher piezometric head to lower piezometric head. So the first rule over here, the first rule in solving these kind of problems is flow takes place from higher piezometric head, higher H star, piezometric head is represented by H star, to lower piezometric head, H star. Flow takes place from higher piezometric head to lower piezometric head. Moving further, next thing. The second rule over here is you are going to find many bends over here, many connections over here. For example, you see a bend over here, a bend here and here. Similarly, you're having some connections over here. Now there are going to be some minor losses, but these minor losses are going to be really small in comparison to the major losses involved over here, because the length of each of these pipes is quite large. Therefore, the minor losses in these cases are neglected. So let me write the second rule for solving these kind of problems. The second rule is minor losses are neglected. Minor losses are neglected. third rule now. This is very important rule, and based on this only we are going to solve most of the questions. Now imagine for the sake of argument that I am having a flow taking place over here, a flow taking place in this direction. Let us call the discharge over here as Q1. And let us say that I am having some discharge taking place in this particular direction. Let us call the discharge as Q2. Let us call the discharge as Q2. Now what is happening? You are having influx at junction J. You are having influx at junction J from both the pipes P1 and P2. There is no chance of accumulation of the fluid at any point. Therefore, what should happen? The fluid is supposed to move out over here. And let us say this discharge is equal to Q3. You are having influx. Over here you are going to have efflux. And if I say that the flow is incompressible and there is no accumulation taking place, then this should be equal to the sum of these two, that is Q1 plus Q2. It is supposed to be equal to Q1 plus Q2. Now how do I put this thing in a statement form? Very simple. In simple language I can say that whatever is the amount of influx at junction J should be equal to the amount of efflux at from junction J. So let us write down. Third point over here is influx at junction J has to be equal to efflux at junction, efflux from junction rather, we can rather, one second, efflux from junction J, efflux from junction J. This is the third point we are having. So 3 points we have seen. First thing, we know that flow should take place from higher total head to lower total head, but we neglect the velocity, therefore from higher piezometric head to lower piezometric head. Second point is a very convenient point and very simple point, neglect minor losses. Third point, again a very common sense point, that if there is no accumulation taking place and the fluid is incompressible, then influx must be equal to efflux over here. Now let us take this idea and observe a particular case. Imagine one more case over here. I am having some value of ZA, let us say. I am having some value of ZA over here. I am having some value of ZB over here. ZB over here. I am having some value of Z at junction over here. These three things are given, let us say. Whatever I am writing in black, imagine it is a given data. Apart from Zj given, I am also having the pressure at this particular junction J given. There should be some pressure at junction J. That is also given. Of course, pressure at these 2 points won't be given to you, that is exposed to atmosphere. It is understood it is equal to 0. Fine. Now, you are given the properties of each of these pipes, let us say. You are given the length over here, you are given the friction factor over here, you are given the diameter over here. Likewise, in every pipe you are given these values, L, F and diameter. Likewise, L, F and diameter over here. All these things are. In general, the question that is asked to you will be, what is the value of ZC? If this reservoir is, let us say, last reservoir, and the datum of this particular level is ZC, the question in general is going to be, what is the value of ZC? Let us imagine such a question. Now, this question tends to become slightly lengthy, but I can simplify the question and give you in GATE examination. They can give the entire lengthy question in IS conventionals. They can also create a theoretical question from the points I mentioned previously. Let us see how to identify the answer of ZC over here. First, how many piezometric heads do you know over here? We have 4 points, A, B, C and junction J. At this point, I know the piezometric head at least of these 3 points. Let us say I know the value of H star at A, that is equal to how much? ZA itself. because we know H star is equal to P by gamma plus Z, but the value of P by gamma at point A is equal to 0. Therefore, we also know the value of H star at point B, that is equal to how much? ZB. And we also know the value of H star at point J, that is equal to how much? Pj by gamma plus Zj. All these three things are known to us. Now, once these three things are known to us, now you can identify the direction of flow in these two pipes. In pipe P1 and 2, you can identify the direction of flow. How? Now I can say, if the value, let us take some cases now. You answer the question as if you are sitting in a class. Please answer the question. If, let us take case 1, if the value of H star, at point A happens to be greater than H star at junction J, and let us take one more thing, the value of H star, let us, one moment please, the value of H star at point B is greater than H star at junction J. Now this thing I have given to you. Imagine what would be the conclusion from here. What would be the conclusion? First thing I want to know is the direction of Q1 and Q2. The direction of Q1 and Q2 is going to be what direction? Think over it. Think over the direction of Q1 and Q2. I'm having some discharge over here Q1. I'm having some discharge over here Q2. Tell me, what is the direction going to be for Q1 and Q2? Of course, if H star at A is greater than H star at J, that means the flow should take place towards J. Therefore, the direction of Q1 should be like this. Is it not? Next, how should the direction of Q2 be? Again, I am having the H star at this point greater than the H star at this point. Flow takes place from higher piezometric head to lower piezometric head over here. That means I am supposed to have the direction over here like this. So direction is decided. Now tell me, what is going to be the direction of Q3? Is it towards the reservoir or away from reservoir? And the value of Q3. Two things you have to tell me now. The direction of Q3 and the value of Q3. I can say the direction of Q3 should be towards the reservoir. Towards reservoir R3. Is it not? Right now the direction of Q3 has to be like this. And what will the value of Q3 be equal to? Think from the influx and efflux point of view. I can say the value of Q3 has to be equal to how much? It has to be equal to Q1 plus Q2. It has to be Q1 plus Q2. It has to be equal to Q1 plus Q2. Then you can start solving the problem. How to solve problem? I'll take an example and show you. Right now let us just look at the basics. Fine. This is one case. Let us imagine one more case. Imagine one more case. Let us say the value of H star at A, is lesser than H star at J, and the value of H star at B is lesser than H star at J. Both of them are lesser. What would the answer now be? What would the answer now be? Yes, please think over it. If the junction's piezometric head is greater, then first of all the flow should take place in this direction. Likewise, here also the flow should take place in this direction. Flow should take place in this direction. So now tell me, how will Q3 be going? Will it be going towards the reservoir or away from the reservoir? Towards or away? For sure it has to go away from the reservoir, because I'm having efflux from this point, so I have to have some influx over here also. Is it not? So therefore it has to move in this particular direction. And again, what will the value of Q3? Let us say away over here, away from R3. And what will the value of Q3 over here be equal to? The value of Q3 again should be equal to how much? Q1 plus Q2, because both of them are going that way, is it not? Fine, this was again a simple case. Now let us take a slightly complicated case. Let us say the value of H star at A is greater than, H star at junction J. It is greater than H star at junction J, but the value of H star at B is lesser than H star at junction J. Let us say one of them is greater, one of them is lesser. In this case, how are you going to solve the question? In this case, how are you going to solve the question? Yes, imagine, think over it. First thing, I know that the direction of Q1 has to be in this. The direction of Q1 has to be in this direction. The direction of Q2, I'm not going to tell you the reason now. You have understood this, I hope. The direction of Q2 should be over here. Q2 should be over here. Now the question is, can you directly tell me now the direction of Q3? The answer is no. You cannot decide the direction of Q3 now itself. Now you have to look at who is greater. So in this particular case, you are going to have sub cases over here. You are going to have sub cases over here. One please. You are going to have sub cases. Let us see what are the sub cases. The first sub case you are having over here is the value of Q1 is greater than Q2. Second sub case is the value of Q1 is lesser than Q2. Second sub case. You will have to identify Q1, Q2 and all. And you have to check who is going to be greater. Imagine if Q1 is greater than Q2. That means at this point influx is greater, efflux over here is lesser. That means Q3 right now will be in this particular direction. Q3 right now will be in this particular direction. So I can say Q3 is towards reservoir 3. Let us say this is R3. It is towards reservoir 3. And what will the value of Q3 be equal to? Think over this. What will the value of Q3 be equal to? The value of Q now will be equal to Q1 minus Q2, is it not? It has to be equal to Q1 minus Q2. Now think of the other case now. Let us say over here Q1 is lesser than Q2. If Q1 is lesser than Q2, that basically means that influx over here is lesser, efflux over here is greater. In such a case, I should again get an influx over here so as to compensate. So Q3 will be away from R3, away from reservoir R3. Q3 has to be away from reservoir R3. And what shall be the value of Q3? How much will the value of Q3 be equal to? The value of Q3 now will be equal to, very simple, I hope you are getting this thing. Since Q2 is greater, therefore Q2 minus Q1. This is a very logical topic. Fine. I generally don't think this much of explanation is required. All that is required is to know that those fundamental points are important. Fine. At the junction, influx and efflux have to be same. And you are going to have flow taking place from higher piezometric head to lower piezometric head. I hope you understand till here. Now what you do? How do you find the value of ZC? Very simple. You can apply Bernoulli equation between this point and this point. Let's say you are applying Bernoulli equation between point J and point ZC over here. So what will you get? Let us say, for example, by Bernoulli equation between point J and you are having ZC at point C, let us say Pj by gamma plus Vj square by 2g plus zj plus zj has to be equal to pc by gamma vc square by 2g plus zc plus head loss. Once you know the value of q, you can get the value of head loss. You know that the value of pc is equal to 0. You know that the value of vc is also equal to 0. Please observe over here. At this particular point, the pressure and velocity have to be equal to 0. Let us say you have the value of head loss using the equation. Head loss is equal to 1 by 12.1 FLQ square by d power 5. Now, once you know the value of Q3, you can find this value also. Chaliye, let us say all those things are known to you. Coming to point J, you know this value, you know this value, and at the junction, we always say the velocity is equal to 0 because influx and efflux, both of them are going to come, both of them are going to become equal. So net discharge at point junction J is 0. Therefore, velocity at J we are going to neglect. If this happens, you can find the value of ZC very easily. So this is how in general the 3 reservoir problem has to be approached. After this, I'll be taking an example problem where we will be seeing a gate level of 3 reservoir problem. Let us take an example problem now. You're seeing over here a 3 reservoir problem. This can be worth 2 marks in gate examination. Look at the problem. Pause the video once and look at the problem and look at what he's asking you over here. Question over here says that there are 3 reservoirs and 1 junction. He has given you the direction of Q1. The direction of Q1 is given to you and the magnitude of Q1 also is given to you. Coming to Q2, he has given you the magnitude but he has not given the direction. And Q3, neither direction nor magnitude is given. Furthermore, he has mentioned you regarding the pressure and datum at point J. He has mentioned the datum at point 2. He is asking you what is the value of datum at this particular point 3. This is a question asked. Imagine how we are going to approach the problem first of all. To get the value of datum at point 3, I need to apply Bernoulli equation between these 2 points. For that, I need to know the value of discharge over here because head loss is depending on discharge. To know the value of discharge, I need to know what is the direction of Q2. So my first aim, look at this thing, my first aim will be to identify the direction of Q2. Let us say I got the direction. Imagine now we got direction. The moment we get the direction, we will come to know the direction of Q3 and also will come to know the magnitude of Q3. Fine. After that, using that value of Q3, we can identify the value of head loss in pipe 3. How? You see, we are given the value of L, F and D. All these things are given. If Q is also known, automatically head loss is known. Once head loss is known, I can apply Bernoulli equation between these 2 points. So I have created an algorithm now. First aim is to identify the direction of Q2. Let us start. How to identify the direction of Q2? So first aim is going to be direction of Q2. Now for that, I have to look for the piezometric heads at point J and point 2. So I can say the value of Hj star is equal to how much? It has to be equal to Pj by gamma plus Zj. The working fluid of course is water, needless to mention now. These kind of problems are mostly dealing with water unless specified. So now this value is going to be equal to Pj is given as 120 kilopascal. So 120 kilopascal upon gamma of water is 9.81 kilonewton per meter cube plus Zj is equal to over here 75. It is equal to 75. Now this value is going to be equal to, 12.23 plus 75, that is going to be equal to 87.23 meters. This is the value of piezometric head at junction. Let me save this as some equation number 1. Next thing, let us look at the value of piezometric head at point 2. Piezometric head at point 2 is going to be equal to how much? It is going to be equal to P2 by gamma plus Z2. We already know this value has to be equal to 0 because I am having exposed to atmosphere conditions. Fine, that value is equal to 0. If that value is equal to 0, from here I can imply that the value of H2 star has to be equal to Z2 itself. And what is the value of Z2 mentioned? It is mentioned as 95 meters. So let me take this as some equation number 2. This, let us say, is some equation number 2. Once both these things are established, I can compare Hj star and H2 star. I find over here that the value of H2 star is greater than Hj star. The value of H2 star is greater than Hj star, which implies that Q2 is supposed to move from reservoir to the junction. So Q2 flows from R2 to junction. It is flowing from R2 to junction. This has been established. My first point over here has been established. So let us do one thing. Let us create a bigger image, and we can mention that Q2 is now moving in this particular direction. If Q2 is moving in this particular direction, next thing I can do is I can imagine what is the direction of flow for Q3. For sure, the direction of flow in Q3 has to be over here. And what should the value of Q3 be equal to? You see, both of them over here are in flux. Therefore, both of them combined should be the value of Q3. So from here I can mention that the value of Q3, now I am taking the second point over here. So I have done the first thing, that is to identify the direction of Q2. Now I can write Q3 has to be equal to how much? It has to be equal to Q1 plus Q2. That is equal to how many liters? You see, you are having over here 80, 60, that is going to give you 140 liters per second. That is equal to 0.14 meter cube per second. 0.14 meter cube per second. Once you get the value of Q3, immediately find out the value of head loss in this particular pipe. Head loss 3 is equal to how much you find out? Because once we know head loss, we can find out, or we can apply Bernoulli equation between these 2 points. So let us start writing now. So I can start writing over here. The value of head loss H3 has to be equal to how much? 1 by 12.1 FLQ square by D power 5. All these things corresponding to pipe P3. And that is going to be equal to how much? That is going to be equal to 1 by 12.1. F over here is equal to how much? 0.02. L is equal to how much? L is equal to 200 multiplied to FLQ square. Q we have identified as 0.14 square. upon diameter power 5. Diameter, if you see, equal to 0.2 meters. So 0.2 power 5. 0.2 power 5. From here you can get the value of head loss in pipe 3, and that should come out to be equal to 20.248 meters. It comes out to be equal to 20.248 meters. Let us save this as some equation number 3. Let us say this as equation number 3. Now the final step. The final step is applying Bernoulli equation between J and point 3 over here, and the flow is taking place in this direction. So I can start writing final step over here. By Bernoulli equation, we know Pj by gamma plus Vj square by 2g plus Zj. Now this is the total head at point J, has to be equal to P3 by gamma plus V3 square by 2g plus Z3 plus head loss, that is head loss pipe 3, head loss in pipe 3. Now I mentioned to you previously also, at the junction we are going to take the value of velocity as 0. So this value is equal to 0. This value is 0. At point 3, now please observe, at point 3 the pressure also is 0, the velocity also is 0. Therefore, at point 3 I am going to cancel off pressure head as well as velocity head. I am going to cancel off velocity head. So from here I can say that the value of Z3 has to be equal to how much? It has to be equal to, now look at this thing, Pj by gamma and Zj are basically H star at point J, minus head loss in pipe 3, Now if you see how much this is going to be equal to, sometime back we have calculated this value, it came out to be equal to 87.23 I believe, minus H3, head loss in pipe 3, is equal to, you are having 20.248. If you calculate the value of Z3 approximately comes out to be equal to 67 meters. Z3 approximately comes out to be equal to 67 meters. The calculation probably has become quite lengthy, but the concept over here is quite simple. This is the answer to the question we have created. Let us now start a very small topic known as pipe networks. Let us see what we study in pipe networks. In pipe network, you will be given a grid formed by some pipes. Your aim will be to identify the relationship of discharge in all the pipes and the relationship of head loss in all the pipes, and find whatever is the unknown value. For example, let us say you are having a grid something like this. You are having a grid something like this. Something like this. Let us say 4 pipes further over here. You are having 4 pipes further over here. Let us say you have some discharge over here entering Q1. You are having certain discharge moving out over here, let us say Q2. You are having some discharge moving out over here, let us say Q3. You are having certain discharge entering over here, let us say Q4. Q4. Further, you are having 5 pipes over here. You are having 5 pipes over here. This is the first pipe, this second pipe, this over here is third pipe, this is fourth, and in between you are having fifth pipe. Let us say you have some QA over here and head loss A over here. You have certain value of QB over here and head loss B over here. Then you have some QC, let us say QC over here and head loss C over here. Next thing, let us say you have some QE, let us say head loss E over here, head loss E over here, and finally let us say you are having some QD and head loss B over here. Fine. So in this particular grid of 5 pipes, you are having discharge and head loss, and these extra pipes you are having, which are input or output, you are only given the value of discharge. Head loss is not given because the end node is not given over here. Now, how to establish the relationship of discharges and to establish the relationship of head loss, we have to see. For that purpose, first thing I am going to talk about is what is going to happen at the node. For example, let us say this is one particular node 1, likewise this is some second node, let us say 2, I am having some third node, let us say 3, and fourth node, let us say 4 over here. At each of these nodes there is some discharge entering, the influx is there, and there is some discharge exiting, there is some efflux. Rule number 1 we are having is, rule 1 let us say we have is, whatever is the influx at a particular node, same should be the value of efflux from a particular node, because we cannot have any kind of accumulation. So influx at a node has to be equal to efflux from node. Influx has to be equal to efflux from node. This is rule number 1. Let us now apply this rule at all these 4 nodes. Let us start with node 1. At node 1, tell me what is the influx, what is coming in. Directions are already mentioned over here, so please tell me what is coming in. I see that Q1 is coming in and QE also is coming in. So from here I can say Q1 plus QE has to be influx. What is moving out from here? I see QA is moving out from node 1 and QC also is moving out. Therefore, this has to be equal to QA plus QC. QA plus QC. Next thing, one moment. Let us talk about second node now. Second node. At node 2, what is the influx over here? I have only one influx over here, that is QA. QA is the only influx over here. And what is moving out? What is the efflux? I have 2 effluxes. One is Q2, the other is QB. So I can say this has to be equal to Q2 plus QB. Fine, this is the equation for node 2. Let us now talk about node 3. Node 3. Come on, this time you are supposed to answer me. What is the influx over here? I find there are 3 influxes. 3 influxes. QD also is in flux, QC also is in flux, QB also is in flux. So I can say QD plus QC plus QB. All of them happen to be in flux over here. All of them combined has to be equal to E flux. What is the E flux over here? It has to be equal to Q3. Has to be equal to Q3. Final node now. Final node. Yes, node 4. Influx. I find there are two influxes over here. One is Q4, the other over here. This also is in flux. The other, no, I'm having only one influx over here rather. Q4 is the only influx. And what is the efflux over here? The efflux over here has to be QE, QD. QE plus QD. QE plus QD. So this is how you can solve the conditions by taking this rule 1. Fine. After having seen this rule 1, the next rule we are having. The next rule we have over here. Let me first of all save this thing. The next rule is for a particular loop. If you see, I'm having two loops. 1, 2, 3, back to 1 is one loop. 1, 3, 4, back to 1 is one more loop over here. Two loops. The rule is the net head loss in a particular loop has to be equal to 0. So let me mention over here rule 2. Rule 2. That is net head loss. Net head loss. Head loss in a loop is equal to 0. Net head loss in a loop has to be equal to 0. Let us see. I'm taking the first loop, that is 1, 2, 3 back to 1. 1, 2, 3 back to 1, let us say, is my first loop. Now, whenever you talk about loops, you are supposed to measure the direction sense in clockwise or anti-clockwise direction, rotational direction sense. For example, I am considering anti-clockwise direction as positive. I am considering anti-clockwise direction sense as positive, let us say. Now you see, with respect to this centroid, tell me, HA is going to be anti-clockwise or clockwise? Of course, it is anti-clockwise, so I can say HA is going to be clockwise, therefore positive. Next thing, HB again is clockwise, therefore plus HB over here, plus HB. Lastly, if you see HC is anti-clockwise, therefore minus HC has to be equal to 0, which implies from here, HA plus HB has to be equal to HC. HA plus HB has to be equal to HC. Now let us take the second loop. Let us say this is 1, 3, 4, 1. 1, 3, 4, 1 is the next loop I'm having. Let us see now. With respect to this, HC is going to be clockwise now. So HC is clockwise, therefore positive. I am having HE also clockwise, therefore plus HE clockwise. It is creating a clockwise motion with respect to the center. HD is these are both of them are anti-clockwise, therefore positive. HD is creating clockwise, therefore minus HD has to be equal to 0. From here I can say HC plus HE has to be equal to HD. HC plus HE has to be equal to HD. This is the second relationship I am having, which is helping me understand the relationship of head loss. Having seen the concept of pipe networks, let us take an example. You can pause the video for a moment and take down the question. Once you have taken down, we'll start solving it. Now let us start the question. You are seeing some pipe network like this. Let me make a smaller diagram out of this. Let us start now. First, we are going to start with nodes. Let us start with a particular node over here, that is node A. At node A, I am observing that there are three connections. One is an influx, one is an efflux for node A. Fine. We do not know whether the pipe 4 is creating an influx at A or efflux. So we'll look over here. Tell me, QA and Q1, if you compare, whom do you find greater? You're finding QA greater. You're finding QA is greater. If QA is greater, it means influx is greater. Therefore, at 4 also I'm supposed to have efflux. So let me create the direction sense over here. This is going to be efflux over here. Let us start now. I can say at node A. Some books also might refer to it as junction A. Same thing. At node A, influx has to be equal to efflux, which implies Q1 has to be equal to efflux over here. Sorry, QA has to be equal to Q1 plus Q4. Q1 plus Q4. From here I can say the value of Q4 has to be equal to QA minus Q1. Now tell me, what is the value of QA minus Q1 over here? So Q4 is equal to 100 minus 40, that is equal to 60 units. So let me write over here, this is equal to 60 units. This is equal to 60 units. Next you see, I know the direction over here, I know the value of Q here, same thing here, same thing here. That means only the value at 5 is unknown. So let us now talk about node D. At node D. Please observe, there are two influxes over here. Sorry, there is one influx over here and two efflux. That is, Q4 is influx, QD and Q3 are efflux. If you compare QD and QE, the value over here combined is equal to 50, while the entry value is 60. Therefore, I can decide that the direction over here has to be something like this. Because entry is greater than exit, therefore he should also be an exit. So over here I can write the value of Q4 has to be equal to, inlet is Q4 only, has to be equal to QD plus Q3 plus Q5, Q3 plus Q5, QD plus Q3 plus Q5. I wish to find out the value of Q5. So I can say the value of Q5 has to be equal to Q4 minus QD minus Q3. Now you can compare 60 minus 20 minus 30 is going to be equal to 10. Therefore, the value of Q5 has to be equal to 10 units. So let me mention over here, Q5 is equal to 10 units. Q5 is equal to 10 units. Next thing, let us now talk about this particular node. Why? I know this influx, I know this influx, I know this efflux. The only thing I don't know is over here. Let us compare, please. Influx I am having is 40 and 10, that is 50. Efflux I am having is 30. Therefore, influx is more. Therefore, I can say this should also be in the form of efflux. This should also be in the form of efflux. Let us mention this thing. Fine. So I can write at node B, that is node B, at node B, what can we say? Influx is Q5 and Q1, efflux is Q2 and QB. So Q5 and Q1 combined has to be equal to Q2 plus QB, Q2 plus QB. I wish to find out the value of Q2 over here. So the value of Q2 has to be equal to how much? It has to be equal to, Q2 has to be equal to Q5 plus Q1 minus QB, that is equal to Q5 and Q1 combined is 50, QB is 30. Therefore, I can say the value of Q2 has to be equal to 20 units. Fine, I have identified the value of Q2 also now. So Q2 is equal to 20 units. Lastly, let us talk about node C. At node C, tell me, I am having two influxes over here, Q3 and Q2, only one influx, that is QC. So I can write Q3 plus Q2 has to be equal to QC. Therefore, the value of QC will come out to be equal to 50 units. The value to be equal to 50 units. So let us mention over here, this value is equal to 50 units. We have identified all the discharges over here. We have also identified the direction sense in each of these pipes. Next thing, after having understood the discharges, let us now talk about head loss. I see there are two loops or two circuits over here. One is ABDA, the other is DBCD. Let me first talk about this circuit, and I am taking anti-clockwise direction over here as positive. Okay, and over here also let us say anti-clockwise direction is positive. I am talking about this circuit ABDA. Let us say ABDA circuit. Now please observe, this is having an anti-clockwise effect, this is having a clockwise effect, and this also is having a clockwise effect. From here I can say that the value of H1 minus H5 minus H4 minus H4 has to be equal to 0. H1 minus H5 minus H4 has to be equal to 0. From here I can conclude that the value of H4 plus H5 is equal to H1 and is equal to 120 units. Still I haven't got the value of H4 or H5. Let us now talk about the other loop. Let me save this equation. As let us say some equation A, not A rather, equation 1 let us say. Let us now talk about the other loop, that is DBCD. Other loop is DBCD. Yes, what do we have from this loop? Now you see, H5 is creating anti-clockwise effect, H2 is creating anti-clockwise effect, H3 is creating clockwise effect. So I have over here H5 plus H2, H5 plus H2 minus H3 has to be equal to 0. From here I can find out the value of H5. The value of H5 over here is equal to how much? It is supposed to be equal to H3 minus H2. That is equal to how much? If it is H3 minus H2, it is supposed to be equal to 60 minus 40, that is 20 units. So H5 over here is 20 units. Let me save this as equation 2. If H5 is 20 units, now I can put H5 is 20 in this equation. So I can say from here, therefore the value of H4 has to be 120 minus 20, which is equal to 100 units. which is equal to 100 units. So now I can write down in this particular circuit, the value of H4 come out to be equal to 100 units. 4 has come out to be 100 units. H5 has come out to be equal to 20 units. These are the answers for the given question. Let us start the concept of hydraulic power. Hydraulic power. I'm not going to define this hydraulic power now. First, what we'll do is we'll take up a diagram. We'll try to understand what is hydraulic power. Later, we'll define it. Imagine you are having a reservoir. You are having a reservoir, let us say something like this, in which you are having a fluid. Suppose this is a reservoir to which in which you are having a fluid. Suppose you are connecting a very lengthy pipe from this reservoir to a turbine. Let us draw a line diagram for this pipe. Imagine that this pipe is quite lengthy. This pipe is actually known as penstock. It is known as penstock. Penstock, penstock. This pipe is trying to discharge water or whatever fluid you are having to a turbine. But before that happens, you are supposed to connect over here. You are supposed to connect over here a nozzle. There is going to be a certain nozzle over here. There's a nozzle, and this nozzle is going to discharge the fluid, let us say, to a turbine. Let us say this is turbine and this is nozzle. N for nozzle, T for turbine, and R for reservoir over here. I'm having some setup like this. Fine. Imagine I extend over here this line forward. I extend this line forward. If I extend this line forward and I measure this entire height, if I measure this entire height, I'm going to call this as gross head. This height is known as my gross head. So let us say this H over here is known as gross head. It is known as gross head. Fine. Now this line over here is representing ideal EGL. It is representing ideal energy grade line. But we know that in reality energy grade line is not going to remain horizontal. So what will happen to actual energy grade line? The actual energy grade line would be something like this. This, let us say, is my actual energy grade line. Or if I just write EGL, it is understood it is actual EGL. Actual energy line. Again over here I have made an assumption. That assumption is I am negating the minor losses. If there were minor losses, we have discussed those things, how EGL would vary in the case of minor losses. So I am neglecting over here the minor losses. Let us say if I measure this height, then this height is known as my head loss. One moment please. This height represents head loss. So let us say small h over here is representing head loss. Small h is representing head loss. So tell me how much head is available before entering into turbine. The head that is available before entering into turbine is equal to capital H minus small h. This is known as your net head. This is known as net head. It is known as net head. So we are having three types of head. One is an ideal head, that is known as your gross head. Second is whatever head is lost, that is your head loss. Then the actual fluid that is contributing towards input power over here, that is known as your net head. Fine. Now what we do, we define something called as efficiency. efficiency over here. Let me write otherwise over here. Efficiency. There is something known as efficiency. Now what is the value of efficiency going to be? Efficiency is going to be equal to how much? It is going to be the head available upon the ideal head. That means net head upon gross head. So it is going to be equal to net head upon gross head. Efficiency is net head upon gross head. Therefore, the value of efficiency would now become equal to how much? Net head is capital H minus small h. So capital H minus small h whole divided by capital H. If you want in terms of percentage, you can multiply this to 100%. You can multiply this to 100%, which implies the value of efficiency is now going to be equal to 1 minus small h upon capital H into 100%. 1 minus small h upon capital H into 100%. Fine. These are some terms we are going to use now. Now let us define what this hydraulic power is. You see, the fluid is moving through this penstock into the nozzle, then into the turbine. It means the fluid is going to give certain power to the turbine. It is the input power to the turbine. That input power to the turbine is known as your hydraulic power. So I can define hydraulic power as the power of the fluid transmitted to the turbine when it is passing through a penstock or when it is coming from a reservoir to the turbine is known as hydraulic power. So let me write over here. One moment please. Let me write the fluid power transmitted to the turbine when the fluid from a reservoir passes through a penstock. Passes through a penstock. This is known as your hydraulic power. Fine. So in simple language, it is the input power to the turbine. That is your hydraulic power. Now the question is, how much should the value of this hydraulic power be? What should the value of hydraulic power be equal to? Let us see. To understand the value of hydraulic power, let me put this diagram over here. Let us start writing now the formulas. Tell me, ideally the head available at the nozzle exit ideally is equal to capital H. Let us say discharge is equal to Q. If discharge is equal to Q, head is equal to capital H, and the property of the fluid is gamma, then I can say the value of power ideal or theoretical. TH stands for theoretical, or you can say power ideal has to be equal to how much? Power theoretical or power ideal has to be equal to, let me write over here, has to be equal to gamma into Q into, ideally how much head available over here? The head that should be available over here is equal to capital. So this is the formula for ideal hydraulic power. Ideal hydraulic power. But we know that there is some power loss. So let us now talk about power loss. What is the value of power loss? The value of power loss over here, the value of power loss over here correspond to this small h. So therefore, the value of power that has been lost is equal to gamma into q into which head? Small h. So this is the value of power loss. This is the value of power loss. That means the actual power that is being transmitted to the turbine is lesser than this ideal. So let us now talk about the actual power. Actual power. What is the value of this actual power? Actual power should correspond to which head? It should correspond to the net head. It should correspond to the net head. Therefore, the value of P actual, has to be equal to gamma into Q into capital H minus small h. This is the value of actual hydraulic power. So we are having over here three types of power. One is ideal hydraulic power, power loss, and finally we are having actual hydraulic power. Fine. We have seen the formulas of power now. Let us talk about a particular condition which is important for you to remember. That is condition for maximum actual power. For maximum actual power. What are the conditions required for attaining maximum actual power? Recall the formula for power we got, actual power we got, was equal to gamma into Q times capital H minus head loss. This was a formula we have got previously. If you observe over here in this particular equation, the value of gamma and capital H are constants. Both these are constants. Whereas the value of Q and small h are variables. So from here I can say that the value of P actual has to be a function of Q and H. If I was having only a single variable, then finding the maximum would have been easy. But if you see over here, I am having two variables, Q and capital H. So now the problem is, since we have two variables, what we are going to do, we are going to convert one variable in the form of other. We have already mentioned that the value of head loss over here is only major head loss. So let us say I can write over here the value of head loss has to be equal to 1 by 12.1 FL Q square upon D power 5. I see for a given penstock the value of 1 by 12.1 is constant, F is constant, L is constant, and D power 5 also is a constant. If all these things are constant, I can say from here that the value of head loss has to be equal to some constant times Q square, or I can say from here that the value of Q has to be equal to some constant times head loss power half, some constant C prime, let us say, multiplied to head loss power half. Let us say I put this value of Q in this equation. So now what do I get? I get the value of P actual, excuse me, I get the value of P actual is equal to gamma into some constant C prime times head loss power half multiplied to capital H minus head loss. This is the equation I'm getting. If you look over here, this entire equation has now come in terms of small h. Gamma and capital H again are constant. The only variable over here is small h. So let us say the equation of power now has become, the equation of power actual has now become gamma times some constant multiplied to capital H times h power half minus small h power 3 by 2. This is the equation I'm having. My aim now is to look for the condition for maximum actual power. I can say that for maximum actual power, for P actual maximum, for P actual maximum, the condition has to be dP actual upon d head loss has to be equal to 0. If I differentiate this with respect to head loss and equate it to 0, I am going to get the condition for P actual maximum. Therefore, I have over here gamma into C prime. Now differential of this thing with respect to head loss is going to be half of capital H times h power minus 1 by 2 minus 3 by 2 times head loss power 1 by 2 has to be equal to 0. Now first of all, this cannot be equal to 0, so you cancel this off. I have to equate only this thing is equal to 0. So from here I can say that, I can say 1 by 2 into 1 by 2 times capital H into head loss power minus half minus 3 by 2 times head loss power half has to be equal to 0. Let us cancel off 2 in the denominator. If I cancel 2 in the denominator, I get over here capital H times head loss power minus half is equal to 3 times head loss power half. 3 times head loss power half. So from here I can say this implies capital H is equal to 3 times head loss, or in other words, this implies that the value of head loss is equal to capital H by 3. This is a very, very important relationship. Very important relationship. For getting the maximum actual power possible, I am supposed to have head loss is equal to capital H by 3. And if head loss is equal to capital H by 3, I can say efficiency, which is 1 minus small h upon capital H into 100%, has to be equal to 1 minus capital H by 3 upon capital H into 100%. Now you see I can cancel capital H and capital H over here. I am having 1 minus 1 by 3, that gives me 2 by 3. Therefore, the value of efficiency is equal to 2 by 3 into 100% is supposed to give me 66.67%. So I can say that for getting the value of maximum actual power, I am supposed to have an efficiency of 66.67%. So we know that head loss should be h by 3 or efficiency should be 66.67%. This is half the job done. There is one more type of question that is asked over here, that is regarding the diameter at the exit of the nozzle. Let us look at that question. Diameter at the exit of the nozzle. So we want to find out over here diameter at the exit of nozzle for P actual maximum. For P actual maximum. Diameter at the exit of nozzle for P actual maximum. Let us first of all create some nomenclature over here. Imagine that the penstock is something like this. Then you are having a nozzle over here. You are having a nozzle over here. This is a nozzle. Let us say there is this capital D over here. Capital D is representing the diameter of penstock, and there is this small d over here. There is this small d over here. Small d is representing the diameter at the exit of penstock. So let me write, there is capital D, which is diameter of penstock, then there is small d, which is representing diameter at the exit of penstock, at the exit of nozzle, at the exit of nozzle. Diameter at the exit of nozzle. Fine. Furthermore, let us define two more things. Let us say capital L represents length of penstock, length of penstock, and F is the friction factor of penstock. It is a friction factor of penstock. It is a friction factor of penstock. Fine, these are some nomenclatures we are having. Our aim is to identify this value, small d value is equal to how much when we are having P actual maximum. How to approach this question? Let us draw a small diagram now. Imagine the reservoir was over here. This is going to be a rough diagram. You have a penstock, then you have a nozzle over here. You have a nozzle over here. Let us say this is the level of the fluid present. I extend this line further over here. I know that this height has got to be equal to capital H. This height is got to be equal to capital H. This is equal to capital H. And I know that if I draw actual EGL, let us say it comes something like this. Actually comes something like this. And I know that this distance has to be equal to head loss. This has to be equal to head loss. Fine. Let us take 2 points now. I choose a particular point over here. Let me take this as point 1. And I take another point over here at the exit of nozzle as point 2. Fine. These 2 points I have taken. Let us apply Bernoulli equation between these 2 points. So I am having by Bernoulli equation I can say that P1 by gamma plus V1 square by 2g plus Z1 has to be equal to P2 by gamma plus V2 square by 2g plus Z2 plus head loss. This is the equation I'm having. If you observe, both these points are exposed to atmosphere, therefore P1 and P2 cancel off. First thing, P1 and P2 have got cancelled. Second thing, at point 1 you are in the reservoir, therefore the velocity has to be 0. Velocity is 0. Next, if I take the value of Z2 as 0, automatically the value of Z1 becomes gross head, which is equal to capital H. Which is equal to capital H. From here I can say the value of capital H is equal to V2 square divided by 2G plus head loss. Plus head loss. This is the equation we are having. Now, I want to find out for the condition of maximum actual power. I have established already that for maximum actual power, head loss has to be equal to H by. So now let us see that. I have over here capital H is equal to V2 square G, V2 square by 2G plus this is by 3. This is H by 3, which implies from here that the value of V2 square 2G has to be equal to 2/3 of, or let me rather do this way. Let me do one thing. Instead of writing this as H by 3, let me write this as H only. What I am doing is, in place of capital H, let us say we write 3 times head loss. This is also fine, is it not? In place of capital H, I am writing 3 times head loss. Now you see over here, V2 square by 2G, I can write as 2 times head loss. This is equal to 2 times head loss. Fine. What is the value of head loss we know? We know that head loss has to be equal to, from here, V2 square by 2G is equal to 2 times FLV square by 2GD. Please observe over here. This velocity is different, this velocity is different. This is the velocity at the exit of nozzle. This is the velocity in the penstock. Okay, these two are two different things. I can cancel off 2G and 2G over here. If I cancel 2G and 2G, I am going to get now that the value of V2 square upon capital V square, V2 upon capital V square has to be equal to 2 times FL upon capital D. This is the value we are having. Now, by continuity equation, we know that the value of pi by 4 times small d square into V2 square, small d square into V2 has to be equal to pi by 4 capital D square into V. A1 V1 is equal to A2 V2. I can cancel off over here pi by 4 and pi by 4. If I cancel these two things off, I see that the value of V2 upon V1 is equal to how much? It is equal to D square upon small d square. It is equal to D square upon small d square, which implies from here I can say that the value of V2 square upon V square has to be equal to capital D power 4 upon small d power 4. Now in place of this, put that value. So you are having capital D power 4 upon small d power 4 is equal to 2 times FL upon capital D. This is the value I am having. If I look for the value of small d now, the value of small d power 4 is equal to d power phi upon 2 times fl, or you can say small d has to be equal to fourth root of capital D power phi upon 2 times fl. This should be the diameter at the exit of nozzle. This should be the diameter at the exit of nozzle if you want to have maximum actual power. So I can summarize over here. I can summarize for maximum actual power, there are two conditions to be satisfied. The first condition that should be satisfied is the value of head loss has to be equal to capital H by 3, or efficiency should be equal to 66.67%. Both these things are same. And second thing is the value of diameter at the exit of nozzle has to be equal to fourth root of d power 5 upon 2 times fl. These two conditions have to be satisfied. This is regarding the concept of hydraulic power. In examination, please do not use this directly. Use these conditions only if you are given that the power actual is maximum. If power actual is not maximum, then you cannot use any of these two conditions. Fine. You will have to develop the equation of small d. That you have seen how to do, right? After having seen the concept of hydraulic power, now let us look at the next power, which is known as pumping power. Pumping power. Pumping power. Now regarding pumping power, first of all, where do we use pump? We use pump in order to increase the energy in the fluid, is it not? Let us say you are having two reservoirs. One reservoir over here, one reservoir over here. There is another reservoir present over here. Another reservoir present over here. Let us say the fluid level is something like this. The fluid level is something like this. Imagine I connect over here some kind of piping system. This is a piping system I'm connecting. This, let us say, is reservoir R1, and this, let us say, is reservoir R2. Tell me, where will the flow take place from? Is it taking place from R1 to R2 or R2 to R1? It should take place from R2 to R1. The reason being, over here the total head is higher and over here the total head is lower. So real flow would take place from higher total head to lower total head. But imagine I want the flow to take place from R1 to R2. What should I do now? In order for the flow to take place from R1 to R2, I am supposed to install over here a pump. So let us say I am having a pump installed over here. Imagine a pump is installed over here. There is a pump installed over here. Our aim right now is to identify how much power should this pump supply to the fluid. Recall, previously what was happening in hydraulic power? The fluid was giving us power. Now what is happening? We, using some kind of mechanism, are giving power to the fluid. Are you following this thing? Now if you observe, let us say I take this difference in the elevation. The difference in elevation, let us say, is equal to capital H. The difference in elevation is equal to capital H. Fine. Let me take this point as certain point A and this point as some point B. And let us write Bernoulli equation between point A and point B. See what will happen if we write Bernoulli equation. So I can write over here by Bernoulli equation. By Bernoulli equation, what have we got? We have got the value of PA by gamma plus VA square by 2G plus ZA has to be equal to, it has to be equal to PB by gamma plus VB square by 2G plus ZB plus ZB. Next, since you are having losses also involved, you can write plus head loss. Now most important term over here, which is regarding pump, I am going to write minus head of pump. Minus head of pump. Fine. Observe over here, what all things can be cancelled off. I know that point A and point B, both of them are exposed to atmosphere. Therefore, the gauge pressure they are having is 0, cancelled off. I know that the velocity at A and velocity at B, both of them are same, 0 velocities, of course. From here, I can say the value of head of pump has to be equal to how much? It has to be equal to ZB minus ZA plus head loss. The difference in datum plus head loss. If you see, ZB minus ZA is equal to capital H. So I get over here that the pump has to supply a head which is equal to how much? It is equal to capital H plus loss. This is supposed to be the head that is supposed to be supplied by the pump. Now we are going to take two cases. First case, let us say we are having ideal flow. If ideal flow takes place, let us say case 1, if ideal flow is taking place, I would be having ideal pumping power. Ideal pumping power. Ideal pumping power. Fine. In the case of ideal pumping power, I am going to have head loss equal to 0. Head loss equal to 0. So the value of pumping power now, pumping power has to be equal to gamma into Q into head of pump. Gamma into Q into head of pump, that is equal to gamma into Q into head of pump. If you cancel off head loss, you are going to have only H. This is the value of pumping power ideal. So pumping power ideal is gamma into Q into H. Ideal pumping power. Ideal pumping power. Case 2, in reality, I am going to have head loss. So let us take case 2, wherein you are having actual pumping power. Case 2, actual pumping power. Actual pumping power. Now actual pumping power, the value of head loss is still going to be there. That means over here HP has to be equal to both H plus small h. So again I write over here pumping power is equal to gamma into Q into HP, and the value of pumping power now is going to be equal to gamma times Q times capital H plus small h. This is going to be the value of actual pumping power. Actual pumping power. So this is regarding the concept of pumping power. Please be careful. In the case of hydraulic power, you are having actual value as capital H minus small h. In the case of pumping power, you are actual value as capital H plus small h. Over there minus, over here plus. The reason now, you can think of it, the reason is over there you are getting the power from the fluid. When you get the power, you will get less than ideal. You will get less than ideal, therefore minus over here, over there. Over here you are giving the power. When you give the power, you are supposed to give more than ideal. These are the requirements for efficiency, right? So you have to give more than ideal, therefore plus over here. Now let us take some miscellaneous problems in flow through pipes. One very interesting problem is when the diameter of the pipe is a variable. Let us see an example. You have actually drawn the grade lines for such a case. Let us see that problem now. You are having a reservoir, let us say over here R1, excuse me. You are having a reservoir over here, let us say R1. You have another reservoir over here, R2. And you're seeing a tapering kind of pipe is moving from R1 to R2. The diameters are D1 to D2, length is L, friction let us say is a constant F, and the elevation difference of course is equal to head loss over here. All these things are given. You are supposed to identify the formula of head loss. The question is, develop the equation of head loss. What is the equation of head loss over here? Even though The value is known, but we have to develop the equation of head loss in terms of discharge, length, diameters, and whatever is given. Fine. How to approach this problem? First thing, we are going to use Darcy-Weisbach equation over here. Darcy-Weisbach equation. But you can say that how can we use Darcy-Weisbach equation if the diameter is variable? Because it was actually derived when diameter was supposed to be a constant. That is correct. We can use Darcy equation provided, let me mention over here, provided this L over here is much greater than the difference between these diameters D1 and D2. So if the length of the pipe is so much big in comparison to the difference between these diameters, then we can use this thing. For example, let us say you are having over here 40 centimeters. For example, let us say, one moment please. You are having, let us say, D1 equal to 40 centimeters and D2 is equal to 20 centimeters. And let us say the length of the pipe is equal to 1 meter. Length of the pipe is equal to 1 meter. Now what is happening? Value of D1 minus D2 over here, D1 minus D2 over here is equal to how much? 20 centimeters. Length is equal to how much over here? It is equal to 100 centimeters. You are seeing that L is greater than D1 minus D2, but it's in comparison to this thing. It is comparable. In this particular case, you can't apply this thing. The reason is diameter is rapidly decreasing or rapidly changing. For example, instead of having 1 meter, let us say, instead of having 1 meter, I was having over here 100 meters. 100 meters. Just imagine if it was 100 meters. If it was 100 meters, then what would happen? You are having L equal to 100 meters and D1 minus D2 equal to 0.2 meters. Now this is much greater than this value. In that case, the change in diameter is very, very small. Then we can apply this particular condition. Let us see how do we solve this problem now. Let us start the problem now. For solving this question, I am going to first of all start with differential head loss. So instead of writing that the value of loss, instead of writing that the value of head loss is equal to 112.1 FLQ square by d power 5, I am going to write differential head loss. Differential head loss is equal to 1 by 12.1 F times, I am not having complete length now, I am going to take a very small length dx times q square by d power 5. By d power 5. Now what is this dx? How to understand this dx? Let us see over here. Suppose at some distance x, I am going away. I am taking a thickness of pipe over here, very small thickness of pipe, let us say. This thickness of pipe, let us say, is equal to dx. This thickness of pipe is, let us say, equal to dx. Now if you observe, if the variation in diameter is very small, I say that this small length of the pipe, is as good as a uniform diameter pipe, and let us say the diameter over here is equal to capital D. My first aim is to attain the value of capital D as a function of x. With respect to x, how is the value of capital D varying? That I have to get. Once I get that, now what will happen? If you observe, f over here is a constant, q is going to be constant by the virtue of what do you call continuity equation. Only thing is dx and d power 5 are going to be real, and you can integrate to obtain the entire value of head loss. Let us see how do we do this thing. How to obtain the value of diameter in terms of x. I am seeing that the diameter is varying linearly with respect to x. So I can say the value of diameter has to be equal to initial diameter minus kx. Initial diameter minus kx. Next thing, how to get the value of k? If you have basic mathematical sense, you can straight away say the value of k is equal to change in diameter per length, therefore it has to be equal to d1 minus d2 upon L. It is going to be equal to d1 minus d2 upon L. If you find it difficult, then how do you proceed forward? Put the limits. Put the limits. What limit are you going to have? If you put the value of x as L, if you put the value of x as L, d has to become equal to how much? D has to become equal to d2. So let us say at x is equal to L, d is equal to d2. This is a boundary condition we are having. So what do we have now? We have over here d2 is equal to d1 minus k times L. From there again you will get the value of k, this much only. So let me save this value of k. Let me save this value of k, and let us say the value of diameter I am going to use is this thing. I hope this is understandable for you. Let us start solving the question now. I mentioned that I am going to start with differential head loss. The value of differential head loss is equal to 1 by 12.1 f into q square times dx upon d power 5. This is the equation we are having. Now let us write d in terms of x. So this becomes equal to 1 by 12.1 f into q square into dx divided by d power 5 is basically d1 minus kx whole power 5. This is the value we are having. This is equal to differential head loss. Now if I want complete head loss, I'll have to integrate this thing. So let us say complete head loss has to be equal to 1 by 12.1 f into q square multiplied to integral of dx upon d1 minus kx whole power 5, where x is ranging from, you can say x is ranging from 0 till x is equal to complete length L. This is what we have. Fine. Now if you integrate this thing, this is quite a simple integration. Head loss is equal to 1 by 12.1 f into q square multiplied to integral of this thing is equal to how much? I am going to have d1 minus kx whole power minus 4 whole divided by minus 4 multiplied to, now since it is integration I have to multiply to differential of inverse of differential of this thing, that is equal to minus 1 by k, and x over here has to range from 0 till x is equal to how much? L. Let me cancel off minus on both the sides. This minus and this minus I am cancelling off. If I cancel this off, now this value becomes equal to how much? This value of head loss becomes equal to 1 by 12.1 fq square by 4 multiplied to 1 by k value, k is equal to how much? d1 minus d2 by L. So I am going to have L upon d1 minus d2 multiplied to 1 by d1 minus kx power 4 ranging from x is equal to 0 till x is equal to L. X is equal to L. Now we know that when x is equal to L, the value of diameter is equal to d2. And when x is equal to 0, the value of this entire diameter is equal to d1. From there I can write the formula. The value of head loss, I'm writing the formula now. The value of head loss is equal to 1 by 12.1 FLQ square by 4 times d1 minus d2 multiplied to 1 by d2 power 4 minus 1 by d1 power 4. This is the formula. This is the formula for head loss we are having. This is the formula for head loss we are having. Now at this moment, let me tell you how to remember this thing. You already know 1 by 12.1 FLQ square by d power 5. In place of d power 5, you are getting these 4, this thing, and this thing. These terms you are getting in place of d power 5. Fine. In a better way, you can remember it something like this. Actually, I like to remember it like this. I like to remember it as, instead of d1, d2, I like to remember it as d bigger minus d smaller, because a positive value is going to be bigger minus smaller. And when it comes to inverse, this has to be d smaller and d bigger. This is how I like to do this. B stands for bigger diameter, S stands for smaller diameter. For this to become positive, you need bigger minus smaller. For this to remain positive, you need smaller, because it is inverse. So you need smaller minus bigger over here. This is the formula we are having. Now one question comes up over here. You are having a pattern. You are having a pattern of pipe, or a pipe which was something like this. What if the pipe was in this particular manner? You are having in this particular manner. So flow was taking place from bigger diameter to smaller diameter. What if the flow is taking place from smaller diameter to bigger diameter? Will this particular formula still hold good? The answer is yes, it has to hold good. Let us check once whether it is holding good or not. If you have understood it is holding good, then you can stop the video, you can understand from here, remember this formula and move ahead. If you are having doubts regarding whether this formula will still hold good, let us check it once. Imagine you are having a pipe which is something like this. I'm not drawing the entire diagram, and please excuse my artistic skills. Just understand the diagram now. Let us say this is d smaller, this is d bigger. I am going some distance x away. I am taking a thin thickness over here. The thickness is equal to dx and the diameter is equal to d. Entire length over here is equal to L. All these things you already know. The question now is, what is the value of d over here? The value of d is equal to how much? I can say the value of d is equal to d smaller plus kx. I see that my diameter is linearly increasing and it is increasing from ds till there, d smaller plus kx. What is the value of k? If you again do the limit thing, the value of k will be equal to how much? It has to be equal to d bigger minus d smaller whole divided by L. This would be the value of k. Okay. Let us again write the formula. The value of differential, one moment please. The value of differential head loss is equal to 1 by 12.1 F into Q square multiplied to dx upon d power 5. Dx upon d power 5. I know that I can write this d power 5 as ds plus kx whole power whole power 5. And I know this integration, it is going to be equal to 1 by 12.1 f q square divided by minus 4 multiplied to ds plus kx whole power minus 4 multiplied to 1 by k and ranging from x is equal to 0 till x is equal to L. X is equal to 0 till x is equal to L. This is what I'm having over here. Now, if I write this as plus, I can shuffle the limits. If I shuffle the limits, I'm having over here x is equal to L to x is equal to 0. Fine. Let us put in the values now. If I put in the values, I'm going to have, this is complete head loss. The value of complete head loss will now be equal to how much? 1 by 12.1 fq square by 4 multiplied to. Now this 1 by k is going to give me L upon d bigger minus d smaller. That is fine. It's going to give me this thing. Next thing. Now I know if I put the value of x is equal to 0 over here, ds will remain. So I'm having 1 by ds power 4 minus. If I put x is equal to L, I'm going to get d bigger. So db power 4. This is the equation. Now you observe, same equation it is. Nothing different. So you can say if the flow in a frustum kind of pipe is taking from either end, whether from a bigger diameter to smaller diameter to bigger diameter, from either end, the formula for head loss is going to remain the same. So you're having 1 by 12.1 FLQ square by, then in place of d power 5, you are having all these things put in. Of course, the kind of grade line is going to change, but the formula of head loss, net head loss, is still going to remain the same. This was first case in our miscellaneous problems. Now let us take this case under miscellaneous problems, one more case we are having. Imagine you have a pipe, and from this pipe water at every distance, some distance away, is moving out. It is getting discharged. Okay, you can imagine something like this. Let us say you're having some pipe over here and you're having taps everywhere over here, taps everywhere at some distance, and the fluid is discharging at the same flow rate from everywhere. The fluid is discharging at the same flow rate everywhere. Let us say the initial discharge you gave was Q. After some length L, there is no discharge over here. Q has become equal to 0. Entire discharge has come out from here. And let us say discharge per unit length, discharge per unit length is equal to small q. That is equal to basically per unit length how much discharge is getting out, or you can say capital Q upon L. This is the value of discharge per unit length you are having. Fine. So now we have to start solving how to obtain the value of head loss in this particular case. Let us start. Let us again draw the diagram. Imagine the pipe is something like this. The pipe is something like this. One moment, please. At this end, the pipe is closed because there is no discharge possible. Let us say I have given an input discharge over here, capital Q. The length of the pipe is equal to L, and I'm having from the side of the pipe discharge coming out. So you're having discharge coming out everywhere over here. We are assuming that this discharge coming out everywhere is constant, or the value of small q, which is equal to capital Q upon L, is equal to constant. It is equal to constant. Let us say the friction factor of this particular pipe is equal to F. All these things are there. My aim over here is to obtain the formula of head loss. How do we start this thing? To obtain the value of head loss, I realize over here that again my head loss needs to be started with differential head loss for a very small element of this particular pipe. Let us say after some distance L, let us say x rather, not L, after some distance x, I am taking over here a small thickness of pipe. Small thickness of pipe. Let us say this thickness is equal to dx. Since it is a very small thickness, I can say that the discharge over here is a constant. The discharge over here is a constant. Acha, how much is the discharge over here? What is the value of Q over here equal to? How much is the value of Q over here equal to? Let me rather show it with Q prime. What is the value of Q prime over here equal to? It is supposed to be the input discharge minus whatever discharge has already taken place in the downward direction of, and that is going to be equal to small q times x. Discharge per unit length times whatever the length I'm having over here. Fine. So this is the value of q prime I'm having. From here I can say that the value of differential head loss has to be equal to 1 by 12.1 f into dx into the discharge for the small pipe portion is equal to q prime square flq square by d power 5. Now what all things do I have constant? I have over here 1 by 12.1 constant, f constant, d power 5 also constant. So now from here I can say that the value of differential head loss has to be equal to 1 by 12.1 into f upon d power 5 times. Let us write the value of q prime now. The value of q prime is equal to capital Q minus q times x whole square times dx. This is the value. Furthermore, what I can do is, in place of small q, I can write capital Q by L. So let us do that also. If I want to find out complete head loss, I can say 1 by 12.1 f upon d power 5 into f upon d power 5 into integral x ranging from 0 till x ranging till L multiplied this. In the integral I'm having q minus, in place of small q I'm writing capital Q upon L times x whole square times dx. This is what I have. Fine. Very simple integration now. So from here you can see the value of head loss has to be equal to 1 by 12.1 f into, let me take this q outside so it becomes q square, that is the initial discharge square, upon d power 5 into 1 minus x by L square times dx integral ranging from x is equal to 0 till x is equal to L. This is my answer. What is the integral of 1 minus x by L whole square? It is going to be 1 minus x by L whole cube divided by 3 multiplied to minus 1 by L. Is it not? So let us write that value. the value of head loss we get is equal to 1 by 12.1 f into q square by d power 5 multiplied to 1 minus x by L whole cube multiplied to 1 by 3 multiplied to minus 1 by L minus 1 by L, excuse me, multiplied to minus 1 by L, and this is having the range of x is equal to 0 till x is equal to L. This is the value I'm having. If you observe, if I remove over here minus, I can shuffle the limits. So if I shuffle the limits, what do I have? This and this cancel off. Rather, I'm going to have from x is equal to L to x is equal to how much? 0. Fine. One moment please, I have made a mistake over here. That mistake over here is, I should rather, one moment, let us correct this thing. If you put the integral, you are going to have over here minus 1 upon 1 by L. It should be minus 1 upon 1 by L. Now this is ranging from where to where? X is equal to 0 till x is equal to L. If I remove minus, I can shuffle the limits, and the limits are going to become from x is equal to L to x is equal to 0. This is how my limits are going to become. Now let us see. If I put x is equal to 0 over here, it becomes 1 cube. If I put x is equal to L over here, I am going to get 0 cube. That means its value after putting in the limits is going to be equal to 1 only. If its value is equal to 1, then the formula of head loss becomes 1 by 12.1 f into, that L is on top, LQ square on d power 5 multiplied to 1 by 3. Now you see how easy this formula is. 1 by 12.1 FLQ square by d power 5 multiplied to 1 by 3. It is basically here, head loss is basically the 1/3 value of head loss if Q is constant. If the value of Q is constant, that means if I'm having a pipe from where there is no fluid moving out for every distance, how much the head loss would be? Its 1/3 value going to be the value of head loss over here. So you can remember this formula very, very easily. It is equal to 1/3 of 1 by 12.1 FLQ square by d power 5. This is the value of head loss. Now you see, memorizing this formula is quite easy. If you find all these things required for you, then forget about that. At least memorize the formula in this particular conditions. You have seen two cases still here in miscellaneous problems. One case was where diameter was a variable. Okay, even over there memorizing the formula was quite easy. One case over here where discharge is variable. See, whenever these variables are there, what we do is we try to take differential value of head loss, and whenever we take this differential value of head loss, we take it over a differential length, that is dx length. The moment you take it in for a length of dx, you have to get every other thing in terms of x, whichever is variable. For example, diameter was also as a function of x. Over here, discharge also was a function of x. From there onwards, you can proceed. Let us now start the last topic in the chapter of flow through pipes. This topic is known as water hammer. Water hammer. Simple topic. Not many questions have appeared from here in GATE examination, but this topic is quite favorite in IES examination, especially in theoretical kind of questions. Very simple theoretical questions. And let me tell you one more thing. This topic is a very interesting example of where you can have an incompressible fluid experiencing compressible flow. Before introducing itself, let me tell you, it is a good example of incompressible fluid experiencing compressible flow. Fine. You'll understand this as we move further. Let us start. In this particular case, we are going to be interested in a particular working fluid, which is water. That is why it is called as water hammer. Imagine that in a penstock, let us say you're having a very lengthy penstock. You must be knowing these penstocks stretch in kilometers. Let us say you have over here a nozzle. Let us say a nozzle over here. Suppose in this penstock, you are having a valve for regulating the flow. Somewhere over here, let us say you have a valve for regulating the flow. Suppose at a particular instant, you want to stop the flow, so you close the valve. The moment you close the valve, what happens is the fluid coming from here with the velocity retarding, and suddenly this kinetic energy is going to convert a pressure wave which is moving in the backward direction. A pressure wave is going to move in the backward direction. This pressure wave is going to be a compressible pressure, and the fluid over here in this region is going to experience a compressive flow. It is going to experience compressible flow. This compressible pressure wave is so strong that this penstock can even burst off. This pressure wave keeps on hammering, or it keeps on striking on the wall of this pipe. That is why this tendency is known as water hammer effect. So we can write down over here some theory as when a valve is closed, comma, when the sudden drop in kinetic energy, creates a compressible pressure wave, propagating in the direction against the flow, against the flow. So this pressure wave is going to propagate in the direction against the flow. Now this rise in pressure is going to induce some striking effect on the wall of the pipe, which is known as water hammer. The striking on the wall by this pressure is known as water hammer. Water hammer. Now it is quite evident from here that water hammer is something which is not desirable. Of course, it is non-desirable for us. Now since water hammer is non-desirable, we have to think of some method of controlling the adverse effect due to this water hammer, and that is very simple. In general, what we do is somewhere in the upstream of this valve, let us say somewhere over here, we are going to install a secondary tank. Let us say you install a secondary reservoir over here. Let us say a secondary reservoir, something like this, a secondary reservoir. This secondary reservoir you have installed is known as surge tank. It is known as surge tank. It is known as surge tank. Now, what happens when you install a surge tank? When you install a surge tank, this pressure wave, instead of propagating along the length of this particular penstock, will rather escape off from the surge tank. Once it escapes off, you have safeguarded this penstock. This is the advantage of having surge tank. In some cases, instead of having surge tanks, they install some chimney-like structures. Those are known as surge towers. Apart from this, you can have some diaphragms and all, which also can be used in place of surge tank. Moving further, let us now talk about the mathematics behind, or the formulas behind, the concept of this water hammer effect. Now, we are going to introduce a concept, or first of all, let us now talk about what are the parameters which are going to affect this rise in pressure. So, the rise in pressure can be a function of what all things? It can be a function of what all things? First of all, it can be a function of velocity of flow. V stands for velocity of flow. It can be a function of density of fluid. It can be a function of length of penstock. It can be a function of speed of closing, valve. Speed of closing valve. That is, are you closing the valve very quickly or very slowly? That also is going to determine the rise in pressure or water hammer pressure. So let me mention over here, V stands for velocity of flow. Velocity of flow. L stands for penstock's length, or length of penstock. Length of penstock. And density, of course, needless to mention, is the density of water over here. Generally, the working fluid is going to be water. We are discussing mostly about water. If it is not water, whatever fluid you are having, its density. Now let us talk about the formulas involved in the concept of water hammer effect. The first thing we are going to introduce over here is known as critical time of closure. It is known as critical time of closure. Critical time of closure. This critical time of closure is represented by capital T with a subscript C. Critical time of closure. How do we define this critical time of closure? Critical time of closure is defined as the time taken by the pressure wave to propagate back and forth the length of penstock. Back and forth the length of penstock. Very simple definition. It is a time taken by the pressure wave to propagate back and forth the length of pencil. So basically back means L, forth means again coming back to the valve. So it is 2L. It is going to be equal to 2L. So we can say that this critical time of closure has to be equal to distance over here is L plus L, that is equal to 2L upon speed. What speed is it? You see, the pressure wave, a compressible pressure wave is going to move at acoustic velocity speed, and that is given by C, acoustic velocity. So C over here stands for acoustic velocity. So let me mention this C over here is acoustic velocity. How do you define acoustic velocity? Acoustic velocity can be defined as the speed at which a compressible pressure wave travels in a fluid medium. And what is the formula for this acoustic velocity? Very simple formula. It is equal to root over of bulk modulus of fluid upon density of fluid. Root over of bulk modulus upon density of fluid. Fine. This is known as your critical time of closure. The time taken by pressure wave to move back and again come back to the valve is critical time of closure. Then you have one more time of closure. You have one more time of closure. And that time of closure is known as actual time of closure. Actual time of closure. Actual time of closure. This I am going to represent by T with a subscript A. T with a subscript A. So this is known as your actual time of closure. How do you define actual time of closure? Its name itself is mentioning the definition. It is a time taken for closing valve. For closing valve. It is a time taken, actual time taken for closing valve. Now one moment please. Let me tell you one more thing, that I have mentioned over here that the pressure is going to depend on these things. Please include over here one more thing, that is the bulk modulus. K over here stands for bulk modulus. Sometimes it can also depend on the Young's modulus of pipe and geometry of pipe. Include these things also. Geometry of pipe. In some rare cases, it can depend on these things also. Fine, the pressure can depend on these things. Apart from this, it can depend on bulk modulus of fluid, Young's modulus of pipe, and geometry of pipe. Moving further, we have defined over here two times of closure. One is known as critical time of closure. The other is known as actual time of closure. Now, depending on these two times of closure, we are having two types of closure. So let me mention over here types of closure. Types of closure. We are having two types of closure. The first type of closure. Imagine that you are taking a lot of time compared to the critical time in order to close the valve. So actual time of closure is greater than critical time of closure. So you are taking a lot of time in order to close the valve when compared to critical time. So basically you are slowly closing. That is why this type of closure is known as gradual closure. It is called as gradual closure. Gradual closure. The second type of closure, let us say the actual time taken is lesser than or equal to critical time. That means you are very quickly closing the valve. This is dangerous. And this type of closure is known as sudden or rapid closure. It is known as sudden or rapid closure. Rapid closure. This type of closure is known as sudden closure or rapid closure. So we are having these two types of closure. Now what we are going to do, for each of these types, we are going to look at the formula of water hammer pressure. How much is going to be the water hammer pressure? Let us see. Let me start with first case, that is gradual closure. First case over here is gradual closure. In the case of gradual closure, I am first of all going to look at the force exerted on the valve's face. Imagine that you are having a pipe, a penstock of length L, and you have over here a valve closing. Let us say something like this, a valve closing, a nozzle over here, This, let us say, is your valve V. Let me not represent by V because V is for velocity. V, let us say, is the velocity of flow over here. This is the valve. It is the valve. Let us say the cross-section area over here is A. Density of fluid is equal to rho. All these things are there. My first aim over here is to identify how much force is exerted on this particular valve closure. How much force is exerted by the virtue of retardation. I can say the force exerted over here has to be equal to mass times retardation. A over here stands for retardation. And what is it going to be? We know that mass has to be equal to density times volume. What is the volume of fluid present over here? The volume of fluid present over here is cross-section area A multiplied to length. This is the value of mass multiplied to retardation over here. You see, the velocity is moving from V to 0. Therefore, the change in velocity over here is equal to V, and it is moving from V to 0 in a time of t actual, that is TA over here. So this is basically the amount of force acting on the face of the valve. Now, I can say the value of pressure water hammer, the water hammer pressure has to be equal to how much? It has to be equal to this force upon cross-section area. It has to be equal to force upon cross-section area. So how much will the value of pressure due to water hammer be equal to? The pressure due to water hammer has to be equal to, force is equal to density times area times L times V divided by T actual multiplied to area. I can cancel off area and area over here. From here I get the formula for force. Very simple formula. The formula for, pressure. The formula for pressure due to water hammer. I'll just write WH for water hammer. The formula for pressure due to water hammer in gradual closure has to be equal to rho into V into L upon T. Rho into V into L upon TA. This is the formula for pressure due to water hammer in gradual closure. So let me save this as my equation number 1 over here. Next, we have to look at the rise in pressure due to water hammer in sudden closure. Let us see the second case. Second case having is rapid or sudden closure. Rapid or sudden closure. Sudden closure. What is going to be the formula for water hammer over here? Pressure due to water hammer. In this case, I'm going to have two subcases. Let us say 2.A. Two subcases. First subcase is when the pipe or penstock is rigid. Penstock is rigid. penstock is rigid. Basically, nothing is rigid. We know this thing. Any engineering material has to be having some modulus of elasticity which is finite. But what do I mean penstock is rigid? You are going to consider the penstock is rigid as long as the Young's modulus of penstock is not given. If Young's modulus is not mentioned, you will assume that the penstock is rigid. Fine. If the penstock is rigid, in this particular case, straight away we'll take the formula. The pressure due to water hammer is going to be equal to density into C into V. This is the formula. Rho CV, that is C over here again stands for acoustic velocity. C over here stands for acoustic velocity. Fine. Again recall the formula for C is equal to root of bulk modulus by rho. C is root over of bulk modulus by rho. Second case, let us say 2B over here, 2B. Imagine you're having an elastic penstock or non-rigid penstock. Elastic penstock. Let us say he says that the penstock is made of steel and steel is having 200 GPa, Young's modulus of elasticity. So basically let us say he has given you E is mentioned. E is a given value, let us say. What to do if E is a given value? This formula is not going to change. This formula will repeat itself. That is, the value of pressure due to water hammer is going to be equal to still rho into C into V. This formula shall not change. But the formula of acoustic velocity is going to change. The value of acoustic velocity over here will be equal to root over of effective Young's modulus effective bulk modulus divided by density. So basically, the fluid's compression and the penstock's compression, both of them are combining over here. Fluid's compression and penstock elasticity, both of them are getting combined over here. What is the formula for this effective bulk modulus? The formula for 1 by effective bulk modulus is equal to 1 by bulk modulus of fluid plus d upon T times E plus d upon T times E. Now what is this D? What is T? What is E over here? D over here stands for diameter of penstock. Diameter of penstock. T stands for thickness of penstock. Thickness of penstock. Thickness of penstock. And E over here is Young's modulus of penstock. Young's modulus of penstock. Young's modulus of penstock. Now you are seeing over here that this effective bulk modulus is having over here, if you see, it is having a fluid property and it is also having a penstock property. Both of them are going to combine to give you the effective bulk modulus for getting the pressure in the case of water hammer. So now I can think of this formula, always this formula is there. If you apply this formula for acoustic velocity in the case of rigid pipe, imagine you are having a rigid pipe, you are still applying this formula. In that case, Young's modulus is infinite. This entire value becomes 0. That means K effective will be equal to. So I would say better remember only this thing. Better remember this thing only. Whenever the Young's modulus is infinite, that time you will again get back, this case only. Fine. This is regarding the concept of water hammer, not that much important for GATE, but quite important for IES examination and ISC examinations. Now let us take up questions in flow through pipes. Let us start with some basic questions. Later on we'll go for previous GATE and IES examination questions also. Look at this question, it's a theoretical question. The question says, Darcy-Weisbach equation for head loss is valid for which kind of flow? Recall what is Darcy-Weisbach equation? It says that the value of head loss is equal to FLV square upon 2GD, also equal to 1 by 12.1 FLQ square upon D power 5. Now regarding this equation, when we were discussing, I have told you that this equation is going to be valid for any kind of internal flow as long as the flow has been fully developed and the flow is steady. Any type of flow, be it laminar or turbulent or even transition, as long as you know the value of F for that particular flow, you can use the formula. So now let us see what are the options given to us. Option A is only for laminar flow through smooth pipes. That should be wrong. One more thing that is wrong over here is when the flow is laminar, there is no point of talking about whether the pipe is smooth or rough. Even though that point might not be important in this question, but please bear in mind that smoothness or roughness of a pipe has nothing to do when flow is laminar. Let us move further. Option B says only for turbulent flow through rough pipes. Again wrong. Option C says for laminar or turbulent flow through smooth pipes only. Now this phrase over here, smooth pipes only, is making it wrong. We know that for every flow. Look at option D, for laminar or turbulent flow through smooth or rough pipes. This has to be correct. Therefore, option D over here is correct. The answer for this question is option D. Let us move further to the next question. Look at this question. It's a good one. It is worth 2 marks in gate examination. Similar kind of question has appeared in mechanical gate for 2 marks. Now, same question, similar question. Read the question for yourself once. The question says, water flows steadily through a smooth circular tube of diameter 5 centimeters at a flow rate of pi kg per second. This is supposed to be pi kg per second. It's a printing mistake. Pi kg per second. The water viscosity mu, please correct this, the viscosity is mu. The water viscosity mu is equal to 0.001 Newton second per meter square. Density rho is equal to 1000 kg per meter cube. 1000 kg per meter cube. The Darcy friction factor for a pipe of diameter D is given as 64 by Re for fully developed laminar flow. We know that very well. And 0.316 by Re power 0.25 for fully developed turbulent flow. You will be seeing this equation again later on. It is known as Blasius equation. The approximate pressure drop per unit length in fully developed region of the tube in Pascal per meter is how much? You are allowed to take the value of G as 10 meters per second square. So I hope the question is clear to all of you. Let us write down the given data now. Given data. The question says that the mass flow rate is pi kg per second. Even though he has mentioned only flow rate over here, but since the units are kg per second, I can say it is mass flow rate. So let me write over here, first thing, mass flow rate m dot is equal to pi kg per second. Pi kg per second. Next thing, viscosity is equal to 0.001 Pascal second. Viscosity is equal to 0.001 Pascal second. Next thing, density is given as 1000 kg per meter cube. Density is 1000 kg per meter cube. Now he has given you Darcy friction factor for laminar and turbulent flow. He says that FD, let us say F rather, Darcy friction factor is equal to 64 upon Reynolds number. Now this is for laminar flow. This is for laminar flow, and the value of F is equal to 0.316 into Re power minus 0.25. Now this is for turbulent flow. Turbulent flow. This much is given to you. Also given to you is the value of G. So let me write over here. You can assume the value of G to be 10 meters per second square. The question asked over here is regarding the value of pressure drop per unit length. So we have to find out over here delta P upon L is equal to how much? This is the question asked. Delta P upon L is equal to how much? Now at this stage I would recommend you to pause the video and think of what procedure or what method are you going to use, what steps you are going to use to identify the answer. Let us see. Delta P upon L is equal to how much? How to think of delta P upon L over here? Remember one rule. Drop in pressure is going to have a direct relationship with head loss. So since he's asking me regarding drop in pressure per unit length, I have to start thinking about how much is the value of head loss. So let us say the steps I'm going to employ over here. Suppose I want the value of delta P by L, for which I want head loss. But for head loss, I require the value of F. Now he has given me two formulas regarding the value of F. That means I am supposed to find out which flow it is or what is the Reynolds number. For Reynolds number, I require rho, V, D and mu. You see over here, I have rho, I have mu. I think I have D also, which I have not mentioned though. If you see, diameter is 5 centimeter. So let me write over here. Diameter is 5 centimeter. So diameter also is given. I don't have over here velocity. So let us say, first thing I will find out the value of velocity. First thing is I find the value of velocity. After finding the value of velocity, once I have rho, V, D and mu, I can find out the value of Reynolds number. So after velocity, Reynolds number. After Reynolds number, I'll find the value of friction factor. Once I have friction factor ready with me, next thing is I'm going to find out the value of, let us say, head loss. And from head loss, I will get the value of delta P by L. This is the procedure we are going to follow. Let us start now. Let us start. How do I get the value of velocity? Now you see, mass flux is given, diameter is given and density also is given. So how do you find the value of velocity? I can say velocity has to be equal to m dot upon density into area, because we know m dot is equal to rho AV, is it not? From there I'm get value, which implies velocity is equal to m dot is pi kg per second, density is 1000 and area is going to be pi by 4 into d square, that is 0.05 whole square. I can cancel off pi and pi on both the sides. After cancelling pi, 4 goes on top. So let us say this is equal to 4 upon 10 power 3 multiplied to 25 into 10 power minus 4. This would be the value. That is equal to 4 upon 2.5, or I can say velocity is equal to 1.6 meters per second. So the first thing I was supposed to find out, velocity, is known to me. Let me highlight this as some equation number 1. So velocity is done with. After getting velocity, next step is to use this velocity to identify the Reynolds number. Recall, what is the formula for Reynolds number? Reynolds number is equal to rho Vd upon mu. This is the Reynolds number. Let me put in the numbers over here. Put in the numbers. That is equal to, density is 10 power 3. Density is 10 power 3. Velocity is equal to 1.6. diameter is 5, that is equal to 0.05 meters upon mu is equal to 10 power minus 3. Now if you calculate this value, you would be getting the value of Reynolds number, Re comes out to be equal to 8 into 10 power 4. This is the value of Reynolds number we are getting. Let me save this as some equation number 2. I've got the value of Reynolds number. Now the next question, tell me, this Reynolds number is indicating towards which flow through pipe? Is it laminar flow through pipe or turbulent flow through pipe? Of course, this is going to be turbulent flow. It is well beyond 4000. So what I'll do next is I'll employ the equation given to me for turbulent flow. So I can write over here, since the flow is turbulent, I can now say that the value of F has to be equal to, the equation given to me was Blasius equation, which says that 0.316 into Re power minus 0.25. This was the value of F. Now if I put in the numbers given to me, so F is equal to 0.316 into 8 into 10 power 4 multiplied to power minus 0.25. If you calculate this value of F, it comes out to be equal to 0.01879. This is the value of friction factor. Let me save this as some equation number 3. This is the value of friction factor. I have found out the value of friction factor now. Now is the time to use Darcy equation. So what does Darcy equation say? We know that according to Darcy equation, the value of head loss is equal to FLV square upon 2GD. We also know that the value of head loss has to be equal to delta P upon gamma. We know both these things. Now I would want you to look at this equation over here, this part of the equation, that is FLV square upon 2GD is equal to delta P by gamma. I want delta P by L. The question asked to me is regarding delta P by L. So all I have to do is take this L from here, push it over here, gamma over here. So from here I can say that the value of delta P upon L that is asked is equal to, it is equal to F times gamma times V square upon 2GD. Furthermore, I can cancel the G from here and the G from here. I am remaining with density over here. Therefore, this is equal to F times density times V square upon 2D. This would be the value of delta P. Let us put in the numbers we are having. So the value of delta P upon L is going to be equal to, the value of F is 0.01879 times density is equal to 1000 times velocity is equal to 1.6, so square of this velocity. upon 2 times diameter. Diameter was the data, so 0.05 over here. If you do the calculation, then you're going to get the approximate value of delta P upon L to be 481. Since we have chosen SI units everywhere, this also should be in SI units, that is Pascal per meter. This is the answer to the question asked. This is the answer to the question asked. Now this question might seem lengthy to many of you, but let me tell you, it was not such a difficult question as well. You see, the moment you look in a question which is indicating towards friction factor and delta P, you should know somewhere there has to be a role of head loss plate, is it not? So you can create a sequence then. It is all about, see, whenever you see these kind of formula based questions for 2 marks in gate examination, it is all about creating the sequence and knowing the formulas. You should know what the sequence is. If you find it difficult to arrange the sequence, I would recommend you to go in the reverse manner. What do I mean by reverse manner? See, you wanted delta P. Let us say for delta P, I want head loss. For head loss, I want the value of friction factor. For friction factor, I want the value of Reynolds number. For Reynolds number, I want the value of velocity. Now you have gone in the reverse manner. Now it is arranged, first velocity, then Reynolds number, then friction factor, and so forth. Is it clear? Now this is all something which requires practice. So over a period of time, you will develop this speed, and you can become much quicker than me also. No problem about it. Anyway, let's go further to the next question. Look at the question. The question says 2 reservoirs are connected by a pipeline consisting of 2 pipes A and B of identical friction factor and length. So both the pipes are having same friction factor and same length. These 2 pipes are connected in series, fine. If the diameter of pipe A is 20% larger than that of B, then the ratio of head loss in A to that in B is how much? Okay, quite a simple question, worth 1 mark in examination. The key point over here is the type of connection. Connected in series. The moment you look at this thing, try to construct a diagram. Let us say you are having over here having a pipe over here. Let us say this pipe is pipe A. Then you have a pipe which is slightly smaller than pipe A in diameter. Don't scale my diagrams. Let us say something like this. This is A. Excuse me. This is A and this over here is B. Now regarding A and B, some things are established. They are given to us. That is, the length of A is equal to length of B, first thing. Furthermore, the friction factor in A is equal to friction factor in B. This also is given. Now, the next data is here. The diameter of pipe A is 20% larger than that of B. Let us say the reference we are taking for diameter over here is dB. dB, let us say, is equal to D. Then what would the value of dA be equal to? dA would then be 20% greater than that. It means it is equal to 1.2 D. So let us say dA is equal to 1.2 D and the value of dB is equal to D itself. The question asked over here is, what is the head loss of A to head loss of B ratio? How much is the head loss of A to head loss of B ratio? One more thing required over here, the relationship between the discharge of A and B. That is not given. But since the series connection is mentioned over here, it implies that the discharge in A is supposed to be equal to discharge in B. I hope you're following this. Discharge in both the pipes is going to be same. Now let us start solving the question. I'm writing the solution over here. Solution over here. We know that the formula for head loss is equal to 1 by 12.1 FL Q square upon D power 5. 1 by 12.1 into FL Q square upon D power 5. So now I can say that the value of head loss in A to that in B has to be equal to 1 by 12.1 FA LA QA square upon DA power 5 whole divided by 1 by 12.1 FB LB QB square upon DB power 5. Now let us see what all things can be cancelled off over here. 1 by 12.1, 1 by 12.1 can be cancelled off. FA and FB both are equal, so I can cancel those things. LA and LB are also equal, I can cancel those also. Furthermore, since discharges are same, I can cancel this also. This implies that the value of head loss of A upon head loss of B has to be equal to dB upon dA whole power 5. dB upon dA whole power 5. Now you see, dB we have taken as D and dA is equal to 1.2 D whole power 5. I can cancel off D and D over here. This is equal to 1 upon 1.2 power 5. This is the value. If you calculate this value, you are going to get the value of head loss in A to that in B ratio is equal to 0.402. This is the answer to the question asked. This is the answer to the question. Let us see which option it is. The answer is option A. Therefore, I can go here. Therefore, the answer is option A over here. This was quite a simple question. Let us move further to the next question. Read this question for yourself once. The question says two pipes of same length and different diameters, 10 centimeters and 20 centimeters are connected in series. Coefficient of friction is same for both pipes. Then diameter of an equivalent pipe of length equal to sum of lengths of two pipes is how much? Let us see how to solve this question. Again, we are having a question which is based on series connection. Series connection. The question, let's say, if we draw a diagram, we would have something like this. Let us say two reservoirs we are having connected by two pipes, let us say one is 10 centimeters, the other is 20 centimeters. Suppose this is how we are having. Let us say the level of fluid over here is higher, the level of fluid over here is lower. The flow, of course, should take place from here to here. This, let us say, is pipe 1 and this, let us say, is pipe 2. This, let us say, is pipe 2. Let me call this as reservoir R1 and this as reservoir R2. So we are having some setup like this. It is mentioned that the friction coefficient in both the pipes is same. Moreover, the length is also. So regarding pipe 1 and pipe 2, let us write down the data. Pipe 1, pipe 2. Let us write down the data. The data we are having over here is L1, let us say, is equal to L. L2 also is equal to L. Friction factor 1, let us say, is equal to F. Friction factor 2 also, let us say, is equal to F. Friction factors also same. Diameters now. The value of diameter D1 is equal to 10 centimeter. The value of diameter D2 is equal to 20 centimeter. This much is mentioned to us. The question asked over here is equivalent pipe is having sum of the lengths, that is L equivalent is equal to L1 plus L2, that is equal to twice L, 2L. What is the value of diameter D equivalent? D equivalent is equal to how much? This is the question asked. Now look at this and tell me, you are having series connection mentioned with friction factors and lengths same. Can we use Dupit's equation over here? Yes, we can use Dupit's equation. Now I can write by Dupit's equation. Let us start the solution. So I can say solution over here. We can say by Dupit's equation, we know that L equivalent upon D equivalent power 5 has to be equal to summation of Li upon Di power 5, where I is ranging from first pipe till nth pipe. In our case, it is very simple. We only have two pipes over here, so I can mention over here that L equivalent upon D equivalent power 5 has to be equal to L1 upon D1 power 5 plus L2 upon D2 power 5. This is what we have. Now let us put in the values. So what do we have? We know that L equivalent is equal to 2L. D equivalent is what we have to find out. So let me mention over here, D equivalent power 5 is equal to L upon D1 is equal to 10, so 10 power 5 plus L upon D2 is equal to 20, so 20 power 5. This is what we have. I can cancel L throughout. If I cancel L throughout, then I am having from here, 2 upon D equivalent power 5 is equal to 1 by 10 power 5 plus 1 by 1 by 20 power 5. If we solve for D equivalent, the equation we get is something like this. The value of D equivalent power 5 has to be equal to 2 divided by 1 by 10 power 5 plus 1 by 20 power 5. So the value of D equivalent over here has to be equal to 2 divided by 1 by 10 power 5 plus 1 by 20 power 5 whole in the fifth root. Now if you calculate this value, the answer for diameter D equivalent would come out to be equal to 11.4 centimeters. The value of D equivalent comes out to be equal to 11.4 centimeters. Take this question now. The question says diameter of a circular pipe suddenly increases by 2 times. Fine, you are having a sudden expansion taking place. The question further says the ratio of loss of energy to the velocity head before expansion is how much? Strictly speaking, the question should be the ratio of loss of energy head to the velocity head before expansion is how much? The reason why it should be head is because you cannot have ratio of energy to head. You should have ratio of head to head. Is it not? Anyway, let us draw a diagram to understand this better. Suppose you are having a pipe. This pipe is connected to another pipe. Let us say expansion is taking place. Suppose the diameter of the pipe D1 is equal to D. The diameter of this pipe D2 is equal to 2 times D. You are having a flow taking place in this direction. It is a case of sudden expansion we are having. We are having a case of sudden expansion. Suppose this is section 1 and this over here is section 2. Velocity over here is V1, velocity over here is V2. Let us first of all out what should the value of head loss due to expansion be equal to. We know that head loss due to expansion is equal to V1 minus V2 whole square by 2g. This is the value of head loss due to expansion. I can as well write it as this is equal to V1 square by 2g multiplied to 1 minus V2 upon V1 whole square. This should be the value of head loss due to expansion. Now please observe what the question is asking. The question is asking ratio of head loss due to expansion to that of velocity head. So basically the question over here is talking about head loss due to expansion upon velocity head, that is V1 square by 2g is equal to how much? That means this term I have taken on the left hand side as denominator. So this will be equal to 1 minus V2 upon V1 whole square. This should be the value. Now next thing, what is the value of V2 upon V1? Let us see over here. Look over here. According to continuity equation, I can say V2 upon V1 has to be equal to A1 upon A2, because we know A1 V1 is equal to A2 V2. From there we are having V2 upon V1 is equal to A1 upon A2, which should also be equal to D1 upon D2 whole square. It should also be equal to D1 upon D2 whole square, because we know area is proportional to diameter square. So what I'm going to do next is, I'm going to rewrite this equation. I'm going to rewrite this equation as head loss, head loss due to expansion upon V1 square by 2G equal to, it is equal to 1 minus, in place of V2 upon V1 I am writing over here D1 upon D2 whole square further squared. This is the value. Now we know that the value of D1 upon D2 is half. The reason is diameter is doubling. If it is half, then this is equal to 1 minus half squared then whole squared. Half squared then whole squared. So from here I can say that the value of head loss due to expansion upon V1 square by 2G is equal to, it is equal to 1 minus half squared is 1 by 4 whole square, which is equal to 3 by 4 whole squared, and ultimately this value is equal to 9 upon 16. So the answer to the question is 9 by 16. If you check which option over here, then you see option C is correct. So I can say the answer to the question is option C, 9 upon 16. Now this question is again a simple question on expansion losses or minor losses. One of the minor losses we have seen was expansion losses. Let us move further to a very good question worthy of 2 marks in examination. Read the question for yourself. The question says 2 pipes A and B with details as shown below are connected in parallel between 2 points. So this is a case of parallel connection, and he has given you the values of diameter, length and friction factor of both A and B. Fine. The size of equivalent pipe is 175 meters. That is, the length of equivalent pipe is given to you as 175 meters and is having a friction factor equal to 0.015. You are supposed to identify the diameter of the pipe is how much. Fine. The length is given over here. So length of the pipe is given over here. Friction factor of equivalent pipe is also given. We are supposed to find out diameter of equivalent pipe over here is equal to how much? Diameter of equivalent pipe is equal to how much? This is the question asked. Now how to solve this question? Recall for equivalent pipes, what all things do we know? We know 2 things regarding equivalent pipes. First thing, that the discharge of equivalent pipe is going to be the sum of discharge of individual parallel pipes. Is it not? In the case of parallel pipes, we know discharge is going to be sum. And the head loss of equivalent pipe has to be equal to head loss of each of the pipes. Is it not? So let us start the solution. I am going to write the table again. But this time when I write the table, let us say we write it like this. Pipe, we are having diameter in mm, we are having length in meters and friction factor. we are having three pipes over here, A, B, and not to forget the most important one, which is equivalent pipe. Now the data given to you is, this is having a diameter equal to 100, this is having 80. The question is to identify this diameter. The length over here is 150, the length over here is 150, the length over here is 200, and the length over here is given to you as 175 meters. Fine. The friction factor over here is 0.02, over here it is 0.015, this also has 0.015 as the friction factor. So this is given to you and you are supposed to identify the diameter of equivalent pipe. I would suggest you to observe over here. Both these friction factors are identical. That can be helpful sometime later. Now what I do is, I write down the things we know regarding equivalent pipe for parallel connection. We know that, first of all, the value of Q equivalent has to be equal to QA plus QB. Furthermore, the value of head loss equivalent has to be equal to head loss A has to be equal to head loss B. Now what I do, let us say, I write down the full expansion of head loss. So I am going to have over here 1 by 12.1 FLQ square by D power 5 for equivalent pipe has to be equal to 1 by 12.1 FLQ square upon D power 5 for pipe A. Pipe A has to be equal to 1 by 12.1 FLQ square upon D power 5 for pipe B. This is the sequence I am having. I can cancel off 1 by 12.1 throughout. 1 by 12.1 throughout. So I will be having over here FLQ square upon D power 5 for equivalent pipe has to be equal to FLQ square upon D power 5 for pipe A has to be equal to FLQ square upon D power 5 for pipe B. This is what I have. Now let us see how to start this question. After establishing these things, what I'll do is, first of all, I will take these two into consideration. I'll take these two into consideration. In the given data, I'm having the value of F, L and D for pipe A, F, L and D for pipe B. Neither do I know the value of QA nor do I know the value of QB. But what I can do over here is, I can develop a relationship between QA and QB. So let us say I develop QA is equal to something times QB. So basically I am getting the value of QA in terms of QB. What is the advantage if I get the value of QA in terms of QB? Observe over here. Over here you are having Q equivalent as a sum of QA and QB. Imagine QA also becomes in terms of QB, then you can write Q equivalent also in terms of QB, something in terms of QB. After you get Q equivalent in terms of QB, now look over here. you are having F equivalent, you are having L equivalent, you have Q equivalent in terms of QB, you have F, L and QB as QB itself and diameter of B as diameter of B itself. If you take this and this in a single equation, the only unknown over there will be the value of diameter equivalent. So my sequence is, first step is to identify QA in terms of QB, second step is to identify Q equivalent in terms of QB, then equate head loss equivalent to head loss B. From there you will get the value of diameter of B, diameter of equivalent pi. Let us start now. I am starting with the first step over here. First step says that the value of, one moment please, the value of FA into LA into QA square by dA power phi has to be equal to FB into LB into QB square upon dB power phi. This is the first step over here. I want the value of QA in terms of QB, so I can write QA is equal to QB square root of FB upon FA times LB upon LA divided by dB upon dA whole power phi. This is what we have. This is what we have. Now put in the values of FB, FA, LA, LB and all those things. Let us see what those values are once. So we have over here QA is equal to QB times root over of FB we know is equal to 0.015 upon FA is 0.2, LB is 200, LA is equal to 150 upon dB is equal to 80 and dA is equal to 100 whole power phi. So now you can cancel off these things. The value of QA comes out to be equal to square root of 1.25 power phi. This is the value of QA, which into QB, which is equal to 1.747 times QB. So let us say QA is equal to 1.747 QB. Let me save this as some equation number 1. This, let us say, some equation number 1. After getting the value of QA in terms of QB, what do I have to do next? I have to now write down the value of Q equivalent in terms of QB. We know Q equivalent is equal to QA plus QB, that is equal to 1.747 QB plus QB. So from here we can say Q equivalent has to be equal to 2.747 times QB. So we have the value of Q equivalent also in terms of QB. let me save this as some equation number 2. Final step now, I have to equate head loss equivalent equal to head loss of B. From there we know that since 1 by 12.1 already got cancelled, so F equivalent into L equivalent into Q equivalent square upon D equivalent power 5 has to be equal to FB into LB into QB power 5, sorry, QB square upon DB power 5. We already know the friction factor of equivalent pipe and B are same. And I can now write Q equivalent in terms of QB. So what do I have from here? I have 175 times 2.747 square into QB square upon D equivalent power 5 has to be equal to LB over here is equal to 200 times QB square upon DB is equal to 80, so 80 power 5. I can cancel off QB square and QB square from here. If I simplify this and find out the value of D equivalent, I am going to get the value of D equivalent is equal to 116.7 mm. It is going to be equal to 116.7 mm. This is the answer to the question. Now if you look at the options, which option is correct over here? Let us see. He has given you over here 4 options: 87 mm, 117 mm, 243 mm, 167 mm. The option 117 mm is going to be correct. This is the answer to the question. Let us take this question now. The question says, 2 reservoirs are connected through a 930 meter long 0.3 meter diameter pipe which has a gate valve. The pipe entrance is sharp, coefficient of loss is 0.5, and the valve is half open, coefficient of loss in the valve is 5.5. The head difference between the 2 reservoirs is 20 meters. Assume that the friction factor for the pipe is 0.03. The value of gravitational acceleration is 10 meters per second square. The discharge in the pipe accounting for all major and minor losses is how much, is the question. It is important to note over here that he is asking you to consider accounting all minor and major losses. Let us see how to start this question. Let us first of all start with the diagram. Let us say you are having a reservoir over here, In this reservoir you are having some fluid up till this level. You have another reservoir, let us say over here, another reservoir. You are having the fluid up to some level over here. Now if I measure the difference in level, that is, if I extend this line, if I measure the difference in this elevation, then this is equal to head loss, that is equal to 20 meters. I have a pipe connected over here. The length of the pipe is mentioned, and somewhere in between you are having a valve also present. Let us say this is reservoir R1, this is reservoir R2. R2 over here. How many minor losses are we going to have? We are going to have 3 minor losses over here, 1 minor loss over here, 1 at valve, and 1 at this point. So exit loss, valve losses, entry losses, all 3 losses you are going to have. Let us write the given data. The given data over here is given data over here. The value of head loss is given to you as 20 meters. The length of the pipe is given to you as 930 meters. Friction factor is given to you as 0.03. 0.03. Let us say the coefficient of loss over here C1 and over here coefficient of loss, let us say C2. The value of C1 is given to you as 0.5. The value of coefficient of loss C2 is given as 5.5. 5.5. Furthermore, the diameter, has he mentioned the diameter over here? Yes, he should have mentioned the diameter. 0.3 meters diameter is given. G is given to you. Diameter is equal to 0.3 meters. The value of acceleration due to gravity is equal to 10 meter per second square. All these things are mentioned. We are supposed to find out the discharge. So you are supposed to find the value of discharge Q. The value of discharge over here is how much? In meter cube per second. You're supposed to find this value in meter cube per second. Now let us create the sequence first of all. We know that the net head loss is 20 meters. So now the sequence I am going to arrange over here is, once I know that the net head loss is equal to 20 meters, I can say this is equal to head loss major plus head loss minor. Head loss major and head loss minor. Both these things I can get in terms of V. I can get in terms of V, because we know that head loss major also is going to have proportionality with velocity square. Head loss minor also comes in terms of some velocity square. From there I can get the value of V. Once I get the value of V, then I can use continuity equation. I can get the value of discharge. This is how I'm going to approach the question. So let us start the solution now. Let us say I know that head loss is equal to head loss major plus head loss minor. Head loss is equal to head loss major plus head loss minor. We know that this net head loss is equal to 20 meters. This net head loss is 20 meters. It is equal to FL V square by 2GD plus. There are 3 head losses minor over here. First one is the entry loss, which is C1 into V square by G. Second one is the valve loss, that is equal to C2 into V square by 2G. Third one is the entry loss. He has not given you the coefficient for entry loss. Since he has not given you the coefficient of entry loss, you can say it is equal to V square by 2G. Because if you remember, in the case of entry loss, V1 minus V2 whole square by 2G, V2 is equal to 0, so it becomes V square by 2G. We have discussed all these things. Now I can say this is equal to V square upon 2G common 2. Let us say 20 is equal to V square upon 2G common 2. I have over here FL by D plus C1 plus C2 plus 1. Now it is time for us to put in the numbers. So I can say 20 equal to V square upon 2G is again equal to 20. 2G is again equal to 20. F over here is 0.03. L is equal to 930 and diameter is equal to 0.3 plus C1 is equal to 0.5, C2 is equal to 5.5 and 1 is as it is. 1 is as it is. Now look at these calculations. I can say these two cancel off and 10 remains in the denominator. Then this 0 cancels with this 0. So what do I have now? Let us take this 20 over here. So 400 is equal to V square times 93 plus, add these things up, you have 0.5 and 5.5 should give you 6. 6 plus 1 is going to give you 7. So plus 7. From here you can say V square is equal to 400 divided by 93 plus 7 is equal to 100, that is equal to 4. From here you can say that the value of velocity is equal to 2 meters per second. Half the problem is done. Let me say some equation number 1. Velocity is equal to 2 meters per second. After having obtained the value of velocity as 2 meters per second, next thing we can find the value of discharge. Excuse me. We know that discharge has to be equal to area times velocity, that is equal to pi by 4 times d square times velocity, that is equal to pi by 4 into 0.3 square times velocity is equal to 2. If I calculate from here, I get the value of discharge is equal to 0.141 meter cube per second. This is the value of discharge, 0.141 meter cube per second. Now let us take up this question over here. This is a very good question, worth 1 mark, but really good question. The question says, for a flow through a smooth pipe, the fanning's friction factor is given by F is equal to m into Re power minus 0.2. In the turbulent flow regime, where Re is the Reynolds number and m is a constant. Water flowing through a section of this pipe with a velocity of 1 meter per second results in a pressure drop of 10 kilopascal. What will be the pressure drop across this section in kilopascal when the velocity of water is 2 meters per second? So the question basically is saying that you are having two cases. You are having two cases, case 1 and case 2. Case 1 and case 2. You are having the velocity and drop in pressure also mentioned. In case 1, the velocity is equal to 1 meter per second and drop in pressure was equal to 10 kilopascal. If you have doubled the velocity over here, what is the value of drop in pressure in kilopascal that is asked? Again, I am recommending you to recall that drop in pressure has a direct relationship with head loss. So how to solve this question? I know that drop in pressure is proportional to head loss. is proportional to head loss. So I can say over here drop in pressure is proportional to, I can say FLV square by 2GD, FLV square by 2GD. Now please observe over here, when you are changing the velocity, the Reynolds number is going to change, eventually the value of F also will change. So when you're changing velocity, only F and velocity, these two things are going to change, whereas L upon 2GD will remain a constant. If it is remaining a constant, from here I can say that, delta P over here has to be proportional to F times V square. Delta P has to be proportional to F times V square. Furthermore, we know that F over here is proportional to Reynolds number power minus 2. So I can say it is proportional to Re power minus 0.2 into V square. Now recall, what is the formula for Re? Re is rho V d by mu. Re is rho V d by mu. So let me write over here, Re is equal to rho V d by mu. I see that when I am changing the velocity, neither density nor diameter nor viscosity are changing, only velocity is changing. So ultimately I can say from here that delta P is proportional to, now in place of Re's proportionality I can write velocity's proportionality. So velocity power minus 0.2 multiplied to velocity square, which further implies that delta P has to be proportional to velocity power 1.8. This is the relationship between delta P and velocity in this particular condition. Now I can say the proportionality can be shifted to ratio as delta P1 upon delta P2 has to be equal to V1 upon V2 whole power 1.8. Now we know that delta P1 is equal to 10 upon delta P2 has to be equal to V1 over here is equal to 1 and V2 is equal to 2. From here I can say that delta P2 has to be equal to how much? It has to be equal to 10 into 2 power 1.8. This is the value. If you calculate this value, the value of delta P in case 2 comes out to be equal to 34.8 kilopascal. The value of delta P2 comes out to be equal to 34.8 kilopascal. Now if you check the option over here, that is going to be option C. So the answer to this question is option C, 34.8 kilopascal. Let us take this question. It's a very good question, worthy of examination, but only for 1 mark. The question says, in order to increase a discharge through a horizontal circular pipe, a similar pipe of half the length is added in parallel to the central half length of the original pipe. Fine. Assuming that the end conditions of the pipe remain unchanged, the percentage increase in discharge is how much? Neglect the minor losses is asking. Now this is a very good question. The reason is it is having a small concept also, that is whenever you want to increase discharge, I have told you that there are some methods of increasing discharge when you are having fixed reservoirs. One of the methods is to add a pipe in parallel. One more method is you can also employ a pump. Now over here he has added a parallel pipe. So let us say In this diagram, this over here is the main pipe, and this over here is an additional parallel pipe, He has added a pipe in parallel. Further, he is saying assume that the end conditions remain unchanged. This is a very important phrase. End conditions are remaining unchanged. What do we mean by this? First of all, please understand that these two pipes are between two reservoirs. Let us say this is some reservoir R1, and over here I am having another reservoir R2. Let us say I have some fluid level over here, I have some fluid level over here. That means between these two the head loss is this much. This is the value of head loss. End conditions are remaining unchanged basically means that the value of head loss between these two reservoirs is not changing. The value of head loss between these two is not changing. Now what you have done is you are having a main pipe over here, and in between you have added half a length parallel pipe over here. Let us say this is reservoir R1, this is reservoir R2. This much is given to us. Now we have to identify how much is the percentage increase in discharge. Let us see how to do this thing. Let us start with case 1 when you are not having a parallel pipe. So let us say case 1, in the absence of parallel pipe, in the absence of parallel pipe, Now what happens in the absence of parallel pipe? Let us say the discharge was equal to Q. I am neglecting minor losses as mentioned in the question. So I can say head loss, which is a constant, it is equal to 1 by 12.1 F L Q square upon D power 5. This is the value of head loss. Let me save this as some equation number 1. Now case 2 over here. Case 2, let us say case 2, after adding parallel pipe, Now what happens after adding parallel pipe? The value of head loss would still remain same. The value of head loss is again equal to H. How do we know that? Because he is saying end conditions are remaining unchanged. So head loss still remaining H. But now the equation of H is going to change. I am going to write down first of all for this portion. The length over there is equal to L by 4, and let us say the discharge over here is some discharge Q prime. So now for this length L by 4, I can write the head losses 1 by 12.1 F into L by 4 times Q prime square by D power 5 plus. Now what is happening after the fluid has reached this particular node, it is bifurcating into main pipe partially and the rest into parallel pipe. What is the ratio in which they are dividing? They are dividing exactly in half and half. The reason is both these pipes over here are identical in diameter, friction factor and length. Length means from here till here only in length. So since they are both identical, even the discharge has to bifurcate equally over there. That means the discharge in this particular portion now is going to be Q prime 2. If it is so, if I take the head loss over there, and I'm not supposed to take n number of times head loss. That means 2 times I don't have to take head loss over here, only once, because all parallel pipes are going to have same head loss. So now I can say for that portion 1 by 12.1 F into L by 2 is the length. The discharge over there is Q prime by 2 whole square upon D power 5. Then afterwards what happened? Both these discharges will merge and enter into this last portion of the pipe. So again the discharge over here is Q prime. So therefore for this portion I'm going to have 1 by 12.1 F, length over there is equal to L by 4 Q prime square upon D power 5. This is the equation I'm having. Let us see, I save this equation as equation 2. I save this equation as equation 2. Please observe this thing and identify if you're having any doubts. You can refer back to the video again if you have any doubts. What I'm going to do next is, I see that equation 1 and equation 2 both have same LHS. So I equate RHS of both these equations. So now I can say that since equation 1 equal to equation 2, I'm equating their RHS now. So what do I have? 1 by 12.1 FLQ square by D power 5 is the RHS of portion 1, has to be equal to 1 by 12.1 F L by 4 Q prime square by D power 5 plus 1 by 12.1 F L by 2 into Q prime by 2 whole square upon D power 5 plus 1 by 12.1 F into L by 4 times Q prime square by D power 5. This is what we have. What all can we cancel? I can cancel 1 by 12.1 F, L and D power 5. 1 by 12.1 F, L and D power 5. 1 by 12.1 F, L and D power 5. Likewise over here, if I cancel these things, what am I left with? I am left over here with Q square is equal to, Q square is equal to, over here I am having Q prime square by 4 plus, please observe over here, I am having a half over here and half square over here. That means I have Q prime square by 8. And finally again I have Q prime square by 4. Therefore the value of Q square has to be equal to 5 Q prime square divided by 8. This is what we have. Now I can say that the value of Q prime upon Q is going to be equal to root over of 8 upon 5, which is equal to 1.26. So Q prime by Q is equal to 1.26. That means percentage increase has to be equal to 0.26 into 100%. That is equal to 0.26 into 100%, which is equal to 26% increase. The answer to the question is the percentage increase by adding half the pipe in parallel is 26%.